everybody. I'm Wolf. I'm from Developer Relations. We have a big day ahead of us, full of fascinating talks. We have a big chunk of the Google Brain and research teams here to help, research Brain and research teams here to help you during the breaks and talk to you. But for now, we're going to start the live stream in just a minute. So if you have like a noisy phone, now would be a great time to turn it down. Also, there is an exit here. There is an emergency exit behind you, just in case. Probably won't happen. We want everybody to have the best possible experience at the summit. This is an inclusive community. No matter what your experience or your background, you are welcome here. We encourage you to be excellent to each other, to say hi to new people, to build on each other's ideas, and report any uncomfortable experiences. We have a zero-tolerance policy on harassment of any kind, and our full code of conduct is posted around the venue and on our website. Please share your positive and constructive feedback with all of the staff and speakers. So let's make this the best developer summit ever. And with that, let's get this thing started.
Good morning, everybody. I'm Anita Vijaykumar, Technical Program Manager for TensorFlow. Welcome. Good morning to all of you. It's really exciting to be here with all of you today, and welcome to the 2018 TensorFlow Developer Summit. We have a packed day filled with lots of interesting talks and some really cool demos. We hope you enjoy it as much as we do. As you know, we are together embarking on a transformative journey in the field of machine learning and artificial intelligence. Problems that were impossible or too complex are now possible to solve using this technology. This field is unleashing new frontiers and substantially changing many aspects of our lives in a meaningful way. We've already seen great advantages in many different areas with machine learning. Some examples are, in the field of astronomy, hunting for new planets is no easy task. These planets are small, cold, dark objects compared to their host star. Researchers and astrophysicists have analyzed large amounts of data from the Kepler mission, and by using machine learning, have discovered a brand new planet called the Kepler-90I, making it the only 8-planet solar system that we know of in our universe other than our own. In healthcare, we have discovered that looking at scans of the human eye, machine learning can assess a person's risk for cardiovascular diseases. Just imagine if the screening can be done with a mobile device, how profound the effect will be. Suddenly, the whole world will have access to rapid, easy, affordable, non-invasive screening for heart diseases, saving lots of lives. In aviation, trajectory prediction is a critical component to ensuring that aircrafts can fly safely and efficiently in crowded spaces. Engineers and air traffic controllers in Europe are using machine learning to predict the trajectory of a flight through the airspaces of Belgium, Luxembourg, Germany, and the Netherlands. This has more than 1.8 million flights per year and is one of the most dense and complex airspaces in the world. In dairy farming, we know that a cow's health is vital to the survival of the dairy industry. And folks at Connectera, a company in the Netherlands, wondered if they can use machine learning to track the health of cows and being able to provide insights to farmers and veterinarians on actions to be taken to ensure we have happy, healthy cows that are high yielding. So we now have happy cows not only from California, but also the Netherlands. Fighting climate change. Fighting climate change and in protecting our forests, we believe that technology has a huge role to play. A group of engineers and scientists have built real-time detection and alerting mechanisms to detect logging of trees. They listen to real-time data from chainsaw sounds, from trucking sounds, from logging sounds, and machine learning is fighting deforestation and protecting our precious rainforests. In music, there are many machine learning algorithms using deep neural networks that can learn the characteristics of sounds and create completely new music based on these characteristics. In arts and culture, you can even search if you have a long-lost twin from the past by looking at oil paintings that are using apps that are based on machine learning. How cool is that? At Google, we are an AI-first company, and every product is being fundamentally impacted and changed by machine learning, be it the popular Google Home, or the Pixel, or Search, or YouTube, or even Maps. Do you know what is fascinating in all these examples? TensorFlow is at the forefront of them, making it all possible. A machine learning platform that can solve challenging problems for all of us. Join us on this incredible journey to make TensorFlow powerful, scalable, and the best machine learning platform for everybody. I now invite Rajat, Director of Engineering of TensorFlow, to tell us more about this. Thank you.
Hello, everyone. Good morning. Thanks, Anita. So let's take a look at what we've been doing over the last 2 years. It's been really amazing. With lots of new releases, we've seen the popularity of TensorFlow really grow over the last 2 years. Especially over the last year, we've focused on making TensorFlow easy to use. And with release of higher-level APIs, like TF Data and TF Keras, and new programming paradigms like eager execution, really continue to make that easier. Earlier this year, we hit the milestone of 11 million downloads. Really excited to see how much users are using this and how much impact it's having in the world. So here's a map showing self-identified locations of folks on GitHub that have started TensorFlow. And you can see that it goes all the way up to the Arctic Circle with Tromsø in Norway, and all the way south down to Deception Island, which is part of Antarctica. In fact, TensorFlow is used in every single time zone in the world. An important part of any open source project are the contributors themselves. The community is made of the people who make this project successful. I'm excited to see over 1,000 contributors from outside Google who are making contributions not just by improving code, but also by helping the rest of the community by answering questions, responding to queries, and so on. Our commitment to this community is by sharing our direction in our roadmap, inviting public participation on design direction, and by creating SIGs that help focus collaboration on the key needs, like build-in packaging, TensorBoard. Ed will be talking more about this in detail later this afternoon. Today, we are launching a new TensorFlow blog. We'll be sharing work by the team and the community on this blog, and we would like to invite you to participate in this as well. We're also launching a new YouTube channel for TensorFlow that brings together all the great content that's been created for TensorFlow. Again, all of these are for the community to really help build and communicate. All day today, we'll be sharing a number of posts on the blog and videos on the channel. The talks you're hearing here will be made available there as well, along with lots of conversations and interviews with the speakers. To make reuse and sharing easier, today we are launching TensorFlow Hub. This library of model components is easy to integrate into your models with just a single line of code. Again, goes back to really making things easy for you. Machine learning is important and powerful, as you saw. We care about bringing it to more and more people. As part of this effort, we recently released a machine learning crash course focused on introducing this to a much broader audience. The same course that's trained thousands of Googlers in machine learning and allows us to integrate ML into everything we build is now available to everyone. TensorFlow started as a library for numerical computation with a focus on deep learning and neural networks. Since the early release, it's grown to include a very rich collection of machine learning algorithms. It includes popular algorithms like linear regressions and decision trees, commonly used for many structured data classification problems. There's also a very broad collection of state-of-the-art tools for stats and Bayesian analysis in the TF Probability Library, and several new additions are being released today. You can check out the blog post and website for more details. As I mentioned earlier, one of the big key focus points for us is to make TensorFlow easy to use. And towards that, we've been pushing on simpler APIs, easier to use, and making them more intuitive. At the lowest level, our focus is to consolidate a lot of the APIs we have and make it easier to build these models and train them. At the lowest level, the TensorFlow APIs are really, really flexible, and they let users build anything they want to. With eager execution, these same APIs are now easier to use. TensorFlow also contains a full implementation of Keras. TF Keras contains building blocks like layers to build models to make it easier to do that, and offers lots of utilities to train them as well. Keras works with both graph and eager execution as well. For distributed execution, we provide estimators. So you can take your models and combine them with estimators to distribute them across machines. You can also build estimators from the Keras layers or models. And finally, we provide pre-made estimators, a library of ready-to-go implementations of common machine learning algorithms. So let's take a look at how this works. So first, you would often define your model, and this is a nice and easy way to define your model. It shows a convolutional model here with just a few lines here. Now, once you've defined that, often you want to do some input processing. So in this case, you load your data set from files, and we have a great API, TF Data, that was introduced in 1.4 that makes it easy for you to process inputs while still allowing us to do lots of optimizations behind the scenes. And you'll see a lot more detail on this later today as well. Once you have those, the model and the input data, now you can put them together by iterating over the data set, computing gradients, and updating the parameters themselves. As you can see here, you really just need a few lines of Python to put these together. And in fact, it runs just as Python does, and you can use your Python debugger to debug that and solve problems as well. Of course, you can do it in even fewer lines by just using the predefined utilities that we have with Keras. In this case, it executes the model as a graph with all the additional optimizations that come with it. Now, this is great for a single machine or a single device. Now, often, given the heavy computation needs for deep learning or machine learning, we want to use more than one accelerator or GPU or machines themselves. So for that, we have estimators. Taking the same model that you defined, the same data sets that you had, you can build an estimator and really use that to train across this cluster or across the multiple devices on a single machine. That's great. Why not use a cluster? Why use just a single box if you can actually train faster with that? This picture shows a TPU pod used for training ML models at scale. And again, the focus is to really take everything you've been doing and just build a TPU estimator that allows you to scale that same model across this entire supercomputer. And then finally, once you've trained that model, you can use that one line at the bottom to export that for deployment itself. So deployment is important. You often do that in data centers. But more and more, we are seeing the need to deploy this on the phones, on other devices as well. And so for that, we have TensorFlow Lite. The model that we just exported, we have a script to really convert that to a custom format that's designed for devices, that's lightweight, and it's really fast to get started with. And then once you have that format, you can include that in your application, integrate TensorFlow Lite with a few lines here, and get going. You basically have an application that can do ML predictions and include ML in whatever tasks you want to perform. So TensorFlow runs not just on many platforms, but in many languages as well. Today, I'm excited to add Swift to the mix. And it brings with it a fresh approach to machine learning. Don't miss the talk by Chris Lattner this afternoon that covers the exciting details of how we are envisioning this platform. JavaScript is a language that's synonymous with the web development community. I'm excited to announce TensorFlow.js. It's bringing machine learning to this growing community of exciting web developers. So let's take a brief look at this. It brings the same TensorFlow operations that you're used to into JavaScript, where you can call them just as plain JavaScript code, along with a full-fledged Layers API on top. It also includes full support for TensorFlow and Keras models, so you can pick the most appropriate development and deployment environment that works for you. So you can start in one place, go to the other, whichever way you want. And under the covers, these APIs are accelerated in the browser via WebGL. And then the Node.js support is coming soon, which will give you the power of all of TensorFlow to accelerate on CPUs and GPUs as well. And with that, I would like to invite Megan Cacholia, Engineering Director at Google Brain, who leads our performance efforts, to talk a bit more about how TensorFlow does performance.
Thank you. All right. Thanks, Rajat. So performance across all platforms is critical to TensorFlow's success. First, I want to take a quick step back and just talk about some of the things that we think about when we're measuring and assessing TensorFlow's performance. One of the things we try to do is focus on real-world data and time to accuracy. It's really important to have reproducible benchmarks. We want to make sure those benchmarks are actually realistic of the workloads and types of things that users like you are actually doing on a day-to-day basis. Another thing, like Rajat talked about, is that we want to make sure we have clean APIs. And we don't want to have like a fast version and a pretty version of something. The fast version is the pretty version. And so all of these APIs that we're talking about, like Rajat has mentioned, that we're going to be talking about through various talks throughout the day today, these are the things you can use to get the best performance out of TensorFlow so that you don't have to worry about like which one is fast, which one is pretty. Use the pretty one, it is fast. You'll hear about TF data from Derek right after the keynote, as well as distribution strategy from Igor later today. And these are just some great examples of things we've been pushing on to ensure good performance and clean APIs. So in general, we want to ensure that you have great performance regardless of what type of platform you might be making use of. Whether it's a large data center, like what's shown here, or maybe you're using something like what's shown on the image here. You have a GPU or a CPU box under your desk. Maybe you're making use of a cloud platform, or mobile, or an embedded device. Regardless of the type of hardware you're making use of, we want to make sure that TensorFlow performs well across all of them. So now getting to some numbers, because what is a performance talk if I don't show you slides and numbers? So first, let's look at things on the mobile side. So this is highlighting TensorFlow Lite performance. So TensorFlow Lite we initially released last fall, and there's going to be a talk giving a lot more detail just about how it works and the things we were thinking of when making it later today by Sarah. But I wanted to call out just here the speedups that we see in inference. So a 3x inference speedup when using TensorFlow Lite quantized versus standard TensorFlow Lite for some of the models called out here. And again, it's critical to have strong performance regardless of what platform you're working on. And we're really excited to be able to see these gains in mobile. And looking past mobile, just beyond, there are a number of companies in the hardware space which continues to expand. And the contributions that come out of the collaborations that we have with these companies, the contributions they give back to TensorFlow and back to the community at large, are critical to making sure that TensorFlow performs well on these specific platforms for the users that each group really cares about. One of the first ones I want to highlight is Intel. So there's the Intel MKL DNN library, which is open sourced, and it's highly optimized for TensorFlow. So by making use of this open source library, we're able to achieve a 3x inference speedup on various Intel platforms. I've called out Broadwell and Skylake here, as well as see great scaling efficiency on training. And again, this is one of those things that really highlights how important it is to have strong collaborations with different folks in the community. And we're really excited to be able to see things like this that can go back to all the users. I wanted to call out a few of the collaborations we've had with NVIDIA as well. So one of the first things that we're excited about is TensorRT. TensorRT is an inference optimizer and a runtime for GPU platforms. We've been collaborating very closely with NVIDIA on TensorRT. TensorRT has been around for a little while, but with the TensorFlow 1.7 release, we now have native support for TensorRT built in, and that means you can get low latency, high throughput inference. So here you can see an 8x inference speedup when making use of TensorRT versus just using native FP32 with standard TensorFlow. So it's great, again, to see these types of collaborations that can be done and the contributions come back and the great numbers that can be delivered by it. Looking past inference and going on to some of the training things, so mixed precision training is really important. As faster and more powerful hardware comes out, some of it is optimized such that if you use mixed precision or FP16 support, that's how you'll get the best out of that hardware. One example of this is the Tesla V100 that NVIDIA has. So we've been working closely to make sure that we have this strong mixed precision training support so that way you can get the best performance out of that hardware. So here you can see a 3.5x training speedup. So this is on an 8x Tesla V100 box. And you can see just the performance improvements when you move to mixed precision training versus just using standard TensorFlow. Scaling efficiency is really important as well. Obviously, we want to make sure TensorFlow performs well. Maybe you have a single GPU, but it should keep going regardless of how many things that you throw at it. So we want to make sure that, again, looking at examples for real-world data as well as synthetic data, it's great to benchmark on synthetic data, but it's very important to make sure real-world use cases actually perform as we expect as well. So here we're showing 90% scaling efficiency with real data, 95% with synthetic data, and this is, again, on a DGX1, so an NVIDIA box that has a V100 box that has between 1 and 8 GPUs, and you can kind of see the scaling here. But this is something that we care a lot about, and you're actually going to hear more about how to get easier scaling efficiency by making use of some of our internal APIs later today as well. Moving on to cloud frameworks, I want to talk a little bit about cloud TPUs. So cloud TPUs was launched in beta in February, so just a month and a half ago. This is Google's V2 TPU, so it's designed from the ground up for machine learning workloads, and it's available via Google's cloud platform, like I mentioned. It's really exciting to look at some of the numbers here. So this picture is actually showing a device, and on a single device, you're able to get 180 teraflops of computation. But it's not just about the compute power. It's about what you can actually do on this, right? It doesn't really matter if you have amazing compute power, but you can't run the types of models that you want. So I want to highlight the types of models reference models that we've already open sourced that are available today, as well as a bunch more types of models that are coming soon. Again, just to highlight the breadth of things that you can run on this type of hardware and get great performance, as well as great accuracy. We actually have an internal team that is continually making sure that these models perform well, they perform fast, and that they also are training to accuracy in the expected amount of time. So it's not just about putting a model out there and open sourcing it and saying, here, go with it. It's about making sure it actually works as the community would expect it to work. Again, some numbers, because what good is it if I don't show any numbers in the performance talk? So one of the numbers here I want to call out on this slide is just that for cloud TPUs, the cost to train ImageNet to 76% accuracy is under $85. And we think it's really exciting to be able to just see what you can achieve by making use of this platform. I also want to call out, if you want more numbers than what's shown here, you can definitely take a look at the Dawnbench entry that cloud TPUs submitted for the ImageNet training. One final exciting thing I want to call out about cloud TPUs is the availability of pods, which will be coming later this year. So what's a pod? A pod is actually 64 of the devices, like I showed earlier, all wired up together, and you get about 11.5 petaflops of computation in a pod. So that's a lot of compute power that is going to be available in this. And what can you do with that compute power? One of the things that the team has been pushing on is training ResNet 50 on a cloud TPU pod to accuracy in less than 15 minutes. So we're very excited just to be able to see what can be done with this type of hardware and just the amazing speed that you can get that wasn't really possible before. So Rajat's talked about the APIs and just the ease of use and things we're focusing on. I've given you some fun numbers, but what happens when you put it together? What can TensorFlow actually do? So I want to invite Jeff Dean, who is the leader of the Brain team, to come up and talk a bit more about how TensorFlow addresses real problems. All you.
Thanks. Thanks, Megan. So I think one of the really remarkable things about machine learning is its capacity to solve real problems in the world. And We've seen tremendous progress in the last 2 years. In 2008, though, the US National Academy of Engineering put out this list of grand engineering challenges that they were hoping would be solved by the end of the 21st century. It's 14 different challenges, and I think it's a really nice list of things we should be aspiring to work on as a society. You know, if we solved all these problems, our planet would be healthier, people would live longer, they would be happier, and generally things would be better. I think machine learning actually is going to help us in all of these things, some in small ways where you see machine learning influencing our understanding of chemical molecules and so on, some in very major ways. So I'm going to talk about 2 of these today, but I think machine learning will actually be a key to helping us attack all of these different areas. The 2 I'm going to talk about are engineering the tools for scientific discovery and advancing health informatics. So first, engineering the tools for scientific discovery. You know, clearly machine learning is going to be a big component of what we do to solve some of these challenges, and TensorFlow itself you can think of as a tool for helping us engineer some of these discoveries. But one of the things that I think is really important is that there's a lot more opportunity for machine learning than there is machine learning expertise in the world. The way you solve a machine learning problem today is you have some data, you have some computation, maybe GPUs or TPUs or CPUs or whatever, and then you have a machine learning expert, someone who's taken maybe a graduate class in machine learning, someone who's downloaded TensorFlow and is familiar enough to play around with it. But that's a pretty small set of people in the world. And then you stir all this together, and you get a solution, hopefully. So that's the unfortunate thing about that is there's probably tens of thousands of organizations in the world today that are actually effectively using machine learning in production environments and really making use of it to solve problems. But there's probably tens of millions of organizations in the world that have data in electronic form that could be used for machine learning, but don't really have the internal expertise and skills. So one of the things we're excited about is how can we make machine learning much easier to use so that you don't need nearly as much expertise to apply it. So can we use computation to replace a lot of the need for that machine learning expertise? So we've been working on a technique, a suite of techniques that we call AutoML. And neural architecture search is one example of this. One of the things a machine learning expert does is they sit down and they decide for a particular problem what kind of model structure they're going to use for this problem. Is it going to be a ResNet 50 architecture? Is it going to be a 9-layer CNN with these kinds of filter sizes, and so on? It turns out that you can use machine learning to optimize a controller that proposes machine learning models. And so you can actually have the controller propose machine learning models, train those models on the problem you care about, see which ones work well and which ones don't, and then use that feedback signal as a reinforcement learning signal for the model generating model. It can sort of steer it towards models that are working well for particular kinds of problems and away from the part of the space where those models don't seem to really work very well. And if you repeat this a lot of times, you can actually get really, really powerful, high-quality models. And they look a little weird. So this is not something a human machine learning expert would sit down and sort of construct. But it has characteristics of things we know that human machine learning experts have discovered are helpful. So if you think of the ResNet architecture, it has these skip connections that allow you to skip every other layer. And so these sort of more organic-looking kinds of connections are the same fundamental idea, which is you want to allow input data to flow more directly to the output without necessarily going through as much computational layers. So the interesting thing is AutoML actually does quite well here. So every dot here, this is a graph showing computational cost versus accuracy for ImageNet. And every dot here shows you different kinds of trade-offs there. And generally, as you expend more computation, you get higher accuracy. But every dot here is sort of the work of years of effort, cumulative effort by top machine learning researchers and computer vision experts in the world. And if you look at AutoML, if you run AutoML, you actually get better accuracy and better computational trade-offs than all of those kinds of models. That's true both at the high end, where you care about utmost accuracy and don't care that much about computational budget. But it's also true at the low end, where you have very lightweight models where you care about very low computational cost and high accuracy. So that's pretty exciting. I think this is a real opportunity to use more computation to solve real machine learning problems in a much more automated way so that we can solve more problems more quickly. We've actually released this in collaboration with the Cloud group at Google as a product that customers can use for solving their own computer vision problems. And obviously, we want to broaden it out from beyond just computer vision to lots of other kinds of categories of problems. OK, advanced health informatics. So machine learning and healthcare is going to be a really impactful combination. One of the areas that we've been working on is a variety of different medical imaging problems, including one problem in ophthalmology, where you're trying to look at an image like this and diagnose whether that image shows signs of diabetic retinopathy. This is a serious degenerative eye disease. 400 million people are at risk of this around the world. And it's very treatable if it's caught in time. But if it's not caught in time, you can actually suffer vision loss. So, and there often in many parts of the world, there just aren't enough ophthalmologists to inspect these images. And so we've done work, and with work that we published in the very end of 2016, we showed that we had a model that was on par with board-certified ophthalmologists. And since then, we've been continuing to work on this, and we've changed how we sort of label our training data. We've gotten retinal specialists to label the training data rather than general ophthalmologists. And now we actually have a model that is on par with retinal specialists. This is a much higher standard of care. And we're pretty excited about this, because this means you can bring this and deliver this to lots and lots of places around the world. But more interestingly, I'm going to tell you a little tale of scientific discovery. So we had a new person join the retinopathy team. And as a warm-up exercise, Lily Peng, who leads some of this work, said to this new person, hey, why don't you go off and then see if you can predict age and gender from these images? And she thought, maybe you can predict age within a couple of decades, and you definitely shouldn't be able to predict gender, so your AUC should be 0.5. So the person went off and came back a little while later, and they said, I can predict gender with AUC of 0.7. And Lily was like, that's weird. That must be wrong. Why don't you go off and come back later and just double check everything? So they come back, and they said, my AUC is now 0.85. And so that got us thinking, and we investigated what other kinds of things we could predict from these retinal images. And it turns out that you can predict a variety of different things that are indicative of cardiovascular health. Your age and gender are symptoms or signs of cardiovascular health, as are things like your hemoglobin level, lots of things like this. We now actually have a new non-invasive test for cardiovascular health. Normally, you'd have to draw blood and do lab tests for this. But now we can actually do this just from an image, which is pretty cool. We're also doing a bunch of work on predictive tasks for healthcare. So given a patient's medical record, can we predict the future? This is something doctors want to do. You want to understand how your patient's going to progress. And you want to be able to answer lots of kinds of questions. Will the patient be readmitted if I release them from the hospital now? What are the most likely diagnoses I should be thinking about? What tests should be considered for this patient right now? Lots of questions like that. And we've been collaborating with several healthcare organizations to work on de-identified medical records to see if we can predict these kinds of things. And in January, we posted a many-author archive paper. And we looked at a lot of these different kinds of tasks. I'll highlight just one of them here, which is predicting which patients are most at risk for mortality. And using this, we're able to actually predict which patients are most seriously at risk 24 hours earlier than the clinical baselines that are currently in use. And so that really means that doctors get 24 hours of advance notice to really pay attention to those patients that are critically ill and really need their close attention and close watching. So this is indicative of what machine learning can do for this kind of field. In general, the Google Brain Team's mission is to make machines intelligent and then use that ability to improve people's lives. I think these are good examples of where there's real opportunity for this. I'm going to close with a bit of a story. So when I was 5 years old, I lived in northwestern Uganda for a year. And the local crop there is a root called cassava. And I was 5, so I like to go out and help people pick cassava. But it turns out that machine learning and cassava have a kind of cool twist together. So here, please roll the video.
Cassava is a really important crop. It provides for over 500 million Africans every day.
When all other crops fail, farmers know that they could rely on their cassava plants to provide them food.
There are several diseases that affect cassava, and these diseases make the roots unedible. It is very crucial to actually control and manage these diseases.
So we're trying to use machine learning to respond to those diseases.
And TensorFlow is the best foundation for our solutions. The app that we've designed can diagnose multiple diseases. It's called Nuru, Swahili for light, the light that farmers can use to see their problems and find solutions. You wave your phone over a specific leaf, look at it, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, we have an option for you to get advice and learn about the best management practices.
The object detection that we use through TensorFlow relies upon our team annotating images.
We've collected over 5,000 high-quality images of different cassava diseases for this project. We use a single-shot detector model on a mobile net architecture. It's able to make predictions in less than 1 second.
Instead of having to implement thousands of lines of code, TensorFlow provides a library of functions that allow us to build architectures in much less time.
We need something that can be deployed on a phone without any connection. TensorFlow is able to shrink these neural networks to be able to fit on your mobile device.
The human input is absolutely critical. We're really building something that augments your experience and makes you better at your job.
So with AI tools and machine learning, you can improve the yields, you can protect your crops, and you can have a much more reliable source of food.
AI offers the prospect to fundamentally transform the life of hundreds of millions of farms around the world.
You can see a product that can actually make someone's life better. This is kind of revolutionary.
Pretty cool. And I think we have some members of the Penn State and IITA teams from Tanzania here today. So if you could all stand up or wave, and I'm sure they'd be happy to chat with you. Fantastic. I'm sure they'd be happy to chat with you at the break about that work. So with that, I'd like to introduce Derek Murray, who's going to talk to you about TF Data, which is a really easy and flexible way to describe easy-to-use input pipelines from TensorFlow models. Derek?
Thank you.
Thanks.
OK, thank you, Jeff. And wow, it's really amazing to see how people are using TensorFlow to make the world a better place. So as Jeff said, my name's Derek Murray. I work on the core TensorFlow team. And I'm thrilled to be here at the second Dev Summit to tell you about TF Data, which is our new library that helps you get all of your data from cat pictures to cassava pictures into TensorFlow. So why are we here talking about input pipelines? I mean, after all, they're usually overshadowed by the more glamorous aspects of a machine learning job, the matrix multiplications and the convolutions. But I'd argue that they're actually extremely important, because input data is the lifeblood of machine learning, and our current algorithms and hardware are so thirsty for data that we need a powerful input pipeline to be able to keep up with them. That's the button. There we go. All right. So when I kicked off the TF Data project last year, TensorFlow had room to improve in this regard. You could either feed in data from Python at each step, which was kind of slow, or you could set up queue runners to feed your data. And these were a little, let's say, challenging to use. So I decided to focus on 3 themes, which are going to be the main topics of my talk today. First is performance, because when we're training models on state-of-the-art accelerator hardware like cloud TPU pods or NVIDIA DGX supercomputers, we have a moral imperative to keep those accelerators busy with new data at all times. The second is flexibility, because we want to be able to handle any kind of data in TensorFlow itself. We don't want to have to rely on external tools so that it's possible to experiment with different views of your data on an interactive timescale. And then third, we have ease of use. Because, as Jeff said, our overall mission with TensorFlow is to open up machine learning to users of all abilities. And I know from spending a lot of time on Stack Overflow that it can be a big leap from following along with your first MNIST tutorial to training your first model on your own data. And a good input pipeline story can help smooth this transition. So we aim to make TF Data the only library you need for all input processing in TensorFlow. How do we go about that? Well, we took inspiration from the worlds of databases and functional programming languages and designed TF Data as a library of simple, composable tools that we can divide up into 3 buckets. First, we have the tools to extract data from a wide range of sources. These can range from in-memory arrays to multi-terabyte files that are sharded across a distributed file system like GCS. Then we have the tools to transform your data. And these enable you to change the representation, extract features from your data, perform data augmentation, and ultimately convert your raw data into the tensors that you'll use to train your model. And finally, we have a set of tools for loading the transformed data into the memory of your GPUs and TPU accelerators. And this can be particularly important for end-to-end performance, as we'll talk about a bit later on. Well, that's the high-level pitch, but what does it look like in real code? Well, this is the standard TF data input pipeline for reading a set of example protos from a set of TF record files. And I bet that 90% of all TensorFlow input pipelines start off this way. In fact, it's so common we've wrapped this very pipeline up in a single utility function, but just for pedagogical reasons, it's useful to spell out the individual parts. So we start the extraction phase by getting a list of files, and these can be on your local disk or just as easily in GCS or S3. And we extract the TF records from those files. Then we use a sequence of functional transformations to pre-process the data. And here we took inspiration from languages like C#, Java, and Scala, which use method chaining to build up a pipeline of dataset objects, and a higher-order functional operators like map and filter to let you customize the behavior of that pipeline. And then finally, in the load phase, we tell TensorFlow how to get data out of the dataset. One of the easiest ways to do this is to create an iterator, and just like its namesake in Python, this gives you sequential access to the elements of the dataset. And sequential access is typically what you want when you're doing mini-batch training for a deep neural network, and we'll see some ways to soup up this part of the pipeline later on. So now that I've given you an overview, I want to come back to each of our key themes and tell you how we've been advancing each of them over the last few months. Let's start with performance. So you remember all those exciting performance results that Megan told you about in the keynote? Well, every one of them was measured using real input data and a TF data input pipeline that you can download and use in your own programs. And in our set of benchmarks, there's one experiment that I personally like, and it measures the performance of training an infinitely fast image model on real data in order to tease out any bottlenecks in the TF data pipeline. And when we ran this benchmark last week on an NVIDIA DGX-1V, it managed to process over 13,000 ImageNet images per second. Now, that is actually much faster than we can train a state-of-the-art model on current hardware, but it's still exciting for a couple of reasons. And first of all of them is that this throughput has more than doubled over the past 8 months, and it's really a testament to the great job that the whole team has done in optimizing TensorFlow performance. And the second reason is that accelerators and models are getting faster all the time. So we're in a good place to deal with future generations, and we've got this extremely useful benchmark that guides us as we continue to improve TF data performance. So these results are all very nice in theory, but how do you actually get that kind of performance? Well, one option is you can go on GitHub, fork the TensorFlow benchmarks project, and use that code in your own program. And if you're training a model on ImageNet, you should probably just do that. But maybe you have a different problem to solve. So we've recently launched a performance guide for TF data on tensorflow.org. And this guide is full of useful theoretical and practical information that gives you the ability to put our optimizations into practice on your own pipelines. And to support this on the technical side, we've been adding a raft of new features to TF data to help achieve this performance. One that I would particularly want to call out is this new GPU prefetching optimization that's going to be part of TensorFlow 1.8, although you can start playing with it in the nightly builds right away. And up to this point, TF data has been exclusively for code that runs on the CPU. And this marks our first foray into running pipelines on GPUs as well. There's a lot more I could say on this topic, and we're still developing these features, so watch this space. But let's go back to look again at our program from earlier on. I'll show you how to put some of these techniques into practice. So first off, when you're dealing with a large data set sharded across a cloud storage service like GCS or S3, you can speed things up by reading multiple files in parallel to increase the effective throughput into your model. And you can now turn this on with a single option to the TF record dataset called non-parallel reads. Then, in the transformation phase, you can often improve performance by switching to fused versions of various transformations. So here I've fused shuffle and repeat that avoids a stall between epochs as it buffers. And I've also fused together the map and batch transformations, which parallelizes both the execution of the function in the map and the data transfer of each element into the batch tensor. And together, these two optimizations give big speedups for models that consume a large volume of data per step. And last but not least, we have the GPU prefetching that I just mentioned. So this ensures that the next batch of input data is in memory on the GPU when the next step is ready to begin. And this optimization has been a crucial part of our CNN benchmarks for a while now, but achieving it involved manually staging buffers from the CPU memory to GPU memory and sort of changing up the structure of your program to do this. The new prefetch to device API gives you the same performance and only requires you to add one line of code to your input pipeline to get the benefit. So this is really just the Cliffs Notes version. I'd encourage you to watch my colleague Brennan Sata's talk later here at the summit, and he's going to show you a more scientific approach to pipeline performance optimization. And of course, you can check out the performance guide on TensorFlow.org. So now, let's switch gears and move on to our second theme, which is flexibility. And originally, the flexibility in TF data stemmed from the functional transformations. So they allow you to put any TensorFlow computation, any fragment of a TensorFlow graph, at any point in your pipeline. And so, for example, if you have some existing TensorFlow code for pre-processing images, you can stick it inside a dataset.map and start using it in your pipeline right away. And the initial version of TF data had sort of traded on this and let you pass a list of tensors in and get a list of tensors out from these transformations. But we heard back from our users that they had more sophisticated needs and complicated feature structure. So we added support for nested structure types like tuples and dictionaries. And in TensorFlow 1.5, we added native support for sparse tensors, which are particularly useful when you're dealing with complex categorical data and training embedding models. So at this point, if there are TensorFlow ops for everything that you want to do, then you're all set. But one thing that we've learned over the last few years is that not everything is most naturally expressed as a TensorFlow graph. So we've been working to give you alternative ways to build up your TF data pipelines. The first way is by adding dataset.fromGenerator. And what this allows you to do is build a pipeline from a Python function that generates NumPy arrays. And this gives you the flexibility to wrap existing Python code in a dataset and benefit from some of our performance optimizations, like prefetching to GPUs. The other way might be a little more appealing to power users. So we've opened up the backend API to TF data, and you can now build your own dataset kernel plugins in C++, loading them using TensorFlow's custom op mechanism. We've already heard from some of our partners that this ability is useful for integrating with custom file formats and in-house storage systems. And we're dogfooding this approach for some of the new dataset implementations in TF Contrib, like the recently added Kafka dataset. So I'm really looking forward to seeing what some of you will build with this new API. And of course, I'd encourage you to contribute things back via pull requests. We're really excited to get contributions from the community in this part of the project. OK, final theme I want to cover is ease of use. And when I speak to folks, maybe like some of you, who've used TensorFlow for a year or more, and they've struggled with the old ways of reading data into TensorFlow, I usually don't have to make much of a case here. But our users have really high expectations, and there are new people getting their first exposure to the library every day. So we've continued to push hard on usability. So I just want to share a few highlights from recent months. First off, as Rajat told you in the keynote, eager execution is here, and it makes using TF data a lot more pleasant. In the next talk, Alex is going to tell you a lot more about eager mode. But from my admittedly biased perspective, the best thing about it is that you can start treating data sets just like any other iterable object in Python. So you can simply loop over them with a regular for loop, and there's no more make one-shot iterators required. And what's really neat about this is that it works together with TF data optimizations like GPU prefetching. So you can combine the efficiency of asynchronous graph-based execution for your input pipeline and the flexibility of eager execution for your model code. Next, we've heard feedback that while power users like the composability and configurability of the data API, many users just want an easy way to follow best practices on standard data formats. So TensorFlow 1.8 will contain new standard recipes for TF example protocol buffers and for CSV data that make it a lot easier to handle these formats and apply all of the best practices from the performance guide. So let's go for one last time back to our standard program. And as I promised at the beginning, the whole thing can be replaced with a single call to make batch features dataset. And this performs all the parallel I/O, parallel parsing, shuffling, batching, and prefetching for you. And it gives you back a data set that you can continue to transform using map, filter, and other transformations. And if you have a performance-critical workload, we generally recommend using a binary format like TF example and TF records. But for many users who are just getting started and tend to have smaller data, they often prefer something simple, and comma-separated values or CSV format fits that bill nicely. And in particular, we've noticed how popular CSV data is on Kaggle, where there are thousands of different CSV datasets that you can available to download for free. And this snippet shows you how to use the new Kaggle API by pip installing Kaggle to download them with just a couple simple commands. And once you've done that, you can call the new make CSV dataset function in TensorFlow to get the data out of those downloaded files. In this case, it's a dataset of a million news headlines, and I think it's quite simple. It's only got 2 features. But what I particularly like about this new API is that it takes care of figuring out the types and the column names for you, and it dramatically cuts down the amount of boilerplate you have to write to work with this kind of data. Finally, we've been working to improve the integration between TF data and high-level TensorFlow APIs like estimators and Keras. Now, the Keras support is still in the pipeline, if you'll excuse the pun. But if we want to switch our CSV parsing code from eager mode to using estimators, it's a simple matter of returning the dataset from an estimator's input function, no more iterator required, and then you pass that input function to the estimator's train method, and we're good to go. And really, the approach we're taking on usability here is to make TF data objects, like the datasets and the iterators, as natural and Pythonic as possible. And features like eager execution and the high-level APIs are making this a lot easier to do. And our eventual goal is to make it so seamless that your input processing infrastructure becomes a natural extension of your TensorFlow program. Well, that is about all the time I have. So just to recap, I told you at the beginning that our mission for TF data was to make a library for input processing that is fast, flexible, and easy to use. I hope I've convinced you in the last 15 minutes that we've achieved all 3 of these goals. And so you'll understand why I'm going to say that TF data is the one library we recommend for all input processing in TensorFlow. If you want to find out more, there is a ton of documentation about TF data on tensorflow.org. We cover how-tos and the performance guidance that I mentioned earlier. And both the TensorFlow benchmarks and the official models repositories have examples of high performance and readable input pipelines written in TF data. And with all of this information and knowing the real creativity of this community, I'm really looking forward to seeing what all of you build with this library. Thanks a lot for listening. OK, and now it is my great pleasure to introduce Alex Passos, who is going to tell you all about TensorFlow eager execution. Okay.
Hello. My name is Alex, and I'm here to tell you about eager execution, which I think you've heard in the last 2 talks now, but I'm here to tell you what it's actually about. This new imperative, object-oriented, Pythonic way of using TensorFlow that we're introducing to you today as part of TensorFlow Core. So you know, because you're here or because you're watching the live stream, I hope, that TensorFlow has been this graph execution engine for machine learning that lets you run graphs at high scale and all sorts of other nice things. But has it? And why did we choose to go with graphs in the first place? Since now I'm going to tell you about eager execution, where we move beyond what we can achieve with graphs, I think it's a good idea to recap why we bothered. And a really good reason why you want to have your computation represented as a platform-independent graph is that once you have that, it's very easy to differentiate that graph. And I went to grad school before AltaDiff was standard in machine learning toolkits, and I do not wish that on anyone. Life is much better now, trust me. Also, if you have a platform-independent abstract representation of your computation, you can just go and deploy it to pretty much anything you want. You can run it on a TPU, you can run it on a GPU, you can put it on a phone, you can put it on a Raspberry Pi. There are all sorts of cool deployment scenarios you're going to hear about today. And it's really valuable to have this kind of platform-independent view. Also, compilers work with data flow graphs internally. And they know how to do all sorts of nice optimizations that rely on having a global view of your computation, like constant folding, common sub-expression elimination, data laying, and things like that. And a lot of these optimizations are really deep learning specific. We can choose how to properly lay out your channels and your height and width and stuff so your convolutions are faster. And finally, a key reason that's very important to us at Google, and I hope important to you as well, is that once you have a platform-independent representation of your computation, you can just deploy it and distribute it across hundreds of machines or a TPU pod like they showed earlier. And this is a very seamless process. So since graphs are so good, what made us think that now it's a good idea to move beyond them and let you do eager execution? A good place to start is that you don't actually have to give up automatic differentiation. I'm sure like you're familiar with like other frameworks like Python's Autograd that let you differentiate dynamic code. And you don't need to have an a priori view of your computation to differentiate it. You can just build up a trace as you go and then walk back the trace to compute gradients. Also, if you don't stop to build a platform in like this computational graph, you can iterate a lot more quickly. You can play with your model as you build it. You can inspect it. You can poke and prod at it. And this can let you just be more productive when you're like making all these changes. Also, you can run your model through debuggers and profilers and add all sorts of like analysis tools to them to just really understand how they're doing what they're doing. And finally, if we don't force you to represent your computation in a separate way than the host programming language you're using, you can just use all the machinery of your host programming language to do control flow and data flow and complicated data structures, which for some models is key to being able to make your model working at all. So I hope you're now wondering, how do I get to use this? And the way you use this is super easy. You import TensorFlow, and you call tf.enable eager execution. And once you do that, what happens is, anytime you run a TensorFlow operation, like in this case, a matmul, instead of TensorFlow building a graph that later, when executed, is going to run that matrix multiplication, we just immediately run that matrix multiplication for you and give you the result. And you can print it, you can slice it, you can dice it, you can do whatever you want with it. And because things are happening immediately, you can have highly dynamic control flow that depends on the actual values of the computation you're executing. And here is just a simple like Wolf conditions line search example that I wrote, and it doesn't matter. It just matters. It has like while loops that depend on like complicated values that are computed based on the computation, and this runs just fine on whatever device you have. And together with this enable eager execution thing, we're also bringing you a few symbols in TensorFlow that make it easier for you to write code that's going to work both when building graphs and when executing eagerly. And we're also bringing you a new way of doing gradients. Because I'm sure you're familiar now with how you do gradients in normal TensorFlow, where you just create your variable, you create your loss function, and I hope you can think of a better loss function than this one. And then you call tf.gradients to like differentiate it. But when you have eager execution, we try to be as efficient as we possibly can. And if you're going to, one thing to think about is that if you're going to differentiate a computation, you need to keep track in memory of information about what happened so far, like your activations and things like that. But I don't want you to pay for the cost of this tracking when you're not computing gradients, because performance is really, like, the whole reason why we're doing this is because we want to use these big, nice pieces of hardware that train models super fast. So when eager execution is enabled, when you want to compute gradients, you use this little context manager to keep a tape active. And the tape just records all the operations you execute, so we can play it back when you're computing the gradients. Otherwise, the API is the same. Also, writing training loops in eager, as Derek pointed out, it's very easy and straightforward. You can just use a Python for loop to iterate over your datasets, and datasets work in eager just fine, and they work with the same high performance you get in the graph execution engine. Then you can just do your predictions, compute your gradients, apply your gradients, and do all the things you're used to doing. But really, the interesting thing about eager execution is not when you're just writing this code that's finished, that is done, that we already know works, but when you're still developing, when you want to do things like debug. So when eager execution is enabled, you can just take any model code, and I use my simple silly gradient example here, add nodes to like drop into the Python debugger anywhere you want. And once you're in the Python debugger, you have the full power of debugging available. You can print the value of any tensor. You can change the value of any tensor. You can run any operation you want on any tensor. And this will hopefully empower you to really understand what's going on in your models and really be able to fix any problems you have. You can also take eager execution code and profile it using whatever profiling tool you are most familiar and comfortable with. So here I have a little dumb model that just does a matmul and a bias-add. And let's pretend I don't know which of these operations is going to be the bottleneck, which one is lower. And I'm sure you all know the answer, that the matmul is a lot more expensive. But here you can just run your code through your Python profiler like you would do with any other programming job and find out that the matmul is like 15 times more expensive for my batch size here than my bias addition. And Also, by the way, those examples were run on the Google Colaboratory thing, which is this completely public shared GPU-capable interface for Jupyter notebooks that are like hosted on Google Cloud. It's pretty cool, and I think we have a demo on Eager that's hosted on that you can play out with later, or if you're on live stream, you can play out with it now if you can find the link. But together with Eager, we're bringing you a lot of new APIs that make it easier for you to build TensorFlow graphs and to execute models, and these APIs are compatible with both Eager execution and graph building. So one that's been like a recurring low-priority feature request is how to customize gradients in TensorFlow. And I'm sure you're familiar with like a few of the tricks that people have, like stop gradients and functions and things like that. But we're introducing a new API that works in both Eager and graph execution. And what I like about this example is that it's a thing that's being asked by many, many people how to do if I want to run my forward pass, and then in the backward pass, take the gradient of a particular tensor and clip its norm to keep it small to prevent it from exploding. And it just takes 6 lines of code to make a version of tf.identity that in the backward pass clips its gradient. And I think this is really cool. And I look forward to seeing what you guys can do with this when you're doing more than 6 lines of code and solving like all sorts of new interesting research problems. A big, big change when programming with Eager from Graph that I really want you to stop and think about is that we're trying to make everything as Pythonic and object-oriented as possible. So variables in TensorFlow are usually a complicated thing to think about, but when Eager execution is enabled, it's much simpler. A TensorFlow variable is just a Python object. You create one, you have it. You can change its value, you can read its value. When the last reference to it goes away, you get your memory back, even if it's your GPU memory. So if you want to share variables, you just reuse those objects. You don't worry about variable scopes or any other complicated structure. And because we have this like object-oriented approach to variables, we can look at some of the APIs in TensorFlow and like rethink them in a way that's a little more object-oriented and easier to use. And one that like really stood out to us as needing like an overhaul was the metrics API. So we're introducing this new tfe.metrics package, where each metric has 2 methods, one that updates the value and one that gives you the result. And hopefully this is an API that everyone is going to find familiar to use, and please don't try to compare this to the other metrics API. We're also giving you a way to do object-oriented saving of TensorFlow models. If you've tried looking at TensorFlow checkpoints now, you know that they depend on variable names. And variable names depend not just on the name you gave to a variable, but on all other variables which are present in your graph. This can make it a little hard for you to save and load subsets of your model and really control what's in your checkpoint. So we're introducing a completely object-oriented, Python object-based saving API where it's like Python Pickle. Like any variable that's reachable from your model gets saved, and your model gets saved. You can save any subset of your model. You can load any subset of your model. You can even use this tfe.checkpoint object to build things you want to save that have more than a model. And here we have an optimizer and a global step, but really, you can put whatever you want in there. And the idea is that this object graph that eventually goes down to variables is something you can save and load. So you can have your GAN and save and load your discriminators and your generators separate from each other. Then you can take your discriminator and load it back up as like another neural network that you can use in another part of a model. And this should give you a lot more control to get a lot more out of like TensorFlow checkpointing. But a real question that everybody asks me when I tell them to work on Eager execution is it fast? Because graphs have this high performance promise. So how fast can we make this thing that runs Python code all the time? And the answer is that we can make it fast enough. For models that are highly computationally intensive, you pretty much don't see any Python overhead, and we're as fast as Graph TensorFlow. For sometimes slightly faster, in reasons that I don't fully understand, even for highly dynamic models, you have competitive performance of anything else you can find. And please don't get attached to these numbers. We have many more benchmarks in our code base, and we're optimizing Eager performance very aggressively. But I hope that the message you get out of this is that if your model can keep a GPU busy, if you're doing large convolutions, large matrix multiplications, there is almost no cost in experimenting and doing your research in model building with Eager execution turned on. But when you are doing smaller things, there are some overheads, and I want to go over them. But again, don't get attached to them, because we're being very aggressive about optimizing this. if you just run a no-op in TensorFlow, like an identity, it takes almost a microsecond to execute it. If you run that with eager execution turned on, there's an extra microsecond of overhead. If you're tracing gradients, there are another 3 microseconds of overhead that you get. But if you're just enqueuing something on the GPU stream, that alone takes like single-digit microseconds. So if you can execute enough computation to keep a GPU busy, you're unlikely to see anything bad from using eager execution. And again, these numbers are improving very quickly. Please don't get too attached to them. But there is this large ecosystem of TensorFlow code, libraries, models, frameworks, checkpoints that I don't think anyone wants to give up. And I don't want you to give up if you want to use eager execution. So we're also thinking really hard about how we can interoperate between eager and graph. One way is to call into graphs from eager code. And you can do that with tfe.make template, which has this create graph function argument. When you pass through to it, we build a graph for that little Python function that you wrote. And then you can use it and manipulate and call the graph from eager execution. We also have the reverse, which is how to call into eager from a graph. Let's say you have a big graph that you understand everything in it, but there's a little chunk of your computation that you really don't know how to express in. Either you don't know or you don't want to bother expressing it in using TensorFlow graphs. So you can wrap it in a TFE PyFunc. And what you get in there when that Python function is executing are eager tensors that you can run any TensorFlow op in, including convolutions and other things that are not available in NumPy. But you can also look at the values and inspect and use dynamic control flow in there. So I hope with these two things together, you can really reuse eager and graph code across. But really, the easiest way to get eager and graph compatibility is to just write model code that's going to work in both ways. And if you think about it, once your model is fully written, debugged, and tested, there's not much there that tells you whether you need to build a graph or to execute eagerly. So write, iterate, debug in eager, and then import that same code into a graph, put it in an estimator, deploy it on a TPU pod, deploy it on the GPU, distribute it, and do whatever you want. And this is what we've done in our example models, and there's going to be a link in the end of the presentation, so you don't need to worry about writing this down. So here's some practical advice for you. Write code that's going to work well when executing eagerly and when building graphs. And to do that, use the Keras layers. They're great. They're object-oriented. They're Pythonic. They're easy to understand, manipulate, and play around with. Use the Keras model to stitch those layers together. That will get you saving and loading and training and all sorts of things automatically if you want, but you're not forced to use those. Use TF contrib summary instead of TF summary. They will move to the TensorBoard open source package very soon. So if you're watching this on video, it probably already happened. Use the TFE matrix instead of the TF metrics, because these are object-oriented, friendlier to use, and friendlier and eager. And use the object-based saving, which is a much nicer user experience anyway, so I hope you're going to want to do this all the time. If you do all of this, it's highly likely your code is going to work super well in both eager execution and graph building. So now, I'd like to take some time to tell you why you should enable eager execution. And a real good important reason for us that led us to build this in the first place is that if you're new to machine learning or you're new to TensorFlow and you want to learn, being able to play with these objects and manipulate them directly is just a much nicer experience than having to build a graph and interact with later in a session. It's a lot more intuitive, lets you understand what's going on much better. So if you're new, just by all means, go straight into eager execution, play around with it, and figure out how to get graphs later. Also, if you're a researcher and you're quickly iterating over models, you're changing their internal properties, and you're comparing them, and you try to do models that are non-trivial that we in the TensorFlow team were not thinking about when we designed TensorFlow, eager execution will make it much easier for you to understand what's going on, to debug what's going on, to be productive and advanced. So if you're a researcher, this is for you. Also, if your model's not working and you want to understand why, being able to enable eager execution and then step through it in a debugger, change some values, play around with it, understand, that is priceless, and that has saved me a lot of time. Similarly, if you want to profile your model using the full power of whatever tool you like to use to profile Python, eager execution is your friend. Also, there are some models, like recursive RNNs, that are just much easier to express if you don't need to put your entire computation in a static data flow graph. If you're working on one of those models, eager execution is also a choice for you. But really, the reason I think you should enable this is that it's fun. It's a very nice and intuitive way of interacting with TensorFlow, and I hope you're going to have a lot of fun experimenting with it. So now, I would like to point to a few things. Some of my colleagues, they're sitting over there now, they're going to be in the demo room during the break with laptops, with Colabs, that let you, like Jupyter Notebooks, that let you type and try eager mode there. Please go give it a try. Or if you're watching this on the live stream, type that short link. Hopefully it will stay in the screen long enough for you to type it. And play with it right now. It's really nice. We have a getting started guide on TensorFlow that should be live now, Programmer's Guide/eager, that tells you what you need to know about eager execution and what you need to know about starting to use TensorFlow using eager execution. We also have a ton of example models, like from RNNs to ConvNets to all sorts of things that are available behind that link. And I encourage you to look at them and see how easy it is to write the model and how easy it is to also reuse the same code from graphs for deployment. We have deployment for graphs for all models except for the highly dynamic ones that are just really hard to write in a graph form. And give it a try. If you give it a try, let us know how it went. We're super excited to share this with you. I hope you're going to have a great time playing with this. And yes, thank you. And now you're about to have a treat. It's my pleasure to introduce Nikhil and Daniel, who are going to tell you about TensorFlow.js. They have a really cool demo set up, but I don't want to spoil it. Where are they?
Yep.
All right. Hi, everyone. Thanks for coming today. My name is Daniel.
My name is Nikhil.
We're from the Google Brain team. And today, we're delighted to talk about JavaScript. So Python has been one of the mainstream languages for scientific computing. And it's been like that for a while. And there's a lot of tools and libraries around Python. But it's that where it ends. We're here today to convince you that JavaScript and the browser have a lot to offer. And TensorFlow Playground is a great example of that. I'm curious, how many people have seen TensorFlow Playground before? Oh, wow, quite a few. I'm very glad. So for those of you that haven't seen it, you can check it out after our talk at playground.tensorflow.org. It is an in-browser visualization of a small neural network, and it shows in real time all the internals of the network as it's training. And this was a lot of fun to make and had a huge educational success. We've been getting emails from high schools and universities that have been using this to teach students about machine learning. After we launched Playground, we were wondering, why was it so successful? And we think one big reason was because it was in the browser. And the browser is this unique platform where the things you build, you can share with anyone with just a link. And those people that open your app don't have to install any drivers or any software. It just works. Another thing is the browser is highly interactive. And so the user is going to be engaged with whatever you're building. Another big thing is that browsers, we didn't take advantage of this in the Playground, but browsers have access to sensors, like the microphone and the camera and the accelerometer. And all of these sensors are behind standardized APIs that work on all browsers. And the last thing, the most important thing, is the data that comes from these sensors doesn't ever have to leave the client. You don't have to upload anything to the server, which preserves privacy. Now, the Playground that we built is powered by a small neural network, 300 lines of vanilla JavaScript, that we wrote as a one-off library. It doesn't scale. It's just simple for loops. And it wasn't engineered to be reusable. But it was clear to us that if we were to open the door for people to merge machine learning and the browser, we had to build a library. And we did it. We released DeepLearn.js, a JavaScript library that is GPU accelerated, and it does that via WebGL, which is a standard in the browser. that allows you to render 3D graphics, we utilize it to do linear algebra for us. And DeepLearn.js allows you to both run inference in the browser and training entirely in the browser. When we released it, we had an incredible momentum. The community took DeepLearn.js and took existing models in Python and ported it into the browser and built interactive, fun things with it. So one example is the style transfer. Another person ported a character RNN and then built a novel interface that allows you to explore all the different possible endings of a sentence, all generated by the model in real time. Another example is a font generative model. There was a post about this, that the person that built it allowed users to explore the hidden dimensions, the interesting dimensions in the embedding space. And you can see how they relate to boldness and slantedness of the font. And there was even educational examples like Teachable Machine that built this fun little game that taught people how computer vision models work so people could interact directly with the webcam. Now, all the examples I showed you point to the incredible momentum we have with DeepLearn.js. And building on that momentum, we're very excited today to announce that DeepLearn.js is joining the TensorFlow family. And with that, we are releasing a new ecosystem of libraries and tools for machine learning with JavaScript called TensorFlow.js. Now, before we get into the details, I want to go over 3 main use cases of how you can use TensorFlow.js today with the tools and libraries that we're releasing. So one use case is you can write models directly in the browser, and this has huge educational implications. Think of the playground that I just showed. A second use case is, a major use case, is you can take a pre-existing model, pre-trained model in Python, use a script, and you can import it into the browser to do inference. And a related use case is the same model that you take to do inference, you can retrain it, potentially with private data that comes from those sensors of the browser, in the browser itself. Now, to give you more of a schematic view, we have the browser that utilizes WebGL to do fast linear algebra. On top of it, TensorFlow.js has 2 sets of APIs, the Ops API, which used to be DeepLearn.js, and we worked hard to align the API with TensorFlow Python. It is powered by an automatic differentiation library that is built analogous to eager mode. And on top of that, we have a high-level API, Layers API, that allow you to use best practices and high-level building blocks to write models. What I'm also very excited today to announce is that we're releasing tools that can take an existing Keras model or TensorFlow safe model and port it automatically for execution in the browser. Now, to show you an example of our API, we're going to go over a small program that tries to learn the coefficients of a quadratic function. So the coefficients we're trying to learn are A, B, and C from data. So we have our import TF from TensorFlow.js. For those of you that don't know, this is a standard ES6 import in JavaScript, very common. We have our 3 tensors, A, B, and C. We mark them as variables, which means that they're mutable, and the optimizer can change them. We have our f of x function that does the polynomial computation. You can see here familiar API like tf_at and tf_square, like TensorFlow. In addition to that API, we also have a chaining API, which allows you to call these math operations on tensors itself. And this leads to better readable code that is closer to how we write math. Chaining is very popular in JavaScript world. So that's the feed-forward part of the model. Now, for the training part, we need a loss function. So here is a loss function that is just a mean-squared error between the prediction and the label. We have our optimizer, an SGD optimizer. And we train the model. We call optimizer.minimize for some number of epochs. And here I want to emphasize, for those of you that have used tfigure before, or the talk before us, Alex's talk, the API in TensorFlow.js is aligned with the eager API in Python. All right, so clearly, that's not how most people write machine learning, because because those low-level linear algebra ops can be quite verbose. And for that, we have our layers API. And to show you an example of that, we're going to build a recurrent neural network that learns to sum two numbers. But the complicated part is that those numbers, like the number 90 plus 10, are being fed character by character, and then the neural network has to maintain an internal state with an LSTM cell. That state then gets passed into a decoder, and then the decoder has to output 100 character by character. So it's a sequence-to-sequence model. Now, this may sound a little complicated, but with the layers API, is not that much lines of code. We have our import TF from TensorFlow.js. We have our sequential model, which just means it's a stack of layers. For those of you that are familiar with TF layers in Python or Keras, this API looks very familiar. We have the first two layers are the encoder. The last three layers are the decoder. And that's our model. We then compile it with a loss, an optimizer, and a metric we want to monitor, like accuracy. And we call model.fit with our data. Now, what I want to point out here is the await keyword. So model.fit is an asynchronous call, which means, because in practice, that can take about 30 or 40 seconds in a browser. And in those 30 or 40 seconds, you don't want the main UI thread of the browser to be locked. And this is why you get a callback with a history object after that's done. And in between, the GPU is going to do the work. Now, the code I showed you is when you are trying to write models directly, when you want to write models directly in the browser. But as I said before, a major use case, even with DeepLearn.js, was people importing models that were pre-trained, and they just want to do inference in the browser. And before we jump into the details of that, I want to show you a fun little game that our friends at Google Brand Studio built that takes advantage of an automatically pre-trained model ported into the browser. And the game is called Emoji Scavenger Hunt. And the way it works, I'm going to show you here a real demo with the phone. It's in the browser. Let me see. You guys see here? So you can see I have a Chrome browser opened up on a Pixel phone. You can see the URL on the top. And the game uses the webcam and shows me an emoji. And then I have some time, some number of seconds, to find the real version item of that emoji before the time runs out. So before we play, Nikhil here is going to help me identify the objects that this game asks. You ready?
I'm ready.
All right, let's go.
All right.
All right, watch.
Watch.
You have
Did
a watch?
I just see a velvet?
I have a watch.
Did I spot a velvet?
Come on.
Hey, you found
Yay,
watch.
we got that.
Awesome.
Let's see what our next item is. Shoe.
Shoe.
I
You
think
gotta
I
help
saw
me
a
out here,
wolf.
buddy.
Did I spot a
Oh,
spindle?
yeah.
Hey, you found
Woo, we
shoe.
got the shoe.
All right, what's next?
Right.
Do
Wants
I
a
spy
banana.
A banana?
Yeah, do you
Does
have
anyone have a
Do I
banana?
see
This
a
guy's got a
velvet?
banana.
Oh,
What?
that
Come over
This
like
here,
guy's got a
man.
banana.
Come over here.
Am I seeing a wolf?
Yay!
All right.
All right. Look at us.
I'm ready.
We're gonna have a high score here. Beer.
Could that be a
Beer.
hat?
It's 10:30 in the morning, Daniel.
Did I spot a velvet?
Let's get back to the talk.
All right.
I think I saw a milk can.
All right, so I'm going to jump into some of the technical details of how we actually built that game. Come with the clicker.
Yeah.
Let's get the slide off. So what we did was we trained a model in TensorFlow to be an object recognizer for the scavenger hunt game. We chose about 400 different classes that would be reasonable for a game like this, you know, watches and bananas and beer. So what we did was we used the TensorFlow for Poets code lab. And in that code lab, what you essentially do is you take a pre-trained MobileNet model. And if you don't know what MobileNet is, it's a state-of-the-art computer vision model for edge devices. So what we effectively did was we took that model and we retrained it for these classes. Now we have an object detector in the Python world. How do we actually now get this into the browser? Well, we provide a set of tools today that help you actually do that. Once it's in, you skin the game and you make the computer talk and all that kind of fun stuff. Let's jump into how we actually convert that model. So as Daniel mentioned earlier today, we actually support two types of models. So we support TensorFlow saved models. We have a converter for that. And we also have a converter for Keras saved models. So you define your model and you save it with a saved model. This is a standard way to do that. Similarly, this is code that you would do that for Keras. This is unimportant. The next piece is that we actually convert it to the web. Today, we're releasing a pip package. It's TensorFlow.js. You can install that there. There's a script in there that lets you point to your TensorFlow saved model and point to an output directory. And that output directory will be where those static build artifacts will go for the web. Keras is the same exact flow. Point to your HDF5 input, and you have an output directory where those build artifacts will go. Now you statically host those on your website somewhere, just simple static hosting. And on the JavaScript side, we provide an API that lets you load that model. So this is what it looks like for TensorFlow. In the TensorFlow save model, you'll notice that it's a frozen model. We don't right now support continuing training of this model. Well, in the Keras case, we actually let you continue training. And we're working hard to keep these APIs aligned in the future. OK, so under the cover, what are we actually doing? So we're doing some graph optimization, which essentially means that we prune out nodes that you don't need to make the prediction. You don't need that in the web. We optimize weights for browser auto-caching. So we pack and shard in chunks of 4 megabytes, which helps your browser be quick the next time your page loads. Today, we support about 90 of the most commonly used TensorFlow ops. And we're working very hard to support more like control flow ops. And we support 32 of the most commonly used Keras layers today. And as I mentioned, we let you continue training for Keras models. And we let you do evaluation, as well as make predictions from that model. OK, so obviously, there's a lot you can do with just porting your models to the web for inference. But since the beginning of DeepLearn.js, we've made it a high priority to make sure that you can train directly in the browser. This opens up the door for education and interactive tools like we saw with the playground, as well as let you train with data that never leaves your client. So this is huge for privacy. So to show off what you can do with something like this, we built another little game. So the goal of the game is to play Pac-Man with your webcam. Now, Daniel's going to be my helper here. He's much, much better at this game than I am for some reason. So say hi. So there are 3 phases of the game. Phase 1, we're going to collect frames from the webcam, and we're going to associate those with up, down, left, and right, these classes. Now, Daniel is going to move his head up, down, left, and right, and he's just simply going to play the game like that. And you'll notice as he's collecting frames, he's kind of moving around a little bit. This kind of helps the model see different angles for that class and generalize a little bit better. So after he's done collecting these frames, we're going to go and train our model. So we're not actually training from scratch here when we hit that train button. We're taking a pre-trained MobileNet again, porting that to the web, and doing a retraining phase with that data that's local. And we're using the Layers API to do that in the browser here. Do you want to press that train button? All right, our loss is going down. It looks like we're learning something. That's great. So as soon as we press that play button, what's going to happen is we're going to make predictions from the webcam. Those are going to get plugged into those controls, and it's going to control the Pac-Man game. Ready? All right, so you can see in the bottom right, it's highlighting the class that it thinks it is. And Daniel, if he moves his head around, you'll see it change that class. And he's off. So all of this code is online, and you can go fork it. We invite you to do so. And obviously, this is just a game. But you can imagine other types of applications of this, like make a browser extension that lets you control the page for accessibility purposes. So again, all this code is online. Please go fork it and play and make something else with it. OK, Daniel. I know this is fun. I know this is fun.
I got it. All right.
You got to get back to the talk. OK, so let's talk a little bit about performance. So what we're looking at here is a benchmark of MobileNet 1.0 running with TensorFlow. This is TensorFlow Classic, not with TensorFlow.js. And I want to point out here we're using a batch size of 1. This is important because we're thinking about this in the context of an interactive application. So maybe this Pac-Man game where you feed in webcam data, you want to know what the prediction time is for 1. You can't really batch things. On the top row, we're looking at TensorFlow CUDA running on a 1080 GTX is a beefy machine. It's about 3 milliseconds. And I want to point out, the shorter the bar, the faster it is, clearly. In the second row, we have TensorFlow CPU, and this is running with AVX 512. And this is on actually one of these MacBook Pros here. It's about 60 milliseconds for that frame. Where does TensorFlow JS fit into this picture? Well, it depends. If you're running on a beefy 1080 GTX, we're actually getting about 11 milliseconds for one pass through this MobileNet model, which is pretty good if you think about this in the context of an interactive game. So on the laptop that we just showed the game with, we're getting about 100 milliseconds for that inference pass through MobileNet. And that's still pretty good. Like, you can build a whole interactive game with something that's running at 100 milliseconds. So the web is only going to get faster and faster. There's a whole new set of standards coming, like WebGPU, that will really push the boundary for these kind of things. But the browser still has its limitations. You can only really get access to the GPU through WebGL and these APIs. So how do we scale beyond that? How do we scale beyond the limitations that we have in the browser? There's a whole ecosystem of server-side JavaScript tools using Node.js that we would love to take advantage of. So today, I'm really happy to tell you that we're working on Node.js bindings to the TensorFlow C API. What that means is you'll be able to write that same low-level ops API with the eager mode we saw with the polynomial example, or the high-level layers API, which we saw for the Pac-Man example, and bind to TensorFlow C and run headless on your TensorFlow running with CUDA installed. Eventually, that also means we can run with a TPU on a backend, that same JS code. So these bindings are under active development, so stay tuned for more. All right, so let's recap some of the things that we launched today and that we talked about. So we talked about this low-level ops API, which does hardware-accelerated linear algebra, as well as the eager mode differentiation for AutoGrad. This is previously known as DeepLearn.js. We're rebranding that today. We released the high-level layers API. This is the Keras-inspired API that mirrors TensorFlow layers, and we saw an example of that with the addition RNN, and we saw an example of that with the Pac-Man demo. We also showed you how you can import TensorFlow saved models and Keras models for prediction and retraining in the browser. We also have released a bunch of demos and examples on GitHub. These are not the only two. There's a whole repository of different examples that can get you started. And they all have live links, so you can go and poke around and play. So I invite you to go do that. So we really want to see you get involved in this project. We have a bunch of links here. So js.tensorflow.org is our official website. All of these links, everything we talked about is there. There are tutorials, there's documentation, et cetera. Our code is obviously open sourced under TensorFlow/TFJS, so I invite you to go play there too. And we also started a community mailing list today. That's the short link here. And the community mailing list is for people to post demos and ask questions and that kind of thing. So this project was not just Daniel and myself. This was a larger team effort between many of our amazing colleagues at Google, so we want to thank them. And we also want to thank all of the amazing open source contributors for DeepLearn.js. And we're really excited to build the next chapter of machine learning and JavaScript with you. Thank you.
Thank you.
Hi. Like to get started again? So hi, my name is Brennan, and I'm going to be talking to you today about training performance. Now, this talk is centered around a user's guide to how to improve performance. So performance is very complicated. There's a lot of internals to TensorFlow as to things we're doing to optimize your training time. But what I'm going to talk to you today is about how you can make the most of the TensorFlow you know and love to converge faster. Now, before I go any further, I do want to take a moment to acknowledge the great work that is done not just by other engineers on the TensorFlow team, and not just by other teams at Google, but actually also by our partner teams, for example, the performance team at NVIDIA. They've done a lot of work to help make TensorFlow work fast, and I want to make sure we acknowledge that. With that, let's dig into a little bit of motivation. Why do we need performance? Why do we need to improve performance? Isn't it just fine today? Some folks at Baidu put together some research, and they showed that if you want to improve the quality of your models, just train on larger data sets. These beautiful straight lines are showing that for multiple different models, as you just give more and more training data, you just get linearly more accurate. Now, I'm actually being slightly facetious here. If you look closely, the axes on this graph are actually logarithmic. They are not linear. And so really, we don't need linearly increasing the amounts of data. We need exponentially more data to keep improving our models. And they found that this trend holds not just for different model classes on, in this case, it was sequence-to-sequence type work, but they found this applied to images. They found this applied to translation to multiple different areas across multiple different model types. So we're going to need to train on exponentially more data to improve our model quality. Unfortunately, we're running into quite the obstinate adversary, physics. Here's a graph of microprocessor trend data over 40 years, and we can see that clock frequency has entirely hit a wall. Single-threaded performance is not getting that much faster compared to how it used to. We're going to have to work a lot harder to meet the challenges of today and tomorrow with performance. Silicon itself is not going to get us there without a little bit of cleverness. The result of these two forces coming together has resulted in a Cambrian explosion of accelerator hardware. Not just CPUs, but we have GPUs today, and TPUs, and there's other more exciting things coming. There's startups like Nirvana that is now part of Intel, and there's the IPU from Graphcore that are taking a bunch of different points in the design space and are trying different hardware methodologies and layouts to try and get the best machine learning performance. So this is going to be a very exciting area coming forward as we think about performance in the future. Now, before I dig into the meat of my talk, I do want to acknowledge this is actually the Jurassic period and not of the pre-Cambrian era. So if you have a good picture of trilobites that is Creative Commonsly licensed, please do send it my way. In a nutshell, the machine learning training loop across a wide variety of different models and paradigms looks roughly as follows. You have your training data, and you need to load that in. This is sort of phase one. You read it from either disk or generate it from a reinforcement learning environment. You decompress it, you parse it. If you're doing, for example, an image model, you perform image augmentations, random flips, color distortions, and whatnot. And you batch it up to feed it into your model. And phase two, you compute the forward pass of your model, you compute the loss, the backwards pass, your gradients, and finally, after you have the gradients, you update the weights, the things you're trying to learn, and you repeat the cycle all over again. Now, again, there's a wide variety of accelerators, but to a first approximation, we see the following patterns emerge. Your training data and your pre-processing, your phase one, happens mostly on CPUs. The accelerator then takes over phase two and phase three. And with that, let's dig in. In my experience, as people migrate to modern accelerators, new TPUs, new generation of GPUs, et cetera, phase one is actually where the most performance problems are. Things everyone hits. There's always a problem with phase one. So we're going to spend a bit of time digging into input pipelines. Now, you heard earlier from Derek about tf.data. And this is definitely the far and away recommended API and way to load data into TensorFlow. And here's, if you're doing a simple image model, for example, ResNet 50, your input pipeline will probably start off looking like this. You have your data, your images batched together into TF record files, and you load them in with the TF record data set. You can shuffle and repeat your parser function that you map across every input image. That will do things like parse TF examples, JPEG decode, your color transformations, augmentations. You batch it up, and you return your data set. Now, if you run this on a fancy pants cloud TPU, a modern accelerator, you're actually only going to get about 150 images a second. This is nowhere near what you should expect. Now, before you think, wow, cloud TPUs must be total garbage, I'm going to go back to what I was doing before, it behooves you to try and optimize performance. Now, when you're optimizing performance, it's incredibly important to follow a methodology. You have to measure your performance, find your bottleneck, optimize your bottleneck, and repeat. So what does that look like with a cloud TPU? Again, there's tools in TensorFlow for GPUs and TPUs. But for cloud TPUs, we have this tool called Capture TPU Profile. And you can run this to, you can run this pointing it to your TPU. In this case, the TPU name is SATA. And you will also have it capture the profile into a log directory. This is the same log directory you use with TensorBoard, and so you can load it up into TensorBoard. And with that, I'd like to switch to my laptop, where we can actually see what the profiling tools look like. So here is a trace from actually the very same input pipeline, or very similar to the input pipeline I just showed. And you can see here that your step time graph, you have this tiny bit of orange at the bottom. And this is the compute time on the cloud TPU. And everything up here, this blue, that's actually waiting for data. That's input pipeline processing. So our TPU is actually sitting idle, and this is telling you 92% of the time. Totally not what we want to be doing. So let's dig in. Now, what I recommend using, we have a bunch of tools, and they're constantly improving and getting better. But for now, to really understand what's going on underneath the hood, we're going to use the trace viewer. So here I've loaded it up. One thing I should note is that the trace viewer, it's very much designed for power users, so it may be a little unapproachable. Let me walk you through a little bit about where to look in the trace viewer. So in the top, you actually have your TPU. Now, one cloud TPU has 8 compute cores, and these operate independently, although typically they're operating on the same sorts of data, just in parallel. So these are at the top. You can see your step number. You can see the TensorFlow ops that it's executing. And finally, the XLA ops. So TPUs are programmed via XLA, and you can see what's going on underneath the hood. Below that, you see your CPU compute threads. Now, this TF compute, these are your general TensorFlow thread pool threads. You've got your iterator thread. And then finally, there's a set of threads for in-feed and out-feed. These are the threads that are managing DMAs to and from the TPU device. Now, it's a little hard to see at the top, so we're going to need to zoom in. We're going to need to look in a little bit more depth. So in order to navigate around within the trace, the keyboard shortcuts I find are the most useful. Now, the keyboard shortcuts are from the left hand, so A and D move left and right. W and S move in and out. So this is a little bit like the arrow on like a keypad, just with your left hand on the home row. Now, there's a couple other keyboard shortcuts. So for example, if you click on something, you can see the details about what this is. And if you press F, you'll focus in on just that sort of element of the timeline, so you can zoom in and navigate around really easily. And if you want to see a little bit more about it, you can press M, and this marks it on the UI. And so you can see that our step time, our training step 80, took 5.4 seconds. And if we go to the in-feed queue, that was actually also 5.4 seconds. So let's dig into what's going on the CPU, since the TPU is just sitting idle waiting for data. Now, there's a lot of things going on, so we're going to need to zoom in a lot farther. So let's zoom in, not just at the second range, but let's zoom in down to the millisecond range. So here, we can see each of these vertical bars. That's 5 milliseconds, OK? And if we zoom in this far, we can see that our iterator is running continuously, and the map function is what's taking the longest amount of time, OK? The map function, there's a bunch of other little ops that are happening here that are your batching or your repeating or whatnot. But the map function is the bulk of the time. So that's where we need to focus our optimization efforts. And the map function runs the elements of the map on your normal standard TensorFlow thread pool. And if you look actually closely, we can zoom in a bit further, there's actually no 2 ops running at the same time. Even though we're using multiple different threads in the thread pool, we're actually processing this single-threaded. And that leads us to our first optimization. So we're going to switch back to the slides. this is what you need to do to use multiple threads for your input pipeline for your map function. You just set num parallel calls to 64, and you'll be using up to 64 threads on your compute node. And because cloud TPUs are hooked up to a very powerful host machine, you can certainly use all of these threads running concurrently. And if you do this and rerun your tool, rerun your model, you have a 4x improvement, over 600 images a second. So that's pretty great. But we're not done. An important part of the performance methodology is step 3, repeat. You have to repeat again. So we take a new trace. And I'm not going to do it live on the laptop because we want to go through. We have a lot of stuff to cover. We now see right here, we have a lot more compute threads going on, but we're still very much input bound. And if we zoom in a lot, you can actually see that the bottom element here, this TF record, we're waiting for data to load from our file system. We then process things in parallel really quickly, and then we take a while to transfer them to the device over PCIe. And so this presents a pipelining opportunity. Now, to give you a bit of intuition for what I mean, input pipelines you should always mentally associate with ETL. Extract is the first phase where you load the data from storage. Transform phase is where you prepare it for training. And finally, you load it into the accelerator. And this is reflected not just in the API, but this is a very useful mental model when you think about performance. Now, to give you a bit of intuition for that, each of the different phases of ETL use different hardware components in your server system. Your extract phase is exercising your disk in your storage system, or your network link if you're loading from a remote storage system. Transform typically happens on the CPU and is very CPU hungry. And your load phase is exercising the DMA, the connections to your accelerator. And this is true whether you're using a GPU or a TPU or potentially any other accelerators that you might be using. And so what's going on is if you map this out over time, you're extracting, and while you're extracting, you're doing nothing with the CPU. And during the transform phase, you're doing nothing with the connection between the CPU memory and your accelerator. And while you're training, the entire CPU and the whole rest of the machine is just sitting idle. This is incredibly wasteful. Because they're all using different components in your system, you can actually overlap all of this in a technique called software pipelining. So with software pipelining, you actually are extracting for step 5 while you're transforming for step 4, you're loading data for step 3, and you're training for step 2. And this results in a very efficient use of your compute resources. You get to train a whole lot faster. Now you'll notice that in a well-pipelined model, your accelerator will be 100% utilized, but it's possible that your CPU, or maybe even your disk, will be a little bit idle. And that's OK. Your accelerator is typically your most precious resource, and so that's what you want to be the bottleneck. It's OK if some of the other resources are slightly faster than you need them to be. So how do you enable software pipelining with data sets? It's actually very easy. You set num parallel reads is equal to 32, and underneath the hood, tf.data is automatically using parallel interleave, which is a key data set transformation that enables software pipelining. The other important change to make to your input pipeline is you set prefetch is equal to 2 right at the end. And this ensures that everything above is pipelined with everything below. In particular, your data transformations and your extraction is pipelined from your loading into your accelerator. Now, one thing I want to mention, when you set num parallel reads is equal to 32, you're also using, well, parallel reads. And this actually, the reason why we've sort of conflated these two in the API is because we believe that distributed storage is going to be critical going forward for machine learning workloads. So why is that? As we have the research, we see that data sets are going to become larger and larger over time. And so you're really going to need, they just won't fit on a single machine. You're going to need to distribute them across a cluster. Additionally, when you have data disaggregated from your accelerator nodes, it means you can more efficiently share your accelerator nodes. So that if you're training on them today, and tomorrow, or maybe in 3 minutes, someone else wants to train on it, you're not copying data sets around. It's just easier to use. And finally, it makes it a lot nicer when you're doing large-scale hyperparameter searches if you have one high-performance cluster and a fungible pool of accelerator resources. So we believe that distributed storage is going to be very important. We've worked very hard to make that fast with tf.data. So what happens if you do this? Well, as it turns out, with a cloud TPU, you'll get over 1,700 images a second with these optimizations. So we're now about 12 times faster than our initial input pipeline with actually less than 60 characters worth of typing. So that's pretty good. But we can do better. If you capture the trace, you'll actually see that our transform step is slightly longer than our accelerator training model time. The TPU is just too fast. And we need to break out some advanced optimization techniques that are available today. One of the most powerful ones is to use these fused dataset operators, map and batch, shuffle and repeat, that fuse together these operations to improve your performance on your CPU. TF.data works very, very hard to ensure that the elements produced out of your dataset by your iterator are in a deterministic order. But if you give TF.data permission to reorder, we can enable a number of additional performance optimizations. And so we can use sloppy interleave underneath the hood, which can work around a lot of variability in certain storage systems. There's other small tweaks that you can do, but if you apply all of them together, and for example, this optimized input pipeline, we get well over 2,000 images a second, and we are now accelerator bound. To see what that looks like, here's TensorBoard, and you can see that everything is 100% orange. We've entirely optimized away our input pipeline. We're entirely accelerator bound, and the accelerator is just churning 100% of the time. This is really great. This means that we now can actually start looking into optimizations that we can do on the TPU to make the TPU faster, because we can see that our CPU is idle. And so we can see that there's some overhead, this reshape and copy, that we might think about optimizing away with some device-specific optimizations, which brings me to phase 2. Now, as I mentioned before, we're in this sort of Cambrian explosion. And while we're still in the early days, we're finding that a lot of these different accelerators behave very differently. Some chips are smaller, some chips are bigger, some chips use HBM2, so for example, TPUs and GPUs, whereas some chips do away with that entirely, such as Graphcore's IPU, and go entirely for SRAM and optimize for communication. And so it's a little hard to provide out-of-the-box performance recommendations that are going to apply to all of these different hardware platforms. That said, there are a few common things that if we peer into the future, if we gaze into our crystal balls, we think this is what we're going to see more of. One thing that I expect we're going to see a lot of is interesting numerical formats. Now, this is FP32. It's a 4-byte, 32-bit floating point format that we know and love, IEEE. Most models today have been trained in FP32. There was some really great work put in by the folks at NVIDIA and Baidu, and they showed that with a little bit of clever tricks, you can train in FP16. Your weights stay in FP32, but your activations are in FP16. And this turns out to be a big win on 2 dimensions. Number one, you can run a larger model because more layers fits in memory. But additionally, your model tends to run faster because accelerators today, GPUs, and actually even TPUs, are not compute bound. They're actually memory bandwidth bound. The high bandwidth memory that we use on the accelerators is still too slow. And so FP16 can unlock a lot of great performance on devices. But I want to mention one other floating point format that's available, and that's bfloat16. TPUs are designed, have hardware support for bfloat16, and this actually is different than FP16. Even though it uses just 16 bits, the range is the same as FP32, and so you don't worry as much about vanishing gradients or exploding gradients in NANDs that you might encounter if you use FP16. There are a number of additional floating point formats or numerical formats, such as FlexPoint. Some folks from Intel presented at NIPS in a poster session, and I encourage you to check that out. But across all of this, we in TensorFlow, we're going to work hard to make it easier to use all these different numerical floating point formats. So stay tuned for more APIs and development in this space. One other hardware trend that I think we're going to see is we're going to see hardware optimization for matrix multiplication, especially in this mixed precision mode. So NVIDIA Volta GPUs, they have these tensor cores, which are hardware optimized 4x4 matrix multiplies. TPUs are built around a 128 by 128 matrix unit, and this is a systolic array, this special hardware transistor configuration that makes it really efficient to compute multiplication, and actually, as it turns out, convolutions. Here's this little graphic illustrating what a systolic array sort of does, and it sort of flows through in this, it's named after the heart, which is pumping blood in these cycles, and it plumbs through the data, and you get really fast matrix multiplication. What this means is because we're seeing hardware-supported matrix multiplication at different sizes and scales, the way you lay out your data and the way your model is implemented can make a huge difference on performance on these accelerators. Here I'm calling out two different models running on GPUs, where if you use channels last on a GPU, you end up losing a fair bit of performance compared to a channels first implementation. If you compare different LSTM cell implementations, the folks at NVIDIA have worked really hard to make really fast kernels for LSTMs, and they make it available as part of the cuDNN package. So if you're using a GPU and you want to get better performance, make sure you use the optimized libraries for your platform. Now, this is true. You need to use the latest version of TensorFlow. We're constantly working on performance improvements, latest version of cuDNN, and Intel MKL, which we talked about earlier today. If you still want better performance, investigate 16-bit numerical representations. We see a lot of potential performance advantages there. And if you're doing inference, we've talked previously about TensorRT, which is available for NVIDIA platforms that can help quantize and make inference really fast. And as a really advanced technique, if you see that, for example, a particular computation is a bottleneck, you can try and substitute it with something that's computationally faster. That said, you have to be very careful because you may change the quality of your model as part of doing this. With that, I'd like to move on to phase 3. Now, typically, when you use an accelerator, you're actually using more than one accelerator. Even if you're using a single device, it may have different components within it that operate in parallel. Here is, for example, a picture of the NVIDIA DGX-1 and shows the connectivity between the 8 GPUs. You have 2 cliques of 4 GPUs each with connectivity between them. And as it turns out, if you don't take advantage of this topology, if you do, for example, a naive gradient aggregation within the single server, for example, by going to the CPU or going via the PCIe switches, you will have a significant performance disadvantage compared to a clever utilization of NVLink via NCCL, NCCL2. Now, we have an optimized implementation available as part of the TFCNN benchmarks, but it's a little tricky to use, and so we're going to be working on making this easy for everyone to use in distribution strategies. And you'll hear a little bit more about distribution strategies in just a few minutes. TPUs, you also need to carefully aggregate your gradients, and we have the cross-shard optimizer. So what you'll do is you take your existing optimizer, momentum, stochastic gradient descent, SGD, and you just wrap it with the TPU cross-shard optimizer. And this will take care of aggregating across all the different compute shards within a single device, but the exact same code works all the way up to a whole cloud TPU pod across 64 different devices. Now, I want to take one moment to actually talk a little bit about measuring performance. I guess the saying goes, there's lies, damn lies, and statistics. Well, I'm going to add a fourth one, performance benchmarks. The internet is replete with shoddy benchmarks and misinformation, and this irks me to no end. We've seen benchmarks that they use synthetic data, or they're measuring only certain subsets, and so you have incomplete comparisons. One benchmark is comparing the full device, one is comparing only one part of the device. We've seen bugs in the machine learning where they've optimized away or done performance tricks that make it run faster, but actually make it not converge to the same accuracy. You've lost quality of your model. And additionally, as we look forward, this is actually, to be fair, a very nuanced space. And hardware is becoming harder and harder to give an apples-to-apples comparison because we have different numerical formats and different algorithms fit better on different classes of hardware. Some chips, for example, the IPU, have very small amounts of memory. And so if you have a very, very big model that just can't fit, that's a very unfair comparison. And so as a result, I strongly encourage you, if you're trying to choose and evaluate different hardware platforms, take your workloads and measure them end-to-end to the accuracy that you want in your application. That said, that's a fair amount of work. So if you can't run your own workloads, look to quality end-to-end benchmarks that measure time to accuracy. And I think the best example of this today is Stanford's DawnBench. Now, while there's nuance in the parameters of how the benchmarking are set, for example, the dataset size. Are you training on a small dataset size that fits in RAM or a large dataset size that you've got to load in over the network? And there's nuance in how you set the accuracy threshold. it's a lot harder, despite these, it's a lot harder for a system to perform well on an end-to-end benchmark, but then not be useful for real work. You're less likely to be misled when you look at these end-to-end benchmarks. That said, while we're pushing very hard for these end-to-end benchmarks, there's actually a lot of utility in what we call micro benchmarks to try and understand how fast are these different components. When I was preparing these slides and optimizing ResNet 50 for the cloud TPU case, how did I know that 150 images a second was way too slow? We can look to micro benchmarks to give ourselves calibration. So as Derek mentioned before, input pipelines on a DGX1 can have over 13,000 images a second, and that's using VGG preprocessing. This preprocessing is a little bit more computationally cheaper than the ResNet or Inception preprocessing, but it shows that we can go really, really fast. ResNet 50 on a DGX1 with real data is about 5.8 thousand images a second. And this is using a mixed precision IEEE Float 16. This is based on TFCNN benchmarks available with TensorFlow nightly. So this is the performance you can expect coming forward in the future. Now, if you just want to test the performance of the GPUs themselves in isolation, that's about 6.1 synthetic images a second. So you basically are excluding the cost of your input pipeline. For a cloud TPU, we have a few other micro benchmarks. For TensorFlow 1.7 that's available today, you can expect to achieve 2.65 thousand images a second on a cloud TPU, and that's using mixed precision bfloat 16 and FP32. You're streaming your data in from GCS with a batch size of 1024, and you can get to 76%, over 76% accuracy in about 13 hours. If you lop off the input pipeline and just test the device performance, you're actually over 3,200 images a second, which is very cool with TensorFlow 1.7. And with TensorFlow Nightly, so this will be coming in TensorFlow 1.8, we've done a huge amount of work to optimize the input pipeline performance, and you go from 2,600 images a second to over 3,000 images a second on a single cloud TPU, and this is coming in TensorFlow 1.8. So very exciting, a lot of work happening underneath the hood. As we stare into the future even further, what is coming in TensorFlow with performance? Now, this is actually our optimized input pipeline, or something very close to it. And you'll notice that there's sort of a lot of magic numbers in there that we've just hand-tuned and picked out. Well, how do we choose them? Well, we spend a lot of time playing around with it and picking them out. Do you need to do that? There's absolutely no reason why you need to do that. We can actually auto-tune a lot of these values, and we're going to be working on adding in smarts into TensorFlow to just tune your pipelines for you. And this is true not just of these magic numbers, but actually of dataset transformations, these fused dataset transformation operations. We'll be working on automatically switching a straightforward implementation to use the fused operations underneath the hood. And if you give us permission, we'll be able to adjust things where we're not preserving necessarily the order, but we're able to do the right things for you. Now, one thing I'd like to mention is that automatically tuning the prefetch buffer size, so that last line, that's available and coming in TensorFlow 1.8. We're not just working on optimizing the input pipelines, we're working on optimizing on-device performance. And there's two frameworks within TensorFlow. There's XLA and there's Grappler that are automatically doing graph transformations, picking optimal image layouts, for example, or rewriting your model to work well on different hardware platforms. And so there's a lot of exciting work going on here that we'll be excited to share with you over time. There's a lot more reading, and there's a huge amount of literature on this, so I encourage you to check out some of these things. If you would like to learn a little bit more about reduced precision training, here's some useful references. And actually, the traces that I had screenshots of in this talk, I'll tweet out this link shortly, but they'll be available so you can download and load them up into TensorBoard and play around with them yourself. With that, thank you very much for listening to me today. Next up is Mustafa, who's going to talk to you more about TensorFlow's high-level APIs.
Thank you, Ben. Hello, everybody. My name is Mustafa. Today, I'll talk about high-level APIs, but I'll keep practitioners like you in mind. So to keep the practitioners in mind, we'll define an example where you can improve user happiness by power of machine learning. And after we defining our example project, we'll use pre-made estimators to start our first experiment. Then we'll experiment more with every feature we have by feature columns. And we'll introduce a couple of pre-made estimators that you can experiment more. And we'll learn how can you experiment other modeling ideas too. So there are a lot of topics we will cover in this talk. And we'll also talk about how can you scale it up and serving so that you can use it in your production. Let's talk about estimators. So it's a library that lets you focus on your experiment. There are thousands of engineers. This is not a small number. And hundreds of projects in Google who use estimators. So we learned a lot from their experiments. And we created our APIs so that the time from an idea to an experiment will be as short as possible. And I'm really happy to share all this experience with all of you. Whatever we are using internal at Google is same as the open source one. So you all have the same things. Estimator keeps the model function. We'll talk about what is a model function later, but it defines your network and how can you train, or what is the behavior during evaluation or during the export time. And it provides you some loops, such as training, evaluation, and it provides you some interface to integrate with TF serving. Also, Estimator keeps sessions so that you don't need to learn what is TF session. It handles it for you. But you need to provide data, and as Derek mentioned, you can return a TF data set from your input function. So let's define our project and start with our experiment. I love hiking. This is one of the pictures I took in one of my hikes. And let's imagine there is a website, hiking website, similar to IMDb, but it's for hiking. And that website has information for each hike, and users are labeling those hikes by saying, I like this hike, I don't like this hike, this is my rating, and other stuff. And we want to use this data. Let's imagine you have this data from that website to recommend hikes for users. How can we do that? There are many ways of doing it. Let's define one way where machine learning can help us. In this case, we want to predict probability of a like, whether a given user will like a given hike or not. What you have hike features and user features. And where can you learn from? You learn from the labeled data. In this case, that website has whether that user like that hike or not. So what can we use to predict probability of a like? You can use one of the pre-made estimators. In this case, the NN classifier, because this is a logistic regression, or you can think it's a binary classification problem. So we designed pre-made estimators so that it can fit well to this kind of problems. This means you can use it as a black box solution. Pre-made estimators are surprisingly popular within Google and in many projects. Why that many engineers are using pre-made solutions instead of building their own models? I think, first of all, it works. It handles many implementation details, so you can focus on your experiment. It has reasonable defaults for initialization, partitioning, or optimization, so that you have a reasonable baseline as quick as possible. And it is easy to experiment with new features. So we'll learn about that. You can experiment with all of your data by using same estimator without changing it. So let's jump into our first experiment so that we can have a baseline that we will improve. I will talk about embedded column, but in this case, you are using hike ID. It may be a hike name or an identification as a single feature to your model. And let's say you instantiate the NN classifier with hidden units 1. So what this will learn, it will learn the average label for each hike ID. So that may be a good baseline for your overall progress. You need to say, what is your evaluation data? What is your training data? Then you can call train and evaluate. Just by this, a couple of lines of code, you should be able to experiment, and you can see the results on the TensorBoard. For example, you can see training and evaluation loss, or accuracy, how accuracy metric is moving. So since this is a classification problem, you will see accuracy metric. And since this is a binary classification, you will see area under curve for precision recall. So all of these things are free and ready to be used. Let's experiment more. Let's start with the data, experimenting with the data itself. We designed feature columns with the same mindset. We want to make it easy to experiment with your features, with your data. And based on our experience, internal experience, it reduces the lines of code and may improve the model quality. There are a bunch of transformations you can handle via feature columns. These are bucketing, crossing, hashing, and embedding. Each of these needs a careful explanation. Unfortunately, I don't have enough time here, but you can check Magnus's tutorial and Josh's video. They are really good. Let's experiment with all the hike features we have. Each hike may have tags, such as kid-friendly, dog-friendly, birding. You may choose indicator column instead of embedding column, in this case, because you don't have a huge number of tags, so you don't need to reduce the dimensionality. And for a numerical column, such as each hike may have elevation gain, you need to normalize so that optimization will be well-conditioned. Your problem will be well-conditioned. And you can use normalizer function here. Or you may choose bucketizing. In this case, the distance of a hike, we bucketize it so that it will help the model to learn different things for different segments. You can consider it as a different kind of normalization, too. How can you use all of these things together? Just putting them into a list, that's it. Then your system should work as it is. So let's experiment with personalization. What we mean by personalization is, instead of recommending same hikes to all users, let's recommend different hikes for different users based on their interests. And one way to do that is using user features. In this case, we are using user embedding by embedding column. So this will let the model to learn a vector for each user and put the users closer if their hike preferences are similar. And how can you use that? Again, it's just appending into your list. And you need to also play with number of hidden units, because you have many more features now, and you need to let your model to learn different transformations. And the rest of the pipeline should work. You will hear this sentence a lot during this talk, because it's based on that. The rest of the pipeline should work, and you should be able to analyze your experiments. Let's experiment more. We have a couple of pre-made solutions. I mentioned you it's very popular, and I picked only two of them here to show. One of them is Wide and Deep, which is a joint training of linear model and neural network. It may help your product, or it may not. You need to experiment. So let's start our experiment. You need to define what are the features you want to fit to neural network. Again, via feature column, it's a list. And you need to define what are the features you need to fit into linear part. In this case, I intentionally put user ID and text crossing so that, for example, if a user always picks dog-friendly hikes, the model will explicitly learn via this feature, via this cross. And you can instantiate DNN linear combined classifier instead of DNN classifier, and the rest of the pipeline should work. Based on the Kaggle survey, 2017 Kaggle survey, trees are extremely popular. And we are introducing gradient boosted tree as a pre-made estimator. This means you can experiment with neural network and gradient boosted trees without changing your pipeline. Let's start our experimentation with gradient boosted tree. In the current version, we only support bucketized column, and we are working on to support numerical column and categorical column too. Here, we use hike distance and hike elevation gain, and we bucketize them. And then you can instantiate boosted trees classifier. And the rest of the pipeline should work. We know that trees are not as computationally expensive as, or training trees are not as computationally expensive as training neural networks. And many of data sets fits into memory. So by leveraging that, we provide you utility so that you can train your model more than an order of magnitude faster than the usual one. And the rest of the pipeline should work. So let's say these already pre-made solutions are not enough for you and you want to experiment more ideas. Let's talk about them. Before delving into these high-level solutions that you can use, let's look at the anatomy of a feed-forward network in a supervised setting. In this case, you have a network which you fit the features. And based on the output of network and the labels, you need to decide what is the loss, what is the objective you want to minimize, and what are the metrics that you will use as a success metric for your evaluation. And your predictions on serving time may be different than in training time. For example, if you have a large multi-class setting, you may want to use just ranking of the classes instead of the probabilities in the serving time. For that, you don't need to calculate probability. You can use the logits output of network to rank them. So for all of these decisions, we abstracted them out under Head API. So Head API expects you to give the label and the output of your network and provides all of these things for you. We'll see in action. And model function is an implementation of this head and network together. We talk about the NN classifier. So the NN classifier has a model function, so it's an implementation, a specific implementation for head and network. Let's implement this with the Head API. In this case, instead of the NN classifier, we use the NN estimator. And we can instantiate a head. In this case, it's a binary classification head because we are trying to predict whether it is like or not like. And why are we introducing this head? Since these two lines is same as the NN classifier, why are we introducing this head? So that you can experiment many more ideas by combining different network architectures and different heads. For example, you can use wide and deep with a Poisson regression head, or the NN estimator with a multi-label head. You can even combine different heads together. We introduced multi-head here. So it's one way of experimenting with multitask learning. With a couple of lines of code, you can experiment with multitask learning. Please check it out. Let's say these pre-made architectures are not enough for you and you want to experiment more. You can write your own model function. We strongly recommend to you use TF Keras layers to build your network. So you can do whatever you want there. You can be as creative as possible. And after you have the output of network, you need to pick one of the optimizers available in TensorFlow. And you can use one of the head we mentioned, which will convert your network output and the labels into training behavior or evaluation metrics or export behavior. Then you can feed this model function to estimator. Again, rest of the pipeline should work. Keras model is another way of creating your model. And it's very popular. It's very intuitive to use. For example, this is one of the Keras model you can build. So how can you get the estimator so that rest of the pipeline should work? You can use model to estimator, which gives you the estimator, so you can run your experiments without changing your pipeline. Transfer learning is another popular technique we do, experiment with. One way of extending is using model A, which is already trained, to improve the prediction of model B. How can you do that? Surprisingly, just copying and transferring the variables from model A to model B works. That's simple, but it works. And we provide utility for you. So you can use warm start from. For example, this one line is saying that transfer all of the model A into model B. Or you can define a subset of model A to transfer from model A to model B. Let's talk about image features. We talked about embedding categorical column and numerical features, but what if you have image features? How can you use them in your pipeline without doing with a couple of lines of code? You can implement one of the state-of-the-art image classifier, which is not a couple of lines of code, or you can, thanks to TF Hub, you will learn a lot later, you can use this one line, just one line from TF Hub, to instantiate a feature column, which is called image embedding column. In this case, you may remember Jeff mentioned AutoML. NASNet is one of the AutoML model, and it's really good. It's one of the state-of-the-art model you can use. Here, you will use NASNet as a featureizer, which means it will use only the output layer of NASNet as a feature in your pipeline. And how can you use that in the DNN classifier we talked about? Same. You are just appending it into your feature columns. Done. Then you can experiment with it. So let's say you experimented and you find some models, but you need to scaling it up. Not all of you, but some of you may need to scale your training. So you can use multi-GPU, which means replication on different GPUs. Igor will talk about that after my talk. The key point here, you don't need to change the estimator or you don't need to change the model code. Everything should work with just a single line of configuration change. Or you may want to distribute your training to multiple machines by saying these are workers, these are parameter servers, and there's one evaluator going on. So same, you don't need to change your estimator or model code. Everything should work based on the configuration. Or you may want to use TPU estimator for TPU. In this case, there's a minimal change in the model function. Hopefully later we will fix that too. But now there's a minimal change in your model function you need to do. To use this in your production, you need to export, or you need to serve. And we recommend you to use TF serving. In the serving time, instead of reading data from the files, you have a request. And you need to define the receiver function, which is defining how can you connect that request into the model. So in this case, and after that, what will be the output of that model, which is defined by signature definition. So here, again, a couple of lines of code. You will export your trained model with TF serving friendly way. For example, if your request is tf.example proto, you can use this utility function to get your receiver function. And then you can use export set model so that it will be used by TF serving. These are the modules I mentioned: TF estimator, feature column, TF keras, contrib estimator, contrib feature column. Please do not use TF contrib.learn. We are deprecating it. And these are a couple of talks and videos I picked. You can check it out. Thank you. I hope some of you will improve your products with the tools that we mentioned. Happy hiking. And I'll introduce Igor. Igor will talk about distribution. How can you do distribution with TensorFlow? And he's coming. Yes, he's coming.
Hey. Well, hello, everyone. My name is Igor. I work in the TensorFlow team, and I'm going to talk to you today about distributed TensorFlow. Well, why would you care about distributed TensorFlow? Many of you know the answer probably, but just in case, it's a way for your models to train faster and be more parallel. It's a way for you to get more things done, iterate quicker. When you train deep learning models, it can take a long time. And when I say a long time, I mean weeks. With all the available hardware to you out there, scaling up to hundreds of CPUs or GPUs can really make a difference. how could you scale up? Well, you could just add a GPU to your machine. In this case, this is just plug and play. You insert a GPU, TensorFlow handles all the details for you, and you see a nice bump in the training speed. You could also insert multiple GPUs. In this case, you'd have to write additional code. You need to replicate your model. You need to combine gradients from every GPU. And if you're using batch norm layer, you have that tricky question of what to do with the statistics on each GPU. The point I'm trying to make is that you need to do additional work to make this work. And you need to learn stuff that you didn't plan on learning. You can also use multiple machines. And this situation is similar to the one before. But in this case, your bottleneck is probably going to be that communication between the machines. You'll start thinking about minimizing that communication and probably doing more work locally. For example, combining the gradients on the local GPUs before exchanging them with the remote GPUs. Unless specialized networking hardware is used, the coordination costs in this setup are probably going to limit your scaling. But there is an approach, there's a solution to this. This approach is called parameter server. Some hosts, we call them parameter servers, they're going to only hold training weights. Other hosts, workers, they're going to have a copy of the TensorFlow graph. They're going to get their own input, compute their own gradient, and then just go ahead and update the training weights without any coordination with other workers. So this is an approach with low coordination with between a large number of hosts. And there you go. This scales well, and we've been doing this at Google for a long time. But there is a wrinkle with this approach. You give up synchronicity, and that has benefits. And if you think about it, parameter server approach, it's an approach from the CPU era. With all the reliable communication between GPUs, we can consider designs which have tighter coupling and more coordination between the workers. One such approach is based on allreduce. That's not a new idea. The general goal of allreduce is to combine all the values and distribute results to all the processes. Allreduce is kind of tricky to explain on the slide. But you can think of its results as reduce operation followed by a broadcast operation. But don't think of it that way in terms of performance. It's a fused algorithm, and it's way more efficient than those two operations together. In addition to it, hardware vendors often supply specialized allreduce implementations that TensorFlow could secretly use behind the scenes to help you. All alternative approaches, they typically send all data to a central place. Allreduce is not going to have such a bottleneck because it distributes coordination between GPUs way more evenly. With every tick of allreduce, each GPU sends and receives a part of the final answer. So how could allreduce help us with our models? Well, consider, let's say you have two GPUs. You copied layers and the variables on every GPU, and you performed the forward pass, nice and parallel. But then during the backward pass, as the gradients become available, we can use allreduce to combine those gradients with their counterparts from other GPUs. In addition to that, gradients from the outer layers are available before the gradients from the other layers. So we could overlap backward propagation computation and allreduce communication. That gives you even more steps per second. The bottom line is when communication between GPUs is reliable, allreduce can be fast and allow you to scale well. how could you use all-reduce in TensorFlow? Well, so far in this talk, I told you that to take advantage of multiple GPUs, you need to write additional code, change your model, and learn stuff. Chances are you're following our advice of using the highest level API that works for your use case. That probably is Estimator. With Estimator, your model is specified by the model function, and it has no knowledge about GPUs or devices. So to have that model use multiple GPUs, you just need to add one line. You need to pass an instance of a new class called Mirror Strategy. And Mirror Strategy is a one implementation of our new Distribution Strategy API. Distribution Strategy tells TensorFlow how to replicate your model. Oops, sorry. Another thing I want to say is that Mirror Strategy could take a number of GPUs or a list of GPUs to use, or you can not give it any arguments at all, and then it will just figure out what GPUs to use. Mirror Strategy works in a way exactly as I described before. It replicates your model. It uses all-reduce for communication. So gradient updates from from all GPUs, they're going to be combined before updating the weights. And each copy of your model on every GPU is part of a single TensorFlow graph. That means this is in-graph replication with synchronous training that uses all-reduce on many GPUs. Now, the last 10 minutes are kind of a waste of time for you if this doesn't perform well. And it does perform well. As you add GPUs, this implementation scales well. We have a team at TensorFlow that specifically works on fast implementations of all-reduce for various machine configurations. And this implementation gets 90% scaling on 8 GPUs. And again, it didn't require any change to the user's model. It didn't require any change because we changed everything in TensorFlow that's not your model. Things like optimizer, batch norm, summaries, everything that writes state now needs to become distribution aware. That means that it has to learn how to combine its state with other GPUs. And this is important because alternative APIs out there, they typically ask you to rephrase your model, to supply optimizers, for example, separately, so that they can do all the state coordination behind the scenes. And if you have some experience with training your models on multiple GPUs, you might be wondering, well, can I save my model on a computer with 8 GPUs and then do an evaluation on it on a computer with, say, no GPUs? Typically, this causes a problem. But with Distribution Strategy API, we maintain the backward compatibility on the checkpoint level. So Mirror Strategy, it has multiple copies of the state on every GPU, and that state is in sync. So Mirror Strategy is going to save only one copy, and then at the restore time, it's only going to restore that state to required number of GPUs. So this use case is supported. Distribution Strategy works with eager mode as well, but we are still fine-tuning the performance. And Distribution Strategy is a very general API that I hope in the future will support many use cases. It's not tied to Estimator, and we are looking into ways of creating even more better APIs based on Distribution Strategy. In the future, pretty soon, we intend to support many kinds of distributed training: synchronous, asynchronous, multi-node, model parallelism, all of that is going to be supported based as part of Distribution Strategy API. But until then, for multi-node solution, please continue using Estimator, Train, and Evaluate. Or try Horovod. That's an outstanding community project that also offers a multi-node solution. Mirror strategy is available for you in our nightly build, and we are very, very actively working on it. And it's a product of work of many people. And I would really encourage you to try it out and let us know what you think about it via GitHub, or talk to us after my talk. All right, thank you. Thanks for your attention. Next up is Justine and Shanxing to tell you how to debug TensorFlow using TensorBoard.
Well, thank you, everybody, for being here. Today, we're going to be giving a talk about the new TensorFlow debugger, which comes included with TensorBoard, and it's basically a debugger like you would see in an IDE that lets you step and set breakpoints in models and watch tensors. But before we do that, I'd like to give you some background on TensorBoard and some of the other developments that happened in the last year, which we unfortunately don't have too much time to go into. But TensorBoard is basically a web application. It's a suite of web applications that was authored by about 20 people, and it's all packed into a 2 megabyte command line web server that works offline. And TensorBoard can be used for many purposes with all the different plugins that have been baked into it. The one you're all probably most familiar with, for those of you who have used TensorBoard, is the Scalars dashboard. You can plot anything you want. It could be like loss curves, et cetera, accuracy. And these things sort of help us understand whether or not our model is converging on optimal solutions. And here is a really interesting underutilized feature called the embedding projector. And this was originally written by Google, so we could do things like project our data into a 3D space, see how things cluster. Like if you're doing MNIST, the 7s go over here and the 9s go there. And we actually recently, what you see on this screen, is we got a really cool contribution from Francois Luz at IBM Research. And he sent us some pull requests on our GitHub repository since we develop in the open. And what he did was he basically added interactive label editing. So you can sort of go in there and change things as algorithms like TSNE give your data, sort of reveal the structure of your data. To learn more, search Google for interactive supervision with TensorBoard. This is another really amazing contribution that we received from a university student named Chris Anderson. It's called the Beholder plugin. And this basically gives you a real-time visual glimpse into TensorFlow data structures. Like, for example, as your training script is running, it's real-time. And it does require a hard drive, by the way. It doesn't work with something like GCS at this point in time. I think this could be a very useful tool going forward in terms of model explainability. Now, TensorBoard also has some new plugins for optimization. Cloud recently contributed a TPU profiling plugin. And TPU hardware is a little different from what many of you might be used to. And TensorBoard, with this plugin, can really help you get the most out of your hardware and ensure that it's being properly utilized. Now, the TensorBoard ecosystem, part of the goal of this talk, before we get into the demo, is I want to attract more folks in the community to get involved with TensorBoard development. We use many of the tools you're familiar with, such as TypeScript and Polymer. We also use some tools you might not be familiar with, like Bazel, but we use it for very good reasons. You can also explore our READMEs if you go to that folder for all the different plugins we wrote originally. Now, with TensorBoard, the The reason why this is a little bit, just a little bit more challenging compared to some of the other web applications you may have used in the past or written in the past is we deal with very challenging requirements. Like this thing needs to work offline. It needs to be able to build regardless of like corporate or national firewalls that may block certain URLs when it's downloading things. For example, one of the first things I did when I joined the TensorBoard team wasn't actually visualizing machine learning, but rather adding a contribution to Bazel, which helps downloads be carrier grade internationally. And there are a whole variety of challenges, like when it comes to an application like this. But those burdens are things we've mostly solved for you. And here's a concrete example. Writing that toilsome 1,000-line file was what it took to make TensorBoard look beautiful offline anywhere in the world without having to ping fonts.google.com. And that's just one of the many burdens that the TensorBoard team carries on behalf of plugin authors. Now, I want to give you a quick introduction for Shangxing, who is the author of this TensorFlow debugger, and with the help of Qi Zhang. So, as I mentioned earlier, TensorBoard has always done a good job being the flashlight that gives us broad overviews of what's happening inside these black boxes of models. What the TensorFlow debugger plugin does is it turns that flashlight into an X-ray. Using this plugin, you can literally watch the tensors as they flow in real time while having complete control over the entire process. This X-ray is what's going to make it possible for you to pinpoint problems we've previously found difficult to identify, perhaps down to the tiniest nan at the precise moments when they happen. That's why we call it an X-ray. It reveals the graph of math beneath the abstractions we love, such as Keras or Estimator, or, as was recently announced today, Swift. Whichever tools you're using, this can potentially be a very helpful troubleshooting tool. So I'd like to introduce its author, Shangxing, who can show you a demo.
Thank you very much. Okay, so in a moment, the screencast will start. Great. Thank you, Justin, for the generous intro. So I'm Shangxing, and I'm very glad and honored to present a featured plugin for TensorBoard, among many awesome, amazing plugins that people have created for TensorBoard so far. So the debugger plugin, for some of you who may know TensorFlow Debugger or TFDBG, it's the graphical user interface of TFDBG. And TFDBG has had only a command line interface until recently. So like the command line interface, the debugger plugin will allow you to look into internals of a running TensorFlow model, but in a much more intuitive, interactive, and richer environment in the browser. So in this example, in this talk, I'm going to show you two examples. One example of how to use the tool to understand and probe and visualize a working model that doesn't have any bugs in it. I'm also going to show you how to use the tool to debug a model with a bug in it. So you can see how to use the tool to get to the root cause of problems and fix them. So first, let's take a look at the first example. And that's the example being shown on the right part of the screen right now. So it's a very simple TensorFlow program that does some regression using some generated synthetic data. And if we run the program in the console, we can see it works. We can see a constant decrease in the loss value during training. Now, even though the model works, we have no knowledge like how the model works. And that's mainly because in graph mode, session.run is a black box that wraps all the computation in one single line of Python code. Now, what if we want to look into the model? What if we want to look at the matrix multiplication results in the dense layer? And what if we want to look at the gradient on the matmul operation and so forth? The TensorFlow debugger or TensorBoard debugger plugin is a tool that can allow you to do that. So to start the tool, we start the usual TensorBoard binary with a special flag debugger port. So in this case, we specify the port to be 7,000. Now, once the binary is running, we can navigate to our TensorBoard URL in the browser. Now, at the startup, the plugin tells you that it's waiting for connections from TensorFlow session.run, and that's because we haven't started the program yet. It also provides you code snippets that you can use, whether you are using tf.session, estimators, or Keras models. And in this example, we're using tf.session. So we're going to copy and paste 2 lines of code into our program. The first line is an import line, and the second line is a line that wraps your original tf.session object with a special wrapper that has the information of where to connect the port number. Now, with our program instrumented, we can start the program again. Now, as soon as the program starts, we can see the graphical user interface in the browser switch to a mode that shows you the graph of the session.run in 2 ways, in a tree view on the left and in a graph on the right. On the bottom left corner, you can also see what session.run is currently executing. The tree structure on the right corresponds to name scopes in your model. For example, the dance layer corresponds to, the dance name scope corresponds to the dance layer. One thing you can do is to open the source code view to look at the correspondence between your graph nodes and which lines of the Python program created those nodes. If you click matmul, for example, you can see the corresponding node in the graph view. You can also see which line of the Python source code is responsible for creating that node. In this case, it's where we call dance layer, as expected. If you click if you click the loss tensor, you will see the corresponding node in the graph again. You can also see where it's created in the Python source code, and it's where we call the mean squared error. And the gradients name scope corresponds to the back propagation part of the model. So that's how the model is trained. You can click around, poke around, and explore how a TensorFlow model does optimization and back propagation for if you're interested. And these nodes are all created when we call gradient descent optimizer. You can continue to any node of the graph and pause there. So we have just continued to the matmul node in the dense layer. You can also continue to the gradient on the matmul node, which we just did. And in the bottom right corner of the screen, you're looking succinct summaries of the tensor values we have continued to. You can look at their data type, their shape, and also the range of their values. So in the health pills, in the so-called health pills, you can look at how many of those values are 0 or negative or positive, and so forth. If you hover your mouse cursor over those health pills, you can get more information, such as the mean and the standard deviation of the values in the tensor. So next, we can click these links to open a detailed view of those tensors. So in these detailed views, you can apply NumPy-style slicing to reduce the dimensionality, so it's easier to look at the values of high-dimensional tensors. So we have just reduced the dimension from 2 to 1, so we're looking at the value as a curve. Now, next, we're going to continue to the loss tensor, which is a scalar. And yeah, it's a scalar, and the shape is an empty list, as we can see here. We can switch to the history, full history modes. We can look at how the value changes as the model is being trained. So with the full history mode enabled, we're going to continue over a number of session runs, like 50 of them. So we can see in real time how the loss value decreases and how the values on the matmul and its gradient change. So that's how you can use the tool as an X-ray or X-ray animator for your models to have a better understanding of how your model works. So next, let's take a look at an example of a broken model. So that's the debug MNIST model that we ship with TensorFlow. That's the only broken model we ship with TensorFlow, as far as I know, and I'm proud to be the author of it. And if we run the model, we can see the model doesn't quite work. After 2 iterations of training, the accuracy gets stuck at about 10%. Now, we suspect that there might be some bad numerical values like nan, not a number, or infinities in the model, but we're not sure which nodes of the graph are responsible for generating those nans and infinities. So to answer that question, we can use the debugger plugin tool. We start the binary again, and we do a refresh in our browser. And then we can start our debug MNIST example with a special flag to connect to the debugger plugin. So again, we're looking at the graph. Now, in order to find the nodes responsible for the infinities or nans, we can check the checkpoints to activate watch points for all the tensors. And we can use the conditional breakpoint feature to continue running the model until any tensor contains infinities or nans. So right now, you're seeing a list of tensor values. Those are a complete list of tensors involved in training the model. So in a moment, the model is going to stop, and that's because it has hit an infinity in the tensor called cross-entropy/log. Now, we can see in the health pill, we can also see in the detailed tensor view, those orange lines, and those show you the infinity values. Now, the question is, why do those infinity values happen? So we can go back to the source code and find the line of Python code where it's created, and that's where we call tf.log. We can also open up the graph view, and we see the input, so we can trace the inputs. In this case, the input is the softmax tensor. So we can click, expand, and highlight to look at the value of the input to log, which is softmax. And now we know that there are indeed 5 values of the tensor which are 0. And the reason for the infinity is because we're taking log of 0. Now, with that knowledge, we can go back to our source code and fix it, although we're not going to do this in this demo here. All right, so that's the TensorBoard debugger plugin, and I encourage you to use it, explore it, and hopefully it will help you understand your model better and help you fix bugs much more quickly. You can just use this simple command line, TensorBoard, with a special flag. And with that, I would like to hand this back to Justine.
Well, thank you, Shangxing. I thought that was a really interesting demo, and it was a great leap forward for TensorBoard, and it really shows that one of the things we've been doing recently is, rather than being a simple read-only reporting tool, we're trying to explore more interactive directions, as we've shown you today. And this is something that folks who are productionizing TensorBoard, such as Kubeflow, should take into consideration. We also want to attract more contributors. We have 2 approaches for this, where you can develop in our official repo and send us pull requests. We do our work in the open. This does need approval on security, footprint, etc. And there is an escape hatch if that doesn't work out. You can independently develop plugins. You can create custom static builds. Without anyone's approval, you can do whatever you want, because part of the goal on this team is to liberate the tools. With that said, I just want to thank all of you for attending, and I want to thank those of you watching on YouTube. If you like this talk, please hashtag Twitter or reach out. Thank you again.
Hope everybody had a good lunch. So I'm Sarah Sirajuddin. I'm an engineer on TensorFlow Lite team, and I have my colleague Andrew Selly also on the same team. And we're really excited today to talk to you about all the work that we've been doing to bring machine learning to mobile devices. So in today's talk, we'll cover 3 areas. First, we'll talk about how machine learning on device is different and important. Then we'll talk about all the work that we've been doing on TensorFlow Lite. And lastly, we'll talk about how you can use it in your own apps. So before that, let's talk about devices for a little bit. So usually when we say device, we mean a mobile device, basically a phone. And our phones are with us all the time. These days, they have lots of sensors which are giving rich data about the physical world around us. And lastly, we use our phones all the time. Another category of devices is edge devices. And this industry has seen a huge growth in the last few years. So by some estimates, there are right now 23 billion connected devices, so smart speakers, smartwatches, smart sensors, what have you. And an interesting trend to notice here is that technology which only used to be available on the more expensive devices is now available on the cheaper ones. So this rapid increase in the availability of these more and more capable devices has now opened up many opportunities for doing machine learning on device. In addition to that, though, there are several other reasons why you may consider doing on-device machine learning. And probably the most important one is latency. So if you're processing streaming data, such as audio or video, then you don't want to be making calls back and forth to the server. Other reasons are that your processing can happen even when your device is offline. Sensitive data can stay on device. It's more power efficient because the device is not sending data back and forth. And lastly, we are in a position to take advantage of all the sensor data that is already present on the device. So all that is great, but there's also a catch. And the catch is that on-device machine learning is hard. And the reason it is hard is that many of these devices have some pretty tight constraints. Small batteries, low compute power, tight memory. And TensorFlow wasn't a great fit for this. And that is the reason we built TensorFlow Lite, which is a lightweight library and tools for doing machine learning on embedded and small platforms. So we launched TensorFlow Lite late last year in developer preview. And since then, we've been working on adding more features and support to it. So I'll just walk you through the high-level design of the system. So we have the TensorFlow Lite format, and this is different than what TensorFlow uses. And we had to do so for reasons of efficiency. Then there's the interpreter, which runs on device. Then there are a set of optimized kernels. And then there are interfaces which you can use to take advantage of hardware acceleration when it is available. It's cross-platform, so it supports Android and iOS. And I'm really happy to say today that we also have support for Raspberry Pi and pretty much most other devices which are running Linux. So the developer workflow roughly is that you take a trained TensorFlow model, and then you convert it to the TensorFlow Lite format using a converter. And then you update your apps to invoke the interpreter using the Java or C++ APIs. One other thing that I want to call out here is that iOS developers have another option. They can convert their trained TensorFlow graph into the Core ML format and use the Core ML runtime directly. And this TensorFlow to Core ML converter is something that we worked on together with folks who built Core ML. So there are some questions that are top of mind for people every time we talk about TensorFlow Lite. And the 2 most common ones are, like, is it small in size and is it fast? So let's talk about the first one. So keeping TensorFlow Lite small was a key goal for us when we started building this. So the size of our interpreter is only 75 kilobytes. And when you include all the supported ops, this is 400 kilobytes. Another thing that is worth noting here is a feature called selective registration. So developers have the option to only include the ops that their models need and link those, and thereby keep the footprint small. So how did we do this? So first of all, we've been pretty careful in terms of which dependencies we include. And the second thing is that TensorFlow Lite uses flat buffers, which are more memory efficient than protocol buffers are. And then moving on to the next question, which is performance. So performance, super important goal for us, and we made design choices throughout the system to make it so. So let's look at the first thing, which is the TensorFlow Lite format. So we use flat buffers to represent models. And flat buffers is this cross-platform serialization library that was originally developed for game development use cases. And since then, it's been used in other performance-sensitive applications. And the advantage of using flat buffers is that we are able to directly access data without going through heavyweight parsing or unpacking steps of the large files which contain weights. Another thing that we do at conversion time is that we prefuse the activations and biases. And that allows us to execute faster later on. The TensorFlow Lite interpreter uses static memory and execution plans, which allows us to load up faster. There are a set of optimized kernels, which have been optimized to run fast on the Neon on ARM platforms. We wanted to build TensorFlow Lite so that we can take advantage of all the innovations that are happening in silicon for these devices. So the first thing here is that TensorFlow Lite supports the Android Neural Network API. The Qualcomm Hexagon DSP driver is going to be coming out soon as part of the Android P developer release. And Huawei and MediaTek are a couple of hardware vendors who have also announced their integration with Android Neural Network API, so we should be seeing those in the coming months as well. Second thing here is that we have also been working on adding direct GPU acceleration. And we're using OpenGL on Android and Metal on iOS. So quantization is the last bit that I want to talk about in the context of performance. So roughly speaking, quantization is this technique to store numbers and perform calculations on them in representations which are more compact than 32-bit floating point numbers. And this is important for two reasons. One, the smaller the model, the better it is for these small devices. Second, many processors have specialized SIMD instruction sets which process fixed point operands much faster than they process floating point numbers. So a very naive way to do quantization would be to simply shrink the weights and activations after you're done training. But that leads to suboptimal accuracies. So we have been working on doing quantization at training time. And we have recently released a script which does this. And what we see is that for architectures like MobileNet and Inception, we are able to get accuracies which are fairly similar to their floating point counterparts, while seeing pretty impressive gains in the latencies. So I've talked about a bunch of different performance optimizations. Now let's see what do all of these translate to together in terms of numbers. So these are two models that we benchmarked, and we ran them on the Android Pixel 2 phone. We were running these with 4 threads and using all the 4 large cores of the Pixel 2. And what you see is that we are seeing that these quantized models run more than 3 times faster on TensorFlow Lite than their floating point counterparts run on TensorFlow. So I will move on now and talk about what is supported on TensorFlow Lite. So currently, it is limited to inference only, although we are going to be working on supporting training in the future. We support 50 commonly used operations, which developers can use in their own models. In addition, they can use any of these popular open source models that we support. One thing to note here is that we have an extensible design. So if a developer is trying to use a model which has an op which is not currently supported, they do have the option to use what we call a custom op and use that. And later in this talk, we will show you some code snippets on how you can do that yourself. So this is all theory about TensorFlow Lite. Let me show you a quick video of TensorFlow Lite in practice. So we took the simple MobileNet model, and we retrained on some common objects that we could find around our office. And this is our demo classification app, which is already open sourced. As you can see, it is able to classify these objects. So that was demo. Now let's talk about production stuff. So I'm very excited to say that we have been working with other teams in Google to bring TensorFlow Lite to Google Apps. So the portrait mode on Android camera, Hey Google on Google Assistant, Smart Reply on Wear OS. These are some examples of apps which are going to be powered by TensorFlow Lite in the coming future. And with that, I'm going to hand off to Andrew, who will talk to you about how you can use TensorFlow Lite.
Thanks for the introduction. So now that we see what TensorFlow is, or TensorFlow Lite is in particular, let's find out how to use it. Let's jump into the code. So the first step of the four-step process is to get a model. You can download that off the internet, or you can train it yourself. Once you have a model, you need to convert it into TensorFlow Lite format using our converter. Once that's done, there might be some ops that you want to spot optimize using special intrinsics or special hardware that is specific to your application, or there might be ops that we don't yet support. You need to write custom ops for that. Once all that's done, you can go to your app, and you can write it using the client API of your choice. So let's look at the conversion process. So we support input of saved model or frozen GraphDef. Once you have that, you can use our Python API or a command line tool. Here we're showing the Python interface. So we give it a directory of a saved model, and it gives us a TF Lite flat buffer out. Once that's done, well, before that's done, there might be some things that you need to use to make this work better. So the first thing is you need to use a frozen GraphDef, or saved model is actually easier because it doesn't need to be frozen. Second, we need to avoid unsupported operators. A lot of times a training graph will have a lot of conditional logic or kind of checks that are really not necessary for inference. Sometimes it's useful to create a special inference script. Lastly, if you need to look at what your model is doing, the TensorBoard visualizer is useful for the GraphDef, but we also have a TensorFlow Lite visualizer to look at the flat buffers. And looking at these compared to each other can help you. If you find any issues, please file them with GitHub, and we will respond to them as we get needs. So lastly, write custom operators. So let's see how to do that. To write a custom operator in TensorFlow Lite is relatively simple. And it involves defining 4 functions. The main one is invoke. So here I've defined an operator that returns pi, just a 1 scalar pi. This is really useful. So once you've done that, you need to register these new operations. Now, there's a number of ways that you can register operations. If you don't have any custom ops and you don't need to do any overriding, you can use the built-in op resolver. But sometimes you might want to ship a TensorFlow Lite binary that's much smaller. So you might want to do selective registration. In that case, you should ship a needed ops resolver or include your custom ops in that same thing. Once you have that op set, you just plug it into the interpreter. OK, so now we've talked about custom operations. Let's see how we actually put this into practice in the Java API. So in Java, you give it your TensorFlow Lite flat buffer schema to the constructor of interpreter. Once you've done that, you fill in your inputs and outputs. And lastly, you run, which will populate the outputs with the results of the inference. Really simple. Next, how do I actually include this? Do I need to compile a bunch of code? We're working really hard to make it so that you can use TensorFlow from the pip and do all your training, and then you don't need to compile TensorFlow. So one of the things we provide is an Android Gradle file that you can include, and then you don't need to compile your own TF Lite for an Android app. We have a similar thing for CocoaPods to run TensorFlow Lite. So this will make it a lot easier to do. So now that we know how to use TensorFlow, let's look at our roadmap. As we move forward, we're going to add more ops so we can support more and more TensorFlow models out of the box. Second, we're going to add on-device training, and we're going to look at so you can do hybrid training, some of it on the server, some of it on your device, wherever it makes sense. That should be an option for you. And third, we're going to continue to improve tooling to analyze graphs better, to do more optimizations. We have more than we can talk about that we're working on, but we hope that this small peek of what we're doing and what our basis is will make you interested and excited to try it. So there's one remaining question left, which is, should I use TensorFlow Mobile or TensorFlow Lite? So TensorFlow Mobile is a stripped-down version of TensorFlow that includes a subset of the ops. Moving forward, we're going to put all of our effort into improving TensorFlow Lite and improving its ability to map to custom hardware. So we recommend that you target TensorFlow Lite as soon as possible, if it's possible. If there's some functionality that you still need in TensorFlow Mobile, let us know, and we'll work to improve TensorFlow Lite in a commensurate way. OK, demo time. So nothing like a live demo, right? So let's switch over to the demo feed, and we'll talk about it. And so we saw some mobile phones. Mobile phones are really exciting because everybody has them. But another thing that's happening is these edge computing devices. So one of the most popular ones has emerged for hobbyists is the Raspberry Pi. So what I've done is built some hardware around the Raspberry Pi. So if we zoom in, we can see that we have the we have the Raspberry Pi mobile board. And this is just a system on chip, similar to a cell phone chip. And one of the great things about the Raspberry Pi is that they're really cheap. Another great thing is that they can interface to hardware. So here we're interfaced to a microcontroller that allows us to basically control these motors. These are servo motors common in RC cars, and they allow us to move the camera left and right and up and down. It's essentially a camera gimbal. And then we have it connected to a Raspberry Pi compatible camera. So what are we going to do with this? Well, we showed the classification demo before. Let's look at an SSD example. So this is single-shot detection. So what this can do is it can basically identify bounding boxes in an image. So given an image, I get multiple bounding boxes. So for example, we have an apple here, and it identifies an apple. Now, the really cool thing we can do with this is now that we have the motor, we can tell it to center the apple. So we turn down the motors now, so now the motors are active. And as I move it around, it's going to keep the apple as centered as possible. If I go up, it'll go up. If I go down, it will go down. So this is really fun. What could you use this for? Well, if you're a person, it can also identify you. So currently, I have that filtered out. So if I stand back, it's going to center on me. So I could use this as sort of a virtual videographer. Imagine a professor wants to tape their lecture, but they don't have a camera person. So this would be a great way to do that. I'm sure that all the hobbyists around can now use TensorFlow in a really simple way, can come up with many better applications than what I'm showing here. But I find it fun, and I hope that you do. And I'm not an electrical engineer or a mechanical engineer, so you can do this too. All right. So thanks for showing the demo. Let's go back to the slides, please. So I had a backup video just in case it didn't work. It's always a good plan. But we didn't need it, so that's great. Let's summarize. So what should you do? I'm sure you all want to use TensorFlow Lite. Where do you get it? Well, you can get it on GitHub, right around the TensorFlow repository. How you can find out about it is looking at the TensorFlow Lite documentation on the tensorflow.org website. In addition, we're creating a mailing list, tflite@tensorflow.org, that you can email about some of your issues and your ideas. And we're also excited to hear about what you use TensorFlow Lite for. So with that, I hope to hear from all of you. One at a time, please. But so with that, I want to thank everybody. Thanks, Sarah, for her presentation. I thank your attendance, everybody who's around the world listening to this. And in addition, this was work that we worked very hard with other members of the Google team, lots of different teams. So there's a lot of work that went into this. So thanks a lot. So with that, we have our next talk. And where's our next speaker? Our next speaker will be Vijay, and he's going to be talking about AutoML.
Thank you very much. Hi, everybody. My name is Vijay, and today I'll be talking to you, or hopefully convincing you, that when we try to apply machine learning to solving problems, that we should really be thinking about designing search spaces over solutions to those problems. And then we can use automated machine learning techniques in order to evaluate our ideas much more efficiently. I think a big reason why a lot of us are here today is due to the incredible impact that machine learning can have on practical problems. Two often cited reasons for this is that we have increasing amounts of compute capability and access to data to train on. But I think one other aspect is all of you, right? There's so many more people involved in machine learning today that are contributing and publishing ideas. So this graph tries to put this into perspective by measuring how many machine learning papers are published on arXiv every year since 2009, and plotting that against a Moore's law exponential growth curve. And as you can see here, we've been keeping up with Moore's law 2x every 2 years very, very well. And this is demonstrating just how many new ideas are being developed in the field. And this is a great thing, right? So one concrete way of looking at this is that in the field of computer vision, we've seen top one ImageNet accuracy start from something like in the 50% range from the AlexNet architecture, which, by the way, revolutionized the field of image classification. And every year, we've been just getting better and better up until 2017. Now, these improvements haven't come just because we've been training bigger models, right? These improvements have also come from the fact that we have lots of great ideas, right? Things like batch normalization, residual or skip connections, and various regularization techniques. Now, each of these points, like Jeff mentioned earlier, is the result of years of research effort, and we build on each other's ideas. But one of the challenging things is how do we keep up with so many ideas that are being produced? And I also want to zoom in a little bit in terms of the complexity of some of these models. So we're going to zoom in a little bit on Inception v4 here, and look at the kind of idea that's embedded inside there. These are two convolutional cell models, or modules within the Inception v4 architecture. Every single one of these arrows and operations and even the numbers was designed by a human, right? Somebody wrote some code in order to specify all of these little details. Now, there are high-level reasons why this kind of architecture might make sense, but our theory doesn't really explain with so much certainty how every detail seems to matter. And as a field, I think we're definitely working on trying to improve the theory behind this. But for many of us, we're just happy to use this kind of complexity out of the box if we can, because it really helps to solve problems. Now, this isn't too surprising. We know that because machine learning has had such an impact on real products, that we're going to be willing to use anything we possibly can, and even if we don't understand all the little minor details, as long as it solves our problems well and hopefully are understandable. So given all these ideas, how can we harness this explosion of ideas much more efficiently? So let's step back and kind of ask a few questions that we might have heard when we were just trying to train machine learning models. And these are simple questions, but hard questions. Like, what learning rate should I apply for my optimization? Or if I'm training a deep neural network model, what dropout rate should I apply? How do we answer this question today? I think we combine a few different types of benefits. One of them is leveraging researcher intuition and engineering intuition. And what this means is that we start with code, or we ask our colleagues, hey, what are good settings for these fields? And if it were the case that there was one setting that worked for everybody, we wouldn't even be looking at these parameters. But it does matter, so then we move on to some trial and error process. We try a certain setting, and then we see how well it works on our problem, and then we continue to iterate. And I think the other aspect, which is becoming more common, hopefully, is increasing access to compute and data by which we can evaluate these ideas. So this combination is really ripe for automation, right? And not surprisingly, this exists today. It's called hyperparameter optimization. And in this kind of setup, what we have is a tuner that's giving out settings for these hyperparameter settings. We have a trainer that trains our model on our data set and then tries to give some kind of signal about how good those settings were. And so it might give a validation accuracy of some value. And the tuner can then learn from this feedback to find better points from the search space. And this is an existing big field, and there are existing systems like those shown at the very bottom that can help you to do this. But now let's kind of ask a few more complicated questions or detailed questions that I think people do often ask as well. Why do you use batch norm before ReLU? I switch the order, and it seems to work better. Or if you're trying to train a completely new model, should I use one type of sub-architecture or another type of sub-architecture? Now, if you think about it, these questions aren't really that different from hyperparameter settings. So if we think of hyperparameter optimization as searching over a specific domain of ideas, then it seems possible that maybe we can actually treat the decisions made in this type of model as another form of searching over a domain of ideas. And we can therefore think about de-emphasizing any specific decision that we make in our architectures, and instead think about the search space of ideas that we might have. So let's take a concrete example of a search space design that my colleague Barrett did, where he tried to design a search space for a convolutional cell. And I'll walk you through how you might design such a search space. So the first question is, you have to get your inputs. So we might say you have access to your previous input, and if you want to have support for things like skip connections, you might have the previous input. So your first job in the search space is to define which inputs I'm going to select. And then once you have those inputs selected, you want to then figure out what operation should I apply to each of those inputs before summing them together. So I might select something like 3x3 convolution or 3x3 max pooling, and then combine those operations together. Now, we can then recursively turn that crank and apply it several more times, where we use maybe different operations for different inputs. And we can even use the intermediate outputs of previous decisions in our search. And then finally, you take all of your outputs that are unused, and you concatenate them together. And that is your convolutional cell. And then finally, if you want to build your whole model, just like ResNet, you might stack that same model several times. Now, I want to point out that this is just one example, like one point from the search space of ideas. There are a billion possible ways that you can construct a cell like this in this search space by changing the set of operations you have in your list, the kind of ways that the connections can be made, and so forth. So now we've defined that our search space, we kind of go back to that hyperparameter tuning type system where we have a program generator on the left that generates samples from this search space. We then train and evaluate on the task at hand, and oftentimes it's going to be a proxy task. And then we iterate to quickly find what are the best programs from our search space. And the system on the left, this program generator, can optionally learn from feedback. So it might use something like reinforcement learning, evolutionary algorithms, or even random search can work well in certain situations. So we did this type of approach. We took this convolutional cell, we trained it on a proxy task such as CFAR10 for a small number of epochs to make quick progress on the evaluation of an idea. And then we took the best candidate cells that we found from that search. We enlarged in terms of number of filters and number of times we stacked it, and we applied that to the ImageNet data set. And these are two cells found from that search. And if you then look at the results of applying those, you'll see that we were actually able to do better than the existing state-of-the-art models in terms of top one accuracy. Now, this was an effort. This effort was an example where we took a model where decisions were pretty complex, and we honestly found another complex model that was better. But next, I'll show you an example where we can use this general technique to find even more interpretable outputs. So let's look at optimization update rules. Most of you are probably familiar with stochastic gradient descent. And the update rule is shown on the left, where you take the gradient and you multiply it by the learning rate, and that's your weight delta. And then we have more advanced optimization update rules like ATOM. And these can be expressed fairly concisely just by being given things like the moving average of the gradient and so forth. But we really only have like a handful of these type of optimization update rules that we typically apply for deep learning, for example. What if we instead treat these update equation rules as parts of a larger search space? And so you can take these expressions and turn them into a kind of a data flow graph that describes the update rule. And by using a small set of primitive operations and ways of combining them, we can express these two update rules using this simple tree, but also a lot of other ideas. And so you can then turn this crank on this new search space and try to find a better optimization update rule. So my colleagues, Irwin and Barrett, ran this experiment where they took a fixed convolutional model and tried to search over the optimization rules. And they found update equations that did better than some of the others I had shown you on this particular task. And one nice feature of this search space is that the results are much more interpretable. If you look at the fourth update rule here, It's taking the gradient and multiplying it by some expression that essentially says that when the gradient and the moving average of the gradient agree in their direction, then we should take a bigger step in that direction. And when they disagree, that we should take a smaller step. This is actually a form of momentum. And so one thing we can get from this is maybe we should be designing search spaces that have more notions of momentum encoded within the search space of ideas. We may be able to find even better results. So far, I've focused on techniques and search space ideas where we care about accuracy. But what's great about searching over many ideas is that we might have the potential to search over more than just accuracy. So, for example, a lot of us care about inference speed, right? We want to take a model and deploy it on real hardware, real mobile platform. And very often, we spend a lot of time trying to figure out how to take one idea and make it fast enough. But what if you could, as part of the search space of ideas, find ones that balance both speed and accuracy? So we tried to do this experiment where we included the runtime on a real mobile device as part of this inner loop of the evaluation. So we tried to focus to optimize on both accuracy as well as inference speed. And as this process goes on, over time, the program generator is able to find faster models while also figuring out how to make those models even more accurate. One interesting side effect of this is that when you run searches over ideas, the output is actually not just one model, it's a culture of models that implicitly encodes this trade-off. So this kind of shows you that we have points along the space that provide a trade-off between inference speed on a mobile platform and accuracy on the data set that we're trying to solve. And so rather than manually engineering the one point that I really want to get working, I can get a result that maybe can be deployed on various types of platforms. So I'll emphasize this in maybe a slightly different way, which is that we could define a search space of ideas in TensorFlow, and through this automatic machine learning process, we can get models that have a guaranteed runtime performance target on a target platform device. And one of the nice things about having an integrated ecosystem like TensorFlow is that you can just use the libraries that convert from program to program so that you can get this end-to-end pipeline working well together. There's no manual work required to specifically tune a model. So let me conclude by returning to this process of evaluating ideas in this world where we're trying to explore different ideas. The first is that we design search spaces to try to test out a large set of possible ideas. Now, note that when we designed the search space, that required human intuition. Right? There's still a need for human ingenuity as part of this process. So designing the search space properly takes a lot of effort, but at least it allows you to evaluate many more ideas much more quickly. And when it comes to trial and error, we had to start thinking about how software should be changed so that we can permit this type of search process. So for example, I think many of us have probably written scripts where you take things like learning rate and dropout rate as command line flags. What if you wanted to test out much more deeper ideas in your programs? How do you design it such that it's much more tunable at all levels of your program? I think this is a big question for us to tackle. And lastly, we think these ideas will become increasingly relevant as many of you get access to more and more computation capabilities, such as things like TPU pods. Imagine a world where all you have to do is take your idea, submit it to an idea bank, and you have some pod of TPUs crunching overnight, trying to figure out which problems, which solutions or ideas are the best, and then waking up in the morning and it telling you, these were the good ideas, these were the bad ideas, and so forth. I think part of the reason this excites me is that automatic machine learning can keep these machines much more busy than we can. We have to sleep, but machines can keep on churning 24/7. So with that, thanks for listening. Next up is Ian, who will be talking to you about fusion plasmas.
So I want to talk to you about something that's very important to me. And that's how will civilization power itself for the next 100 years? So in 2100, the projected world's population is 11.2 billion. If all 11.2 billion people want to enjoy the same power usage that we do now in the United States, that's going to require burning around 0.2 yotta-joules of energy over the next 100 years. So that's a whole lot. So to put that into perspective, if we wanted to do that with oil alone, we'd have to ramp up oil production by a factor of 10 for the next 100 years. So there's no way that's going to happen. So besides being infeasible, that would contribute to catastrophic climate change. If we want to keep climate change to a level that's not ideal, but at least reasonable, say under 2 degrees of temperature increase, then only 8% of that 0.2 yotta-joules can come from fossil fuels like coal or oil. So where does the other 92% come from? So one possible source would be nuclear fusion. So fusion involves pushing together 2 smaller nuclei, and what you get out is a whole lot of energy and no greenhouse gas. So right now the sun runs on nuclear fusion, and the reaction is so energy dense that 0.2 yotta-joules would require, say, a trivial amount of deuterium found in seawater, or say just 7 months of the world's current boron production, so a very trivial amount of boron. So far it sounds like some sort of miracle fuel. Well, what's the catch? Well, the difficulty is that people have been trying this for 70 years, and so far no one has gotten out more energy than they put in. So to understand this, you have to imagine that the reaction takes place inside of a plasma, and a plasma is a 1,000,000+ degree swarm of charged particles. And these particles don't want to stay in place. The sun uses a gravitational force to keep everything in place. We can't do that, so instead we use magnets. Now, magnets, you try to squeeze it with magnets and it can pop out the end, and you can get little turbulent ripples, and what happens is the plasma breaks up, it gets unstable, it gets cooler, and then the reaction stops. And that's what's been happening for 70 years. So this is the kind of problem that I like. It combines physics, probability, computation, mathematics, and so I was like, I want to work on this, and how can we accelerate progress? So Google is not building a fusion reactor. So what we have done is we partnered with TAE Technologies, and this is the world's largest private fusion energy company. And we've been working with them since 2015. So pictured here is their 5th generation plasma generation device. And this thing is huge. It would fill up a large part of this room. And then in the center, is where the plasma is kept. So this is an elongated toroid. And the goal really is to keep this in place and prevent turbulence. And if it gets out of place, then the reaction stops. So there's magnets and neutral beams and a host of other technologies to keep it in place. Now, what's Google's job specifically? Well, our goal is to take the measurements that come from this experimental reactor, and every time the physicists do an experiment, within 5 minutes, we want to tell them the plasma density, temperature, and magnetic field on a 3-dimensional grid. So how hard is that? Well, first of all, the plasma is very, very hot, so you can't just poke it with a thermometer like a turkey. So the thermometer would melt, and you would disrupt the plasma and ruin the experiment. So what you do have are measurements along the boundary. But there's only so many measurements you can take, because you can't cut that many holes in the side of this device. So let's look closely at one. Let's look at measuring of electron density, and that's done with a device known as an interferometer. An interferometer shines lasers through the plasma, And then the phase shift is proportional to the average electron density along that ray. So we have 14 lasers shining through the center of the plasma. So we know the average density along 14 lines. And from that, we want to know the density everywhere. So clearly, there's no one unique solution to this problem. And instead, we'll have a distribution over possible solutions. So we do this in a Bayesian sense. And our final output will be a probability density function for the density of the electrons given the measurements. And we can visualize that with a graph where you have the mean and some error bars. How does TensorFlow help with this? Well, so the first place is translating measurement physics into code. So let's consider the distribution for the camera measurement. So the cameras measure photons, and say we have some photons that are being emitted from the plasma. The mean number of photons reaching the camera is given by a sparse tensor, dense map mole. But we don't actually realize the mean. Instead, what we realize is a noisy mean. So there's noise due to a finite number of photons. That's Poisson noise. We also have discretization noise because we discretize space. So the TensorFlow distributions library gives you access to this normal distribution object so that this noisy flux represents a normal distribution. It has a mean. It has, you can draw samples. You can compute the PDF and so on. That's not all, though. We also have an analog to digital conversion process that we model as passing this normal distribution through a nonlinear response curve and then digitizing it to 8 bits. So at the end, this digitized charge is another distribution object that has an ability to take samples. You can compute the probability mass function because it's discrete, and so on. Now, since we want to be Bayesian, we can assemble a number of these distributions, giving us a likelihood and a prior and so on, with the goal of producing a posterior. And then we do Bayesian inference. So now to do inference, we do this in 2 different ways. The first way is variational inference, which amounts to minimizing a loss function. And by minimizing that loss function, you get an approximation of the true posterior. So this minimization is done just like any other TensorFlow minimization. For example, we use Atom Optimizer. The second way is using Hamiltonian Monte Carlo. So the TensorFlow probability library gives you access to a number of Monte Carlo samplers, and the Hamiltonian Monte Carlo is one that uses gradients in order to help you take samples faster. So notice in both cases, we're using auto differentiation. Here, whether we're taking gradients of this loss or whether we're taking gradients to do Hamiltonian Monte Carlo sampling. Okay, so popping up a level, you'll notice we're not doing deep learning. Instead, we're doing an inverse problem whereby measurements given to us from physicists are translated into a reconstruction of some physical state. So there's a few differences I want to highlight. First of all, there are no labels that are given to us. The natural label here would be a 3-dimensional image of the actual plasma. But we're the ones who are telling people what the plasma looks like, so we're the ones actually producing the labels. So given that there's no labels, you might be tempted to say, well, this is an unsupervised learning technique like word clustering. There's a key difference, though, that here there really is a right answer. There really was a plasma out there, and if that plasma doesn't fall within our error bars, we've made a mistake. And also, you'll notice that our graph here models physics rather than generic functions. So it's a bit more constrained than these deep neural networks, but that allows us to get the right answer with no labels. So at the end of the day, TensorFlow despite it not being deep learning, TensorFlow adds value with the TensorFlow distributions and probability library. We have auto differentiation to do inference. And in order to provide answers to many measurements at once, GPUs and distributed computing is very important. So thank you very much. And next up, we have Corey talking about machine learning and genomics.
Hello, everyone. My name is Corey McLean, and I'm an engineer on the genomics team in Google Brain. And today, I'm excited to tell you about Nucleus, which is a library we released today to make it easy to bring genomics data to TensorFlow. So genomics is a study of the structure and function of genomes. In every cell in your body, you have 2 copies of the genome, one from each parent. And this is strings of DNA, which is a 4-letter alphabet, and about 3 billion letters in the genome. So here is a picture of a snapshot on chromosome 1, 150,000 letters. What we can see is there's a number of known things about this area. One, there are functional elements, like the genes depicted in that second row. Biological measurements allow us to analyze what are different things that are active in cells. So on that third row, we can see the amount of gene expression across different tissue types is quantified there. And at the bottom, through sequencing many people, we can identify places where there's variation across individuals. Now, there's many different computational and algorithmic challenges in developing that image. This ranges from, on the experimental data generation side, can we better take the output of these physical measurements to get accurate DNA readings, or reduce noise in the experiments that quantify this expression? Can we take the DNA sequence and interpret where are functional elements like these genes, or predict how active are they in different tissue types? And can we identify places where individuals vary compared to a reference, and how is that different in small variants versus, say, in cancer? And how do those changes influence human traits? So one thing that is really exciting for us is there are many opportunities for deep learning in genomics. And a lot of that is driven by the increase in the amount of data available. This graph shows the dramatic reduction in cost to sequence 1 million bases of DNA over the past decade. But also, there's a lot of structure in these data sets that is often complex and difficult to represent with relatively simple models. But this may display convolutional structure, so we can use techniques from image classification as well as sequence models. And there have been a number of proven successes of applying deep learning to problems in genomics, such as Deep Variant, which is a tool our group developed to identify small variants using convolutional neural networks. So our goals in genomics are multifaceted. One is to make it easy to apply TensorFlow to problems in genomics, and do this by creating libraries to make it easy to work with genomics data. We're also interested in developing tools and pushing the boundaries on some of these scientific questions using those things that we've built, and then want to make all of that publicly available as tools that can be used by the community. So today I'll focus on the first part of making it easy to bring genomics data to TensorFlow. So what is a major problem? One major difficulty is that there are many different types of data that are generated for genomics research. You can see here on the right a subset of different types used. And these different file formats have varying amounts of support and, in general, no uniform APIs. We also have some concerns about efficiency and language support, where we would like to be able to express some manipulations in Python, but need some effective ways to efficiently go through this data, such that native Python wouldn't make that possible. So to address these challenges, we developed Nucleus, which is a C++ and Python library for reading and writing genomic data to make it easy to bring to TensorFlow models and then feed through the TF Data API that Derek talked about earlier today for training models for your particular task of interest. In this release, we support the reading of many of the most common data formats in genomics and provide a unified API across the different data types. So we're able to iterate through the different records of these different types and be able to query on specific regions of the genome to access the data there. The way that we develop this uses protocol buffers under the hood so that we can implement all of the general parsing in C++ and then make those available to other languages like Python. And for those of you familiar with genomics, we end up using HTSLib, which is a canonical parser for the high-throughput sequencing formats, like the aligned reads and variants, and then wrap that to generate the protocol buffers, and then use Cliff on top of this to make the data available to Python. And finally, we use some of the TensorFlow core libraries so that we can write out these data as TF records so that they can be ingested by the TF Data API. So the data types that we currently support are the following, ranging from general genome annotation to reference genomes and different sequence reads, or whether they're direct off the sequencer or mapped, as well as genetic variants. So to give an example of the reading API, it's quite straightforward. So this is kind of a toy example, but is essentially similar to what is used for deep variant when we want to train a model to identify actual genome variations based on mapped sequence reads and a reference genome. So we have 3 different data types that we need. We import the different reader types, and then say in this region that we're interested in, we can issue queries to each of the different reader types, and then have iterables of these protocol buffers as output, which we can then manipulate and turn into TensorFlow examples. On the writing side, it's similarly straightforward. So if we have a list of variants for the common VCF format, we'll have an associated header which provides metadata about this, and then open a writer with that header, and then just loop through the variants and write them. And note that we support writing to block gzip format, which is common for the subsequent indexing by other tools. However, we can also write directly to TF records, and here provide some convenience methods to write out sharded data, which we found helps avoiding certain hotspots in the genome using a very similar API. Finally, we have been working with the Google Cloud team, which has some tools for analyzing variant data. And so they have developed a tool called Variant Transforms, which allows you to load the VCF variant files to BigQuery using Apache Beam. And then you can do structured queries over that data. And so we're working now to integrate here to have Nucleus under the hood providing that generation of the variants. And to learn more about that tool, you can go to the link below. So to summarize, we have developed Nucleus, which is a C++ and Python library, to make it easy to bring genomics data to TensorFlow to train your models of interest for genomic problems. And we have the ability to interoperate with Cloud Genomics and are being integrated into the variant transforms at the moment. And this ended up being the foundation of our CNN-based variant caller, which is also available open source at the link below. So with that, I would like to thank you all for your attention today. Next up, we'll have Ed to talk about open source collaborations.
Thank you. Hi, everyone. Now, I was going to talk to you about my plans to reanimate dinosaurs with TensorFlow, but I didn't want to steal those guys' thunder. So actually, I'm here to talk about open source collaboration in the TensorFlow project. And that's my job at Google, to work on growing the participation and the collaboration in the project in the whole community. So you guys all here and everybody watching on the live stream are a huge part of this already. If you saw a slide like this at the beginning of the day in Rajat's keynote, you'll have seen the numbers have already ticked up. In fact, in the 5 days I've been monitoring this slide, I've kept increasing the numbers because the amount of participation on TensorFlow is kind of staggering. As an open source project, it blows my mind when I came to work on it. And so much of that is due to the participation of everybody here in the community. There are parts of TensorFlow that wouldn't exist, and many of them, without that collaboration. For instance, whether it's Spark connectors, whether it's support for particular architectures and accelerators, or maybe certain language bindings. We don't only benefit from a huge amount of adoption by being open source, but as the adoption grows, this is the way we sustain and grow the project. You saw this map earlier as well. This is just some of the GitHub stars that gave it their locations that we could map. And was far north as Norway and far south as the Antarctic. And what is really obvious right here now is, although there's a large team at Google developing TensorFlow, there are far many more people outside and far many more places who are using it. And the truth of a popular open source project is that more adoption is more demand. There's so much for us all to do together to grow TensorFlow. Now, you ever that thing where you turn up to a party and like, everyone's having a good time, and they all seem to know what they're doing and why it's such fun, but who am I going to talk to, and what are they all looking at? And sometimes a large open source project can be a bit like that. You want to get involved in contributing to TensorFlow, but where do you start? You think this module or this feature over here is something you want to work on, but where do you find the right person to talk to? How do you learn what we're thinking about the direction for this? So we've heard some of those things from you, and we recognize that we want to improve our openness, our transparency, and our participation. We're trying to work on making it easier to get involved in TensorFlow. We've already, for instance, refreshed our roadmap, which you can find on the TensorFlow website, about the general direction of a lot of the code. And we'll do that a lot more regularly. But I want to talk about 4 initiatives that we have going that will enable us all to work together more effectively and faster. The first of these is simple. It's a central community for everybody who's working on contributing to TensorFlow. GitHub has so much energy going on. There's so much great debate in all the issues, if you look in there, and the pull requests, really thoughtful conversations and contributions. Thank you for your input in that, and thank you for being part of that. But what we don't have is a central place where we can collaborate. So what we'll be bringing online, in fact, you can go and subscribe now, is a mailing list, developers@tensorflow.org. And that's a place for contributors to TensorFlow to work together. So if you're contributing to TensorFlow or want to contribute towards TensorFlow, go and join. And we can work together as a community to discuss design ideas, to get feedback, to coordinate together. And many of the projects that you've heard about today have mailing lists that you can also find at tensorflow.org/community, whether it's TF Lite or tensorflow.js. So that's collaboration. Now, we already talked about the fact that there are many use cases outside of Google that the core team just don't see. In fact, many more. Much more happens outside than inside the core team. So we want to make it possible for people with shared interests in a project to work together. This is where the beauty of open source comes in. How do we do that? So we're setting up a structure for groups to work on areas of TensorFlow together, special interest groups, or SIGs. We've been piloting the first of these for a few months now. This is called SIG Build, and it's all about building, packaging, and distributing TensorFlow. Familiar with TensorFlow, you know we build it in a certain way. Well, guess what? Not every architecture, not every application finds that the best way for them. For instance, Linux distributions want to build against the shared libraries in the distribution. That's not something we do. So we brought together a bunch of stakeholders over Linux distributions, companies like SUSE, Canonical, Red Hat, companies like IBM, NVIDIA, Intel, to collaborate in a group that will look at the build of TensorFlow and make that work more effectively for more people in future. That's just one group, the pilot. And we want to pave the cow paths. So where there is energy and where there are people collaborating on a particular thing, that's a great candidate for bringing a special interest group together. This week, we're also bringing online a group for TensorBoard, where key stakeholders of the TensorBoard ecosystem can focus on design and collaboration, and also for the Rust language bindings, which is a completely community-driven part of TensorFlow. Each SIG is going to have a different personality, a different way of working, a different community. But the common thing is we're going to provide forums where if you have a shared interest in TensorFlow in a particular area, we can focus on it. Now I'd like to talk about the design of TensorFlow. You know, one of the most amazing things and the benefits of TensorFlow is that the code that we release is the code that Google uses on a daily basis. It's kind of remarkable for an open source project. And so we're really careful about changes. We're really careful about design. We have a commitment, obviously, to the API through the 1.x series release. And we have design reviews internally. So when things change and we have proposals, we get feedback. But by now you're thinking, well, you just said that so many use cases and so many users are outside of Google, yet you're having these design reviews inside. So what we're going to do is open up a public feedback phase to our design process so we can engage much more broadly with every contributor, every user about how that might affect their needs and what their opinions are. Keep an eye on the developers at TensorFlow.org mailing list for this, because that's where we'll notify it coming online in the next couple of months. And my hope that this process will also be a way that everybody can communicate and discuss in a known process about the future direction of TensorFlow, whether you're in the core team here at Google or in the broader community. So contributing to TensorFlow isn't just about issues or PR requests. In fact, I reckon that there's so much more, probably more energy going into people who are blogging, running meetups, doing presentations, teaching, doing courses in so many universities around the world. And we want to amp up and support the amount of content that educates and highlights TensorFlow. And so we're really excited already that so many of you do such amazing jobs, and we'd like to be able to point everybody in the TensorFlow community to the work that you're doing. So there's a couple of things that we launched to support this. The first, you probably already heard, we now have a blog for TensorFlow, blog.tensorflow.org. One of the things that I'm most excited about with this blog is that as well as important announcements and education that we can put out, we're setting it up from the beginning to involve content from around the web and in the community. That's one reason we're using the Medium platform for this, to make it easy for us to integrate content from around the web and still give you the credit for the work you've done. So we'd really like to hear from you. If you have a blog post, an article you want to get into the TensorFlow publication, get in touch. Secondly, and if you're on the live stream watching us, you've kind of found out about this, we have a YouTube channel that's launched today. Now, one of the things I'm most excited about in this is a show called TensorFlow Meets. This is where we're able to get out into the world of contributors and users and really highlight some of the use cases, highlight the work of everybody. Again, this is a chance for you too. We'd love to meet you. We'd love to chat with you about what you're up to and have you featured on the YouTube channel. Again, reach out to us. We'd love you to be a part of it. There is one URL to get involved in all these things that I mentioned, tensorflow.org/community. So if anyone's mentioned a mailing list or a group or something to you about that today, please go to that URL and you find the resources there. It is my hope that TensorFlow is going to continue to be a party, but maybe one you can find yourself part of a lot sooner and have more fun. Please feel free to reach out to me. There's my email address, ewj@google.com, and talk to me about anything to do with your experiences in collaborating around open source and TensorFlow. I'd love to hear about it. Thank you so much. Now, our next speaker is Chris Lattner. He's going to talk to you about a first principles approach to machine learning.
All right. Thank you, Ed. Hi there, everyone. I'm excited to introduce a new project that we've been working on that takes a new project to improve usability of TensorFlow. And we care so much about usability here that we're going all the way back to first principles of the computation that we're performing. But first, why usability? I hope that everyone here agrees that productivity in machine learning is critical because it leads to a faster pace of innovation and progress in our field. And of course, we just want to build beautiful things for TensorFlow users, and so that's a big piece of it as well. But if you look at machine learning frameworks, there's two major approaches. The most familiar are the graph building approaches, where you explicitly define a graph and then execute it to run your computation. This is great for performance, but isn't always the best for usability. In contrast, the defined by run approaches like eager execution aren't always the best for performance, but they allow you to use language control flow and other things that make them a lot easier to use. The interesting thing about both of these approaches is that they're really about allowing Python to understand the difference between the tensor computation in your code and all the other non-tensor stuff like command line option processing and visualization and the other things that you do. And so I think it's interesting to look at how these actually work. In the case of eager execution, for example, you write your model, and Python starts out by parsing it, and then it feeds every statement at a time to the interpreter. And if it's a tensor operation, it fires up TensorFlow and hands it off, and TensorFlow takes care of your tensor operations. Otherwise, the Python interpreter runs it. Now, the key thing about eager execution and graph building is that they're designed within the constraints of what you can do as a Python library. Now, if you crack open the compiler and look at it from what could we do with the compiler and language involved, there's a whole other set of approaches that can be applied to solving this particular problem. And that's what we're doing. The cool thing about a compiler is that after you parse your code, the compiler can see the entire program and all the tensor ops in it. And so what we're doing is we're going to add a new stage to the compiler that automatically takes these tensor operations out of your program, builds a standard TensorFlow graph for you, and then hands it to TensorFlow. And because it's a standard TensorFlow graph, you get full access to all the things that TensorFlow can do, including all the devices. Now, we think that this approach is a really great combination because you get all the power and flexibility of TensorFlow, but you also get the usability of eager execution as well. But there's a catch. There's always a catch, right? The catch here is that we can't do this with Python, at least not with the reliability we expect, because it doesn't support the kind of compiler analysis we need. And what do we mean by that? Well, the compiler has to be able to reason about values as they flow through your program, has to reason about control flow and function calls, has to reason about variable aliasing and other things like that. And if we can't directly use Python, then as users, of course, we care a lot about all the nice things we've come to love about Python, including the ability to use all the standard Python APIs. So I know what you're thinking. Does this mean that we're talking about doing a new language? Well, that's definitely an approach to solve the technical requirements we want. And if we do a new language, we can obviously build all the nice things we want into it. But this comes at a cost, because it turns out that we'd be foregoing the benefits of having a community. And that includes things like tools and libraries, but also things like books, which some people still use. And even more significantly, this would take years of time to get right. And machine learning just moves too fast. No, we think it's better to use an existing language. But here we have to be careful, because to do this right, we have to make significant improvements to the compiler and the language, and we need to be able to do this in a reasonable amount of time. And so, of course, this brings us to the Swift programming language. Now, I assume that most of you are not very familiar with Swift, so I'll give you a quick introduction. Swift is designed with a lightweight syntax, and it's really geared towards being easy to use and learn. Swift draws together best practices from lots of different places, including things like functional programming and generics. Swift builds on LLVM, which means that, of course, it has an interpreter, and it has scripting capabilities as well. Swift is great in notebook environments, and these are really awesome when you're interactively developing in real time. Swift is also open source. It's portable to lots of platforms, and has a big community of people. But the number one thing that's most important to us is it has an fully open design environment called Swift Evolution, which allows us to propose first-class machine learning language and compiler features directly for integration into Swift. And if you bring all of this together that we've been talking about here, I'm happy to introduce Swift for TensorFlow. Swift for TensorFlow gives you the full performance of graphs. You can use native language control flow, has built-in support for automatic differentiation. It can detect errors in your code without even running it, and has full access to Python APIs. But instead of telling you about it, I'd like to invite up Richard Way to show it to you now.
Thank you, Chris. I'm thrilled to show you Swift for TensorFlow. Swift is a high-performance modern programming language. And today, for the very first time, Swift has a full-power TensorFlow built right in. I'm going to walk through 3 major styles of programming: scripting, interpreting, and notebooks. So first, let me show you the Swift interpreter. This is a Swift interpreter. When I type some code, Swift evaluates it and prints the result, just like Python. Now let's import TensorFlow. I can create a tensor from some scalars. Now, I can do any TensorFlow operation directly and see the result, just like I would with eager execution. For example, A plus A, or A's matrix product with itself. Of course, loops just work. I can print the result of A. Now, interpreters are a lot of fun to work with, but I like using TensorFlow in a more interactive environment, just like Jupyter Notebook. So let's see how they work. This is a Swift notebook. It shows all the results on the right. So here's some more interesting code. Fun with functions. So here I have a sigmoid function inside a loop. Now, as I click on this button, it shows a trace of all values produced by this function over time. Now, as a machine learning developer, I often like to differentiate functions. Now, when I type in, well, since we were able to improve the programming language, we built first-class automatic differentiation right into Swift. Now, when I type in gradient of x, it shows the gradient. Swift computes the gradient automatically and gives me the result. So here's the gradient of sigmoid. Now, let's look at some Python code. Let's think about Python. Well, as a machine learning developer, I've been using Python a lot, and I know there are many great Python libraries. Just today, my colleague Dan sent me a data set in Pickle format. Well, I can directly use Python APIs to load it. All I have to do is to type in import Python. And Swift uses the Python API, Pickle, to be specific, to load the data. And here, you can see the data right in the Swift notebook. Now, so here's the Swift notebook. Now, some people like to run training scripts directly in command line. So let me show you how to train a simple model from in command line. So here is a simple MNIST model. In this model, I'm using TensorFlow's dataset API to load training data. As I scroll down, I have the forward pass, backward pass, gradient descent all defined in the training loop. Now, I usually like to work on the go, so this code has been working on the CPU on my laptop. But when I want to get more performance, what do? Well, why don't I just enable Cloud TPU? So all I have to do is add one line to enable TPU execution. When I save this file, open a terminal to run this training script. It's initializing TPU, And the Swift compiler automatically partitions this program into a normal Swift program and a TensorFlow graph. And TensorFlow is sending this graph to the TensorFlow SLA compiler for TPU execution. Now it's running, and we're waiting for the TPU to give the result. Look, the loss is going down. All right. So why don't we simply open TensorBoard and see the training curve? So now I can see the entire training history in TensorBoard. So this is looking great. Now, this is Swift for TensorFlow. It's an interactive programming experience with supercomputing performance at your fingertips. Back to you, Chris.
Richard. Thanks, Richard. All right, to recap quickly, Richard showed you that Swift has an interpreter, and it works just like you'd expect. Now, I know that it's super frustrating to be working on a program, and 2 hours into a training run, you get a shape error or a type mismatch. Swift is designed to catch errors early, and we've started building in support for catching TensorFlow-specific mistakes right into TensorFlow. We showed that you can directly use arbitrary Python APIs and other dynamic languages directly from Swift, which gives you full access to the data science ecosystem and any other Python APIs that you just love to use. Swift is also generating standard TensorFlow graphs, including control flow, which give you the full performance of the session API. And of course, graphs are also awesome because they give you access to everything that TensorFlow can do, including devices spanning the range from the tiniest Raspberry Pi all the way up to a TPU supercomputer. Now, you may be wondering, when do you get this? What does this mean? Well, this is still an early stage project, but I'm happy to say that we're looking forward to our open source release next month. And not only are we releasing the code, we're releasing technical white papers and documents to explain how it works. And we're also moving our design discussions out in the public onto a Google group so that everybody who wants to can participate. Now, we're not done yet. So we have basic support for automatic differentiation built right into the compiler and the language. But we're also really interested in extending it to support exotic cases like recursion and even differentiating custom data structures. Compatibility issues are also super frustrating, particularly if you accidentally use an op or a dtype that's not supported by your device. Swift has great support for detecting availability issues like this, and we're looking forward to wiring this right into support TensorFlow. We're also interested in high-level APIs, but with this, we want to be a little bit cautious. We have some prototypes now, but we'd really like to work with the community and evaluate and iterate and design multiple different approaches and actually experiment with these and then settle on the best one based on real-world experience. Now, this has been a super quick tour of Swift for TensorFlow. Swift for TensorFlow combines the power and flexibility of TensorFlow with a whole new standard for usability. We think it's going to take your productivity and shoot it to the roof. Swift for TensorFlow is also an early stage project, and so we'd really love for you to get interested and help us to build this future. Thank you.
Hello, everyone. Welcome back. Welcome back. I'm Jeremiah, and this is Andrew. We are here from the TensorFlow Hub team. We're based in Zurich, Switzerland, and we're excited to share TensorFlow Hub today. So this first slide is actually one that I stole. I took it from a colleague, Noah Fidel, who leads TensorFlow Serving. And Noah uses this slide to tell a personal story. And it kind of shows the growth of things, the type of tools that we use to do software engineering. And it shows how they mature over time. And he also connects this to a similar thing happening for the tools we use to do machine learning. Right? And he draws these connections. Right? We're rediscovering things as we grow our machine learning tools. Things like the machine learning equivalent of source control, the machine learning equivalent of continuous integration. And Noah also makes this really interesting observation that this growth on the machine learning side is lagging behind the software engineering side by 15, 20 years. So this creates a really interesting opportunity, right? We can look at software engineering. We can look at some of the things that have happened there and think about what kind of impact they may have on machine learning. Right? And so looking at software engineering, there's something that's so fundamental, it's almost easy to skip over. And that's this idea of sharing code, shared repositories. Right? On the surface, this makes us immediately more productive. Right? We can search for code, we can download it, we can use it. But it has these really powerful second-order effects. Right? This actually changes the way we write code. Right? We refactor our code, we put it in libraries, we share those libraries, and this really makes people even more productive. And it's the same dynamic that we want to create for machine learning with TensorFlow Hub. TensorFlow Hub lets you build, share, and use pieces of machine learning. So why is this important? Well, anyone who's done machine learning from scratch knows you need a lot to do it well. You need an algorithm. You need data. You need compute power and expertise. And if you're missing any of these, you're out of luck. So TensorFlow Hub lets you distill all these things down into a reusable package we call a module. Those modules go in TensorFlow Hub where people can discover them and then easily use them. So you'll notice that I'm saying module instead of model. It turns out that a model is a little bit too big to really encourage sharing. Right? If you have a model, you can use that model if you have the exact inputs it wants, and you expect the exact outputs it provides. If there's any little differences, you're kind of out of luck. So modules are a smaller piece. Right? If you think of a model like a binary, think of a module like a library. So on the inside, a module is actually a saved model. So this lets us package up the algorithm in the form of a graph. Lets us package up the weights. You can do things like initialize, use assets. And our libraries make it very easy to instantiate these in your TensorFlow code. So you can compose these in interesting ways. This makes things very reusable. You can produce one of these and share it. These are also retrainable. Once you patch it in to your bigger program, you can backpropagate through it just like normal. And this is really powerful because if you do happen to have enough data, you can customize the TF Hub module for your own application. And to tell us a little bit more about some of those applications, I'll hand it over to Andrew.
Thanks, Jeremiah. Let's look at a specific example of using a TF Hub module for image retraining. Let's say that we're going to make an app that can classify rabbit breeds from photos. The problem is we only have a couple hundred examples, probably not enough to train an entire image classification model from scratch. But what we could do is start from an existing general purpose image classification model. Most of the high-performing ones these days are trained on millions of examples, and they can easily classify thousands of categories. So we want to reuse the architecture and the trained weights of that model without the classification layers. And in that way, we can add our own rabbit classifier on top, and we can train it on our own rabbit examples, and keep the reused weights fixed. So since we're using TensorFlow Hub, our first stop is tensorflow.org/hub, where we can find a list of all of the newly released, state-of-the-art, and also the well-known image modules. Some of them include the classification layers, and some of them remove them, just providing a feature vector as output. And so we'll choose one of the feature vector ones for this case. Let's use NASNet, which is a state-of-the-art image module that was created by a neural architecture search. So you just paste the URL of a module, and TensorFlow Hub takes care of downloading the graph and all of its weights and importing it into your model. And in that one line, you're ready to use the module like any function. So here we just provide a batch of inputs, and we get back our feature vectors, we add a classification layer on top, and we output our predictions. But in that one line, you get a huge amount of value. In this particular case, more than 62,000 hours of GPU time went into finding the best architecture for NASNet and training the result. And then all of the expertise, the research, the testing that the authors put into that, that's all built into the module. Plus, that module can be fine-tuned with your model. So if you have enough examples, you can potentially get better performance if you use a low learning rate, if you set the trainable parameter to true, and if you use the training version of the graph. So NASNet is available in a large size as well as a mobile size module. And then there's also the new progressive NASNet. And then a number of new MobileNet modules for doing on-device image classification, as well as some industry standard ones like Inception and ResNet. That complete list is at tensorflow.org/hub. And of course, all those modules are pre-trained using the TF-SLIM checkpoints, and they're ready to be used for classification or as feature vector inputs to your own model. OK, let's look at another example, in this case, doing a little bit of text classification. So we'd like to know whether a restaurant review is a positive or negative sentiment. So as Jeremiah mentioned, one of the great things about TensorFlow Hub is that it packages the graph with the data. For our text embedding modules, that means that all of the pre-processing is included, doing things like normalizing and tokenizing operations. So we can use a pre-trained sentence embedding module to map a full sentence to an embedding vector. So if we want to classify some restaurant reviews, then we just take one of those sentence embedding modules, we add our own classification layer on top, and then we train with our reviews while we keep the sentence module's weights fixed. And just like for the image modules, tensorflow.org/hub lists a number of different text modules. We have neural network language models that are trained on GNews for English, Japanese, German, and Spanish. We also have Word2Vec models trained on Wikipedia, as well as a new module called Elmo that models the characteristics of word use and how those uses vary across context. And then there's also something really new, as in today. You may have seen a new paper this morning from Ray Kurzweil's team. This is the Universal Sentence Encoder. It's a sentence-level embedding module. It's trained on a variety of tasks, and it enables a variety of tasks, in other words, universal. So some of the things that it's good for are semantic similarity, doing custom text classification, clustering, and semantic search. But the best part about it is how little training data is actually required to adapt a module to your own problem. So that sounds great in our particular case. Let's try it on the restaurant review task. So we just paste that URL from the paper, and like before, TensorFlow Hub downloads the module and inserts it into your graph. But this time, we're using the text embedding column. That way, we can feed it into an estimator to do the classification part. And just like with the image retraining example, this module can be fine-tuned with your model by setting trainable to true. Of course, you have to lower the learning rate so that you don't ruin the existing weights that are in there, but it's something that's worth exploring if you have enough data. Now let's take a closer look at that URL. As Jeremiah mentioned, a module is a program. So make sure what you're executing is from a location that you trust. In this case, the module is from tfhub.dev. So that's our new source for Google-provided modules like NASNet and a universal sentence encoder. Over time, we would like to create a place where you can also publish the modules that you create. So in this case, Google is the publisher, and universal sentence encoder is the name of the module. And finally, the version number is 1. So TensorFlow Hub considers modules to be immutable. That way you don't have to worry about the weights changing between training sessions. So that module URL and all of the module URLs on tfhub.dev include a version number. And you can take that URL and paste it into your browser and see the complete documentation for any module that's hosted on tfhub.dev. Here's the particular one for the universal sentence encoder. And then we also have modules for other domains besides text classification and image retraining, like a generative image module that contains a progressive GAN that was trained on Celeb A. And we added another module that was based on Deep Local Features Network, which can identify the key points of landmark images. Both of those have great Colab notebooks that are available on tensorflow.org/hub. In fact, the images here were created from them. And we're going to be adding more modules over time for tasks like audio and video over the next few months. But most importantly, we're really excited to see what you build with TensorFlow Hub. Use the hashtag TFHub when you build notebooks and share modules. And visit tensorflow.org/hub for links to our documentation, including examples with tutorials, interactive notebooks, and code labs, and our new discussion mailing list. So from Jeremiah, me, and everyone on our team in Zurich, I want to thank you so much. Okay, and next up, Clemens and Raz will tell you about TensorFlow Extended.
Thank you. Hello, everyone. First, thanks everyone for coming to the TensorFlow Dev Summit. And second, thanks for staying around this long. I know it's been a very long day, and there's been a lot of information that we've been throwing at you, but we've got much, much more and many more announcements to come. So please stick with me. So my name is Clemens, and this is Raz, and we're going to talk about TensorFlow Extended today. But before we do this, I'm going to do a quick survey. And can I get a quick show of hands? How many of you do machine learning in a research or academic setting? OK, quite a big number. And how many of you do machine learning in a production setting? OK, that looks about half-half, obviously also a lot of overlap. So for those of you who do machine learning in a production setting, how many of you agree with this statement? Yeah, some, OK. I see a lot of hands coming up. So everyone that I speak with who's doing machine learning in production agrees with this statement. Doing machine learning in production is hard, and it's too hard. Because after all, we actually want to democratize machine learning and get more and more people to allow them to deploy machine learning in their products. One of the main reasons why it's still hard is because in addition to the actual machine learning, so this small orange box where you actually use TensorFlow, where you may use Keras to put together your layers and train your model, you need to worry about so much more. There's all of these other things that you have to worry about to actually deploy machine learning in a production setting and serve it within your product. Now, the good news is that this is exactly what TensorFlow Extended is about. TFX, internally at Google, is an end-to-end machine learning platform that allows our developers to go all the way from data to a production serving machine learning models as fast as possible. Now, before we introduced TFX, we saw that going through this process of writing some of these components, some of them didn't exist before, gluing them together, and actually getting to a launch took anywhere between 6 and 9 months, sometimes even a year. Once we deployed TFX and allowed developers to use it, in many cases, people can use this platform and get up and running with it in a day, and actually get to a deployable model in production on the order of weeks or in just a month. Now, TFX is a very large system and platform that consists of a lot of components and a lot of services. So unfortunately, I can't talk about all of this in the next 25 minutes. So we're only going to be able to cover a small part of it, but we're talking about the things that we've already open sourced and made available to you. So first, we're going to talk about TensorFlow Transform and show you how to apply transformations on your data consistently between training and serving. Next, Raz is going to introduce you to a new product that we're open sourcing called TensorFlow Model Analysis. We're going to give a demo of how all of this works together end to end, and then make a broader announcement of our plans for TensorFlow Extended and sharing it with the community. So let's jump into TensorFlow Transform first. So a typical ML pipeline that you may see in the wild is during training, you usually have a distributed data pipeline that applies transformations to your data. Because usually you train on a large amount of data, this needs to be distributed. And you run this pipeline and sometimes materialize the output before you actually put it into your trainer. Now at serving time, you need to find a way to somehow replay those exact transformations online as a new request comes in and needs to be sent to your model. Now, there's a couple of challenges with this. The first one is, usually those two things are very different code paths, right? The data distribution systems that you would use for batch processing are very different from the libraries and tools that you would use to, in real time, transform data to make a request to your model, right? So now you have two different code paths. Second, in many cases, it's very hard to keep those two in sync. And I'm sure a lot of you have seen this. You change your batch processing pipeline and introduce a new feature or change how it behaves. And you somehow need to make sure that the code that you actually use in your production system is changed at the same time and is kept in sync. And the third problem is sometimes you actually want to deploy your TensorFlow or machine learning model in many different environments. So you want to deploy it on a mobile device, you want to deploy it on a server, maybe you want to put it on a car. Now suddenly you have 3 different environments where you have to apply these transformations, and maybe there's different languages that you use for those. And it's also very hard to keep those in sync. And this introduces something that we call training serving skew, where the transformations that you do at training time may be different from the ones in serving time, which usually leads to bad quality of your serving model. TensorFlow Transform addresses this by helping you write your data processing job at training time. So we actually help you create those data pipelines to do those transformations. And at the same time, it emits a TensorFlow graph that can be inlined with your training model and also your serving model. Now what this does is it actually hermetically seals the model. And your model takes a raw data request as input, and all of the transformations are actually happening within the TensorFlow graph. Now this has a lot of advantages. One of them is that you no longer have any code in your serving environment that does these transformations, because they're all being done in the TensorFlow graph. Another one is wherever you deploy this TensorFlow model, all of those transformations are applied in a consistent way, no matter where this graph is being evaluated. So let's see how that looks like. So this is a code snippet of a pre-processing function that you would write with TF Transform. And I'm just going to walk you through what happens here and what we need to do for this. So the first thing we do is normalize this feature. And as all of you know, in order to mean normalize a feature, we need to compute the mean and the standard deviation. And to actually apply this transformation, we need to subtract by the mean and divide by the standard deviation. So what has to happen is, for the input feature x, we have to compute these statistics, which is a trivial task if the data fits into a single machine. You can do that easily. It's a non-trivial task if you have a gigantic training data set and actually have to compute these metrics effectively. Once we have these metrics, we can actually apply this transformation to the feature. This is to show you that the output of this transformation can then be, again, multiplied with another tensor, which is just a regular TensorFlow transformation. And then in order to bucketize a feature, you also, again, need to compute the bucket boundaries to actually apply this transformation. And again, this is a distributed data job to compute those metrics for the result of an already transformed feature. This is another benefit, to then actually apply this transformation. The next two examples just show you that in the same function, you can apply any other tensor in, tensor out function. And there's also some of what we call mappers in TF transform that don't require this analyze phase. So n-grams doesn't require us to actually run a data pipeline to compute anything. Now what happens here is that these orange boxes is what we call analyzers. We realize those as actual data pipelines that compute those metrics over your data. They're implemented using Apache Beam, and we're going to talk about this more later. But what this allows us to do is actually run this distributed data pipeline in different environments. So there's different runners for Apache Beam. And all of the transforms are just simple instance-to-instance transformations using pure TensorFlow code. And what happens when you run TensorFlow transform is that we actually run these analyze phases, compute the results of those analyze phases, and then inject the result as a constant in the TensorFlow graph. So this is on the right. And then this graph is a hermetic TensorFlow graph that applies all of the transformations. And it can be inlined in your serving graph. So now your serving graph has the transform graph as part of it and can play through all of these transforms wherever you want to deploy this TensorFlow model. So what can be done with TensorFlow transform? At training time for the batch processing, really anything that you can do with a distributed data pipeline. So there's a lot of flexibility here, what types of statistics you can compute. We provide a lot of utility functions for you, but you can also write custom data pipelines. And at serving time, because we generate a TensorFlow graph that applies these transformations, we're limited to what you can do with the TensorFlow graph. But for all of you who know TensorFlow, there's a lot of flexibility in there as well. So anything that you can do in a TensorFlow graph, you can do with TF transform for your transformations. So some of the common use cases that we've seen, the ones on the left I just spoke about, you can scale a continuous value to the z-score, which is mean normalization, or to a value between 0 and 1. You can bucketize a continuous value. If you have text features, you can apply a bag of words or n-grams. Or for feature crosses, you can actually cross those strings and then generate vocabs of the result of those crosses. And as mentioned before, TF transform is extremely powerful in actually being able to chain together these transforms. So you can apply a transform on the result of a transform, and so on. And another particularly interesting transform is actually applying another TensorFlow model. So you've heard about the saved model before. If you have a saved model that you can apply as a transformation, you can use this in TF transform. Let's say you have an image and you want to apply an inception model as a transform and then use the output of that inception model maybe to combine it with some other feature or use it as an input feature to your model. You can use any other TensorFlow model that ends up being inlined in your transform graph and also inlined in your serving graph. So all of this is available today, and you can go check it out on GitHub at TensorFlow/transform. And with this, I'm going to hand it over to Ross, who's going to talk about TensorFlow model analysis.
All right, thanks, Clemens. Hi, everyone. I'm really excited to talk about TensorFlow model analysis today. We're going to talk a little bit about metrics. Let's see, next slide. All right, so we can already get metrics today, right? We use TensorBoard. TensorBoard's awesome. You saw an earlier presentation today about TensorBoard. It's a great tool. While you're training, you can watch your metrics, right? And if your training isn't going well, you can save yourself a couple of hours of your life, right? Terminate the training, fix some things. But let's say you have your trained model already. Are we done with metrics? Is that it? Is there any more to be said about metrics after we're done training? Well, of course there is, right? We want to know how well our trained model actually does for our target population, right? And I would argue that we want to do this in a distributed fashion over the entire data set. Now, why wouldn't we just sample? Why wouldn't we just save more hours of our lives, right, and just sample, make things fast and easy, right? Well, let's say you start with a large data set, okay? Now you're going to slice that data set. You're going to say, I'm going to look at people at noontime, right? That's a feature. From Chicago, my hometown, okay? Running on this particular device. Well, each of these slices reduce the size of your evaluation data set by a factor, right? This is an exponential decline. By the time you're looking at the experience for a particular set of users, you're not left with very much data, right? And the error bars on your performance measures, they're huge. I mean, how do you know that the noise doesn't exceed your signal by that point, right? So really, you want to start with your larger data set before you start slicing. All right, so let's talk about a particular metric. I'm not sure if, who's heard of the ROC curve? It's kind of an unknown thing in machine learning these days. Okay. So we have our ROC curve, and I'm going to talk about a concept that you may or may not be familiar with, which is ML fairness. Okay, so what is fairness? Fairness is a complicated topic. Fairness is basically how well does our machine learning model do for different segments of our population, okay? So you don't just have one ROC curve. You have an ROC curve for every segment. You have an ROC curve for every group of users. Who here would run their business based on their top-line metrics? No one, right? That's crazy. You have to slice your metrics. You have to go in and dive in and find out how things are going. So that lucky user, that black curve on the top, great experience. That unlucky user, the blue curve, not such a great experience, right? So when can our models be unfair to various users? Okay. Well, one instance is if you simply don't have a lot of data from which to draw your inferences, right? So we use stochastic optimizers, and if we retrain the model, it does something different every time, slightly, right? And you're going to get high variance for some users just because you don't have a lot of data there. We may be incorporating data from multiple data sources. Some data sources are more biased than others, right? And so some users just get the short end of the deal, right? Whereas other users get the ideal experience. Our labels could be wrong, right? All of these things can happen. And here's TensorFlow model analysis. You're looking here at the UI hosted within a Jupyter notebook. On the x-axis, we have our loss. And you can see there's some natural variance in the metrics. We're not always going to get spot on the same precision and recall for every segment of population. But sometimes you'll see, what about those guys at the top there experiencing the highest amount of loss? Do they have something in common? We want to know this. Sometimes our users that are most that get the poorest experience, they're sometimes our most vocal users, right? We all know this. I'd like to invite you to come visit mlfairness.com. There's a deep literature about the mathematical side of ML fairness. Once you've figured out how to measure fairness, there's a deep literature about what to do about it. How does TensorFlow model analysis actually give you, these sliced metrics? How do you go about getting these metrics? Well, today you export a saved model for serving, right? This is kind of a familiar thing. TensorFlow model analysis is simple. It's similar. You export a saved model for evaluation. Why are these models different? Why export two? Well, the eval graph that we serialize as a saved model has some additional annotations that allow our evaluation batch job to find the features, to find the prediction, to find the label. And we don't want those things, mixed in with our serving graph. So you export a second one. So this is the GitHub. We just opened it, I think, last night at 4:30 p.m. Check it out. We've been using it internally for quite some time now. Now it's available externally as well. The GitHub has an example that kind of puts it all together so that you can try all these components that we're talking about from your local machine. You don't have to get an account anywhere. You just git clone and run the scripts and run the code lab. This is the Chicago taxi example. So we're using public data from publicly available data to determine which riders will tip their driver and which riders, shall we say, don't have enough money to tip today, right? what does fairness mean in this context, right? So our model is going to make some predictions. We may want to slice these predictions by time of day, right? So during rush hour, we're going to have a lot of data. So hopefully our model is going to be fair if that data is not biased, right? At the very least, it's not going to have a lot of variance. But how is it going to do at 4 a.m. in the morning, right? Maybe not so well. How's it going to do when the bars close? An interesting question. I don't know yet, but I challenge you to find out. All right, so this is what you can run using your local scripts. We start with our raw data. We run the TF transform. The TF transform emits a transform function and our transformed examples. We train our model. Our model, again, emits 2 save models, as we talked about, one for serving and one for eval. You can try this all locally, just like run scripts and play with this stuff. Clemens talked a little bit about transform. So here we see that we want to take our dense features and we want to scale them to a particular z-score. And we don't want to do that batch by batch, right? Because the mean for each batch is going to differ and there's going to be fluctuations. We may want to do that across the entire data set. We may want to like normalize these things across the entire data set. We build a vocabulary, we bucket for the wide part of our model, and we emit our transform function, and into the trainer we go, right? You heard earlier today about TF estimators, and here is a wide and deep estimator that takes our transformed features and emits 2 saved models. And now we're in TensorFlow model analysis, which reads in the saved model and runs it against all of the raw data. You call render slicing metrics from the Jupyter Notebook, and you see the UI. And the thing to notice here is that this UI is immersive, right? It's not just a static picture that you can look at and go, huh, and then walk away from, right? It lets you see your errors broken down by bucket or broken down by feature, and it lets you drill in and ask questions and be curious about how your models are actually treating various subsets of your population. Those subsets may be the lucrative subsets, right? You really want to drill in. And then you want to serve your model. So our demo, our example, has a one-liner here that you can run to serve your model. And make a client request. The thing to notice here is that we're making a gRPC request to that server. We're taking our feature tensors, we're serializing them into the gRPC request, sending them to the server, and back comes, a probability, right? But that's not quite enough, right? We've heard a little bit of feedback about the server, and the thing that we've heard is that gRPC is cool, but REST is really cool. All right, so I tried. So this is actually one of the top feature requests on GitHub for model serving. You can now pack your tensors into a JSON object, send that JSON object to the server, and get a response back via HTTP. Much more convenient. And I'm very excited to say that it will be released very soon. Very soon. All right. I see the excitement out there. Back to the end-to-end. So you can try all of these pieces end-to-end all on your local machine because they're using Apache Beam direct runners. And direct runners allow you to take your distributed job and to run them all locally. Now, if you swap in Apache Beam's Dataflow runner, you can now run against the entire data set in the cloud. And so the example also shows you how to run the big job against the cloud version as well. We're currently working with the community to develop a runner for Apache Flink, a runner for Spark. Stay tuned to the TensorFlow blog and to our GitHub. And you can find the example at TensorFlow/model-analysis. And back to Clemens.
Thank you, Ross. All right, So we've heard about transform. We've heard how to train models, how to use model analysis, and how to serve them. But I hear you say you want more, right? Is that enough? You want more? All right, you want more. And I can think of why you want more. Maybe you read the paper we published last year and presented at KDD about TensorFlow Extended. And in this paper, we laid out this broad vision of how this platform works within Google and all of the features that it has and all of the impact that we have by using it. And it had figure 1, which had all of these boxes and described what TensorFlow Extended actually is. And although overly simplified, this is still much more than we discussed today, right? So today, we spoke about these 4 components of TensorFlow Extended. Now, it's important to highlight that this is not yet an end-to-end machine learning platform, right? This is just a very small piece of TFX. These are the libraries that we've open sourced for you to use, but we haven't yet released the entire platform. And we're working very hard on this because we've seen the profound impact that it had internally, how people could start using this platform and deploying machine learning in production using TFX. And we're working very hard to actually make more of these components available to you. So in the next phase, we're actually looking into our data components and looking to make those available to you so that you can analyze your data, visualize the distributions, and detect anomalies, because that's an important part of any machine learning pipeline, to detect changes and shifts in your data and anomalies. After this, we're actually looking into some of the horizontal pieces that help tie all of these components together, because if they're only single libraries, you still have to glue them together yourself, right? You still have to use them individually. They have well-defined interfaces, but you still have to combine them by yourself. So internally, we have a shared configuration framework that allows you to configure the entire pipeline, and a nice integrated front end that allows you to monitor the status of these pipelines and see progress and inspect the different artifacts that are being produced by all of the components. So this is something that we're also looking to release later this year. And I think you get the idea. Eventually, we want to make all of this available to the community, because internally, hundreds of teams use this to improve our products. We really believe that this will be as transformative to the community as it is at Google. And we're working very hard to release more of these technologies and the entire platform to see what you can do with them for your products and for your companies. So keep watching the TensorFlow blog post for a more detailed announcement about TFX and our future plans. And as mentioned, you can already use some of these components today. Transform is released. Model analysis was just released yesterday. Serving is also released. And the end-to-end example is available under this short link, and you can find it on the model analysis repo. So with this, thank you from both myself and Raz. And I'm going to ask you to join me in welcoming a special external guest, Patrick Brandt, who's joining us from Coca-Cola, who's going to talk about applied AI at Coca-Cola. Thank you.
Hey, great job. Thanks, Clemens. All right. So yes, I'm Patrick. I'm a solution strategist from Coca-Cola. Today I'm going to share with you how we're using TensorFlow to support some of our largest, most popular digital marketing programs in North America. So we're going to take the TensorFlow Dev Summit off to a marketing tangent for a minute before we come back. All right, so as background, what is proof of purchase and what is its relationship to marketing? As an example, back in the day, folks could clip the barcodes off their cereal boxes and then mail these barcodes back into the cereal company to receive a reward, some kind of coupon or prize back through the mail. And this is basic loyalty marketing. Brands, in this case the cereal company, rewarding consumers through purchase, and at the same time opening up a line of communication between the brand and the consumer. Now, over the last 15 some odd years of marketing digitalization, this concept has evolved into digital engagement marketing, rewarding consumers in the moment in real time through web and mobile channels. But often proof of purchase is still an important component of that experience. We have a very active digital engagement marketing program at Coca-Cola. Through proof of purchase, our consumers can earn a magazine subscription or the chance to win a cruise or a vintage vending machine. And this is what proof of purchase looks like at Coke. Underneath our bottle caps and inside those cardboard fridge packs that you can buy at the grocery store. We printed these 14-character product pin codes. And these are unique to every product, and these are what our consumers enter into our promotions. Now, you can enter these in by hand, but on your mobile device, you can scan them. And this had been the holy grail of marketing IT at Coke for a long time. We looked at both commercial and open source optical character recognition software, OCR, but it could never read these codes very well. And the problem has to do with the fidelity of the codes. So these are 4x7 dot matrix printed. The printer head is about an inch off the surface of the cap and fridge pack, and these things are flying underneath that printer head at a very rapid rate. So this creates a lot of visual artifacts, things like character skew and pixel drift, things that normal OCR can't handle very well. So we knew that if we wanted to unlock this experience for our consumers, we were going to have to build something from scratch. And when I look at these codes, a couple of characteristics jump out at me. We're using a small alphabet, let's say 10 characters. And there's a decent amount of variability in the presentation of these characters. This reminds me of MNIST, the online database of 60,000 handwritten digit images. Convolutional neural networks, or ConvNets, are particularly good at extracting the text from these images. So I'm probably going to tell you all something you already know, but here we go. ConvNets work by taking an image and initially breaking it down into many smaller pieces, and then detecting very granular features within these pieces, things like edges and textures and colors. And these very granular feature activations are pooled up, often, into a more general feature layer, and then that's filtered, and those activations are pulled up, and so on, until the output of the neural net is run through a softmax function, which creates a probability distribution of the likelihood that a set of objects exists within the image. But ConvNets have a really nice property in that they handle the translation invariant nature of images very well. So that means, from our perspective, they can handle the tilt and twist of a bottle cap held in someone's hand. It's perfect. So this is what we're going to use. We're going to move forward. So now we need to build our platform, and that begins with training, the beating heart of any applied AI solution. And we knew that we needed high-quality images with accurate labels of the codes within those images, and we likely needed a lot of them. So we started by generating a synthetic data set of randomly generated strings that were superimposed over blank bottle cap images, which were then in turn superimposed over random backgrounds. And this gave us a base for transfer learning in the future once we created a real-world data set. And we did that by doing a production run of caps and fridge packs at our printing facilities and then distributing those to multiple third-party suppliers, along with some custom tools that we created to allow them to scan a cap and then label it with the PIN code. But a really important component to this process was an existing PIN code validation service that we've had in production for a long time to support our programs. So anytime a trainer labeled an image, we would send that label to our validation service, and if it was a valid PIN code, we knew we had an accurate label. All right, so this gets our model trained, and now we need to release it to the wild. And we had some pretty aggressive performance requirements. We wanted 1 second average processing time. We wanted 95% accuracy at launch. But we also wanted to host the model remotely for the web and embed it natively on mobile devices to support mobile apps. So this means that our model has to be small enough to support over-the-air updates as the model improves over time. And to help us improve that model over time, we created an active learning UI, a user interface, that allows our consumers to train the model once it's in production. And that's what this looks like. So if I, as a consumer, scan a cap, and the model cannot infer a valid PIN code, it sends down to the UI a per-character confidence of every character at every position. And this can be used to render a screen much like what you see here. So I, as a user, am only directed to address those particularly low confidence characters. I see a couple of red characters there. I tap them. It brings up a keyboard. I correct them. And I'm entered into my promotion. It's a good user experience for me. I scan a code, and I'm only a few taps away from being entered into a promotion. But on the back end, we now have extremely valuable data for training, because we have the image that created the invalid inference to begin with, as well as the user-corrected label that they needed to correct to get into the promotion. So we can throw this into the hopper for future rounds of training to improve the model. All right, when you put it all together, this is what it looks like. The user takes a picture of a cap, the region of interest is found, the image is normalized. It's then sent into our confident model, the output of which is a character probability matrix. This is the per character confidence of every character at every position. That is then further analyzed to create a top 10 prediction. Each one of those predictions are fed into our pin code validation service. The first one that is valid, which is often the first one on the list, is entered into the promotion. And if none of them are valid, our user sees the active learning experience. So our model development effort went through 3 big iterations. Initially, in an effort to keep the model size small up front, our data science team used binarization to normalize the image. But this was too lossy. It didn't produce enough data to create an accurate model. So they switched to best channel conversion, which got the accuracy up. But then the model size grew too large to support over-the-air updates. So at this point, our team starts over. They just completely re-architect the ConvNet using SqueezeNet, which is designed to reduce model size by reducing the number of learnable parameters within the model. But after making this move, we had a problem. We started to experience internal covariant shift, which is the result of reducing the number of learnable parameters. And that means that very small changes to upstream parameter values cascaded to huge gyrations in downstream parameter values. So this slowed our training process considerably, because we had to grind through this covariant shift in order to get the model to converge, if it would converge at all. So to solve this problem, our team introduced batch normalization, which sped up training. It got the model to converge, and now we're exactly where we want to be. We have a 5 megabyte model. It's a 25-fold decrease from where we started, with accuracy greater than 95%. And the results are impressive. These are some screen grabs from a test site that I built. And you can see across the top row how the model handles different types of occlusion. It also handles translation, tilting the cap, rotation, twisting the cap, and camera focus issues. So you can try this out for yourself. I'm going to pitch the newly launched Coca-Cola USA app that hit Android and iPhone app stores a couple of days ago. It does many things, but you can use it to scan a code. You can also go online with your mobile browser to coke.com/rewards and take a picture of a cap to be a code to be entered into a promotion. All right, so some quick shout outs. I can't not mention these folks. Quantify is the data science team that built our image processing pipeline and the pin code recognition model. Digital platform and innovation at Coke, led by Ellen Duncan. She spearheaded this from the marketing side. And then my people in IT. My colleague, Andy Donaldson, shepherded this into production. So thank you. It's been a privilege to speak with you. I covered a lot of ground in 10 short minutes. There was a lot of stuff I didn't talk about. So if you have any questions or any follow-ups, please feel free to reach out to me on Twitter at Patrick Brandt. You can also hit me up on LinkedIn. That short code URL will get you to my profile page. That's wpb.is/LinkedIn. You can also read an article I published last year on this solution. It's on the Google Developers blog. And you can get there at wpb.is/TensorFlow. All right, so thank you. Next up is Alex. And Alex is going to talk to us about applied ML with robotics. Thanks. Good luck.
Okay. Oh, I need the clicker. All right. Hi, everybody. I'm Alex from the Brain Robotics team. And in this presentation, I'll be talking about how we use simulation and domain adaptation in some of our real-world robot learning problems. So first, let me start by introducing robot learning. The goal of robot learning is to use machine learning to learn robotic skills that work in general environments. What we've seen so far is that if you control your environment a lot, you can get robots to do pretty impressive things. And where techniques start to break down is when you try to apply these same techniques to more general environments. And the thinking is that if you use machine learning, then you can learn from your environment, and this can help you address these generalization issues. So as a step in this direction, we've been looking at the problem of robotic grasping. This is a project that we've been working on in collaboration with some people at X. And to explain our problem setup a bit, we're going to have a real robot arm, which is learning to pick up objects out of a bin. there's going to be a camera looking down over the shoulder of the arm into the bin. And from this RGB image, we're going to train a neural network to learn what commands it should send to the robot to successfully pick up objects. Now, we want to try to solve this task using as few assumptions as possible. So importantly, we're not going to give any information about the geometry of what kinds of objects we're trying to pick up. And we're also not going to give any information about the depth of the scene. So in order to solve the task, the model needs to learn hand-eye coordination, or it needs to see where it is within the camera image, and then figure out where in the scene it is, and then combine these two to figure out how it should move around. Now, in order to train this model, we're going to need a lot of data because it's a pretty large-scale image model. And our solution at the time for this was to simply use more robots. So this is what we call the ARM farm. These are 6 robots collecting data in parallel. And if you have 6 robots, you can collect data a lot faster than if you only have 1 robot. So using these robots, we were able to collect over 1 million attempted grasps, over a total of thousands of robot hours. And then using this data, we were able to successfully train models to learn how to pick up objects. Now, this works, but it still took a lot of time to collect this data set. So this motivated looking into ways to reduce the amount of real-world data needed to learn these behaviors. One approach for doing this is simulation. So in the left video here, you can see the images that are going into our model in our real-world setup. And on the right here, you can see our simulated recreation of that setup. Now, the advantage of moving things into simulation is that simulated robots are a lot easier to scale. We've been able to spin up thousands of simulated robots, grasping various objects. And using this setup, we were able to collect millions of grasps in just over 8 hours, instead of the weeks that were required for our original data set. Now, this is good for getting a lot of data, but unfortunately, models trained in simulation tend not to transfer to the actual real-world robot. There are a lot of systematic differences between the two. One big one is the visual appearances of different things, and another big one is just physical differences between our real-world physics and our simulated physics. So what we did was we were able to very quickly train a model in simulation to get to around 90% grasp success. We then deployed to the real robot, and it succeeds just over 20% of the time, which is a very big performance drop. So in order to actually get good performance, you need to do something a bit more clever. So this motivated looking into sim-to-real transfer, which is a set of transfer learning techniques for trying to use simulated data to improve your real-world sample efficiency. Now, there are a few different ways you can do this. One approach for doing this is adding more randomization into your simulator. You can do this by changing around the textures that you apply to different objects, changing around their colors, changing how lighting is interacting with your scene. And you can also play around with changing the geometry of what kinds of objects you're trying to pick up. Another way of doing this is domain adaptation, which is a set of techniques for learning when you have 2 domains of data that have some common structure, but are still somewhat different. In our case, the 2 domains are going to be our simulated robot data and our real robot data. And there are feature-level ways of doing this, and there are pixel-level ways of doing this. Now, in this work, we tried all of these approaches, and in this presentation, I'm going to focus primarily on the domain adaptation side of things. So in feature-level domain adaptation, what we're going to do is we're going to take our simulated data, take our real data, train the same model on both data sets. But then at an intermediate feature layer of the network, we're going to attach a similarity loss. And this similarity loss is going to encourage the distribution of features to be the same across both domains. Now, one approach for doing this, which has worked well recently, is called domain adversarial neural networks. And the way these work is that the similarity loss is implemented as a small neural net that tries to predict the domain based on the input features it's receiving. And then the rest of the model is trying to confuse this domain classifier as much as possible. Now, pixel-level methods work at the problem from a different point of view. Instead of trying to learn domain invariant features, we're going to try to transform our images at the pixel level to look more realistic. So what we do here is we take a generative adversarial network, we feed it an image from our simulator, and then it's going to output an image that looks more realistic. And then we're going to use the output of this generator to train whatever task model that we want to train. Now, we're going to train both the generator and the task model at the same time. We found that in practice, this was useful because it helps ground the generator output to be useful for actually training your downstream task. All right, so taking a step back, feature-level methods can learn domain invariant features when you have data from related domains that aren't quite identical. Meanwhile, pixel-level methods can transform your data to look more like your real-world data. But in practice, they don't work perfectly, and there are still some small artifacts and inaccuracies from the generator output. So our thinking went, why don't we simply combine both of these approaches? We can apply a pixel-level method to try to transform the data as much as possible. And this isn't going to get us all the way there, but then we can attach a feature-level method on top of this to try to close the reality gap even further. And combined, these form what we call the grasp GAN, which is a combination of both pixel-level and feature-level domain adaptation. In the left half of the video here, you can see a simulated grasp. And in the right half, you can see the output of our generator. And you can see that it's learning some pretty cool things in terms of drawing what the tray should look like, drawing more realistic textures on the arm, drawing shadows that the objects are casting. It's also learned how to even draw shadows as the arm is moving around in the scene. And it certainly isn't perfect. There are still these sort of like odd little splotches of color around. But it's definitely learning something about what it means for an image to look more realistic. Now, this is good for getting a lot of pretty images, but what matters for our problem is whether these images are actually useful for reducing the amount of real-world data required. And we find that it does. So to explain this chart a bit, on the x-axis is the number of real-world samples used, and we compared the performance of different methods as we vary the amount of real-world data given to the model. The blue bar is our performance when we use only simulated data. The red bar is our performance when we use only real data. And the orange bar is our performance when we use both simulated and real data and the domain adaptation methods that I've been talking about. And what we found is that when we use just 2% of our original real-world data set, and we apply domain adaptation to it, we're able to get the same level of performance. So this reduces the number of real-world samples we needed by up to 50 times, which is really exciting in terms of not needing to run robots for a long amount of time to learn these grasping behaviors. Additionally, we found that even when we give all of the real-world data to the model, when we give simulated data as well, we're still able to see improved performance. So that implies that we haven't hit the data capacity limits for this grasping problem. And finally, there's a way to train this setup without having real-world labels. And when we trained the model in this setting, we found that we were still able to get pretty good performance on the real-world robot. Now, this was the work of a large team across both Brain as well as X. I'd like to thank all of my collaborators. Here's a link to the original paper. And I believe there is also a blog post if people are interested in hearing more details. Thanks. All right, and lastly, we have Cheryl, who's going to talk to you about art and music with machine learning.
Amazing, just amazing. It's really just in awe of what machine learning is capable of in how we can extend human capabilities. And we want to think more than just about discovering new approaches and new ways of using the technology. We want to see how it's being used and how it impacts the human creative process. So imagine you need to find or compose a drum pattern. You have some idea of a drum beat that you would like to compose. And all you need to do now is go to a website where there's a pre-trained model of drum patterns sitting online. You just need a web browser. You give it some human input, and you can generate a space of expressive variations. You can tune and control the type of outputs that you're getting from this generative model. And if you don't like it, you can continue going through it, exploring this generative space. So this is the type of work that Project Magenta focuses on. To give you a bird's eye view of what Project Magenta is about. It basically is a group of researchers and developers and creative technologists that engage in generative models research. So you'll see this work published, machine learning conferences, you'll see the workshops, you'll see a lot of research contributions from Magenta. You'll also see the code that after it's been published, put into open source repository on GitHub in the Magenta repo. And then from there, we'll see ways of thinking and designing creative tools that can enhance and extend the human expressive creative process. And eventually ending up into the hands of artists and musicians in inventing new ways we can create and inventing new types of artists. So I'm going to give 3 brief overviews of the highlights of some of our recent work. So this is Performance RNN. How many people have seen this? This is one of the demos earlier today. A lot of people have seen and heard of this kind of work. And this is what people typically think of when they're thinking of a generative model. They're thinking, how can we build a computer that has the kind of intuition to know the qualities of things like melody and harmony, but also expressive timing and dynamics. And what's even moreover, it's even more interesting now to be able to explore this for yourself in the browser, enabled by TensorFlow.js. So this is a demo we have running online. We have the ability to tune and control some of the output that we're getting. So in a second, I'm going to show you this video of what that looks like. You would have seen it out on the demo floor, but we'll show you and all of you watching online. And we were also able to bring it even more alive by connecting a baby grand piano Disklavier that is also a MIDI controller, and we have the ability to perform alongside the generative model, reading in the inputs from the human playing the piano. So let's take a look. So this is trained on classical music data from actual live performers. This is from a data set that we got from a piano competition. I don't know if you noticed, this is Nikhil from earlier today. He's actually quite a talented young man. He helped build out the browser version of Performance RNN. And so we're thinking of ways that we take bodies of work, we train a model off of the data, then we create these open source tools that enable new forms of interaction, of creativity, and of expression. And all these points of engagement are enabled by TensorFlow. The next tool I want to talk about that we've been working on is the variational autoencoders. How many people are familiar with latent space interpolation? OK, quite a few of you. And if you're not, it's quite simple. You take human inputs, and you train it through a neural network, compressing it down to an embedding space. So you compress it down to some dimensionality, and then you reconstruct it. So you're comparing the reconstruction with the original and trying to build a space around that. And what that does is that creates the ability to interpolate from one point to another, touching on the intermediate points where human may have not given input. So the machine learning model may have never seen an example that it's able to generate, because it's building an intuition off of these examples. So you can imagine if you're an animator, there's so many ways of going from cat to pig. How would you animate that? So we're trained, there's an intuition that the artist would have in creating that sort of morphing from one to the other. So we're able to have the machine learning model now also do this. We can also do this with sound, right? This technology actually carries over to multiple domains. So this is NSynth, and we've released this, I think, sometime last year. And what it does is take that same idea of moving one input to another. So let's take a look. You'll get a sense of it. Piccolo to electric guitar. So rather than recomposing or fading from one sound to the other, what we're actually able to do is we're able to find these intermediary recomposed sound samples and produce that. So it looks, there's a lot of components to that. There's a WaveNet decoder, but really it's the same technology underlying the encoder-decoder variational autoencoder. But when we think about the types of tools that musicians use, we think less about, training machine learning models. We see like drum pedals, right? Not drum pedals, guitar pedals, these knobs and these pedals that are used to tune and refine sound to cultivate the kind of art and flavor a musician is looking for. We don't think so much about setting parameter flags or trying to write lines of Python code to create the sort of art, in general. So what we've done, not just are we interested in finding and discovering new things, we're also interested in how those things get used in general, used by practitioners, used by specialists. And so we've created a hardware. We've taken a piece of hardware where we've taken the machine learning model, we've put it into a box where a musician can just plug in and explore this latent space and performance. So let's take a look at how musicians feel, what they think in this process.
Now, it does feel like we're turning a corner of what could be new possibilities. It could generate a sound that might inspire us.
The fun part is even though you think you know what you're doing, there's some weird interaction happening that's can give you something totally unexpected.
I mean, it's great research, and it's really fun, and it's amazing to discover new things, but it's even more amazing to see how it gets used and what people think to create with alongside it. And so what's even better is that it's just released, Ensign Super, in collaboration with the Creative Lab London. It's an open source hardware project. All the information and the specs are on GitHub. We talk about everything from potentiometers to the touch panel to the code and what hardware it's running on. And this is all available to everyone here today. You just go online and you can check it out yourself. Now, music is more than just sound, right? It's actually a sequence of things that goes on. So when we think about this idea of what it means to have a generative music space, we think also about melodies. And so just like we have cat to pig, what is it like to go from one melody to the next? And moreover, once we have that technology, what does it look like to create with that? You have this expressive space of variations. How do we design an expressive tool that takes advantage of that? And what will we get out of it? So this is also another tool that's developed by another team at Google to make use of melodies in a latent space, so how interpolation works, and then building a song or some sort of composition with it. So let's take a listen. Say you have two melodies. And then in the middle, you can extend it. And we really are just scratching the surface of what's possible. How do we continue to have the machine learn and have a better intuition for what melodies are about? So again, to bring it back full circle, we have, using different compositions and musical works, we're able to train a variational autoencoder to create an embedding space that builds tools that enable open source communities to design creative artist tools, to look at new ways of pushing the expressive boundaries that we currently have. This is, again, just released. It's on our blog. All the code is open source and made available to you, and also enabled by TensorFlow. In addition to all these other things, including Nikhil, here enabled by the type of work in creativity and expressivity. And so in wrapping up, I want to take us back to this demo that we saw. Now, the most interesting and maybe the coolest thing about this demo was that we didn't even know that it was being built until it was tweeted by Tero, a developer from Finland, And the fact of the matter is that we're just like barely scratching the surface. There's so much to do, so much to engage in, and so much to discover. And we want to see so much more of this. We want to see more developers, more people sharing things, and more people getting engaged. Not just developers, but artists and creatives as well. We want to explore and invent and imagine what we can do with machine learning together as an expressive tool. And so to go to our website, g.co/magenta. There you'll find our publications and these demos. You can experience it yourself and more. And you can also join our discussion group. So here's g.co/magenta. Join our discussion group, become part of the community, and share the things that you're building so we can do this alongside together. Thank you so much. So that's it for the talks today. We've had an amazing, amazing show, amazing spread of speakers and topics. Now let's take a look at a highlight review of the day.
Earlier this year, we hit the milestone of 11 million downloads. Really excited to see how much users are using this and how much impact it's having in the world.
We're very excited today to announce that DeepLearn.js is joining the TensorFlow family.
Swift for TensorFlow is also an early stage project, and so we'd really love for you to get interested and help us to build this future.
I told you at the beginning that our mission for TF Data was to make a library for input processing that is fast, flexible, and easy to use.
So I'm very excited to say that we have been working with other teams in Google to bring TensorFlow Lite to Google Labs.
In general, the Google Brain team's mission is to make machines intelligent and then use that ability to improve people's lives. I think these are good examples of where there's real opportunity for this.
you.